minute. Okay, Tere Humikost. Good morning to everybody. It's a really great pleasure to be here, and here a greater pleasure to introduce the first invited speaker of the day, Diego Torini from INAF in Italy. And Diego will tell us about elemental abundances in planet formation. Diego.
Thank you, Giovanna. So, in the public speaking manuals, they tell you that the first thing you should do is establish your expertise with the public. So I will start by apologizing and saying that probably the first slides of the talk are going to look very basic, but when talking to an interdisciplinary audience, the experience we had with the Ariel mission, but also in the solar system, is that it is always better to create a common ground and then start from there. So the first thing is connecting the topic of the conference, the connection between stars, disks, and planets, is a problem with a pedigree, because basically this genetic connection was established at the very beginning of the birth of modern astronomy, and then in the late 60s with the birth of modern planetary sciences with the seminal works of Safronov. But the problem, as we all know, is that until the 90s, depending who you ask, it could be 1995 or 1992, with the pulsar planets, we didn't know planets outside the solar system. So everything we had to reconstruct was based on what we knew about the solar system. And this created a number of assumptions that got inbuilt into our understanding of planet formation. And then we found the planets. And when we look at the planets, even if we have a huge number of biases in our knowledge, like, for example, the purple circle are the planets of the solar system, and they are basically completely in uncharted territory from an exoplanetary perspective, except possibly for Jupiter, is that we have a huge diversity, including planets that we were not expecting, like hot Jupiters or super-Earths that don't exist in the solar system. So the question that came out was, are these different products of the same formation process working under different conditions, or it's the evolution that changes the planetary system and creates this diversity? And then, fast forward 10 years, we arrived to the, well, 20 years. We arrived to the 2010s, ALMA starts working. We start seeing disk with resolving them spatially. And what came out is that we see a number of features that looks very like those that were predicted to form in disk when you have giant planets, massive planets embedded in the disk. It is still debated whether these are the signature of planets or these are signatures of where planets will form. But the point is, independent of this, on whether this is the starting point or the end point of planet formation, they are at tens, if not hundreds, of astronomical units. You know, in every single figure that you see there in the mosaic, there is a small white bar in the bottom right corner. That's the 10 AU scale, so that's the distance of Saturn. And as you can see, the features are much larger in scale. And this is not something we were expecting. If you ask people today, generally, they will still tell you that the planet forming region is up to 30 AU, much smaller, 3 pixels on this scale. And these are not just problems in terms of very high-level questions, because when we go down to population synthesis models that are a way to put together all the pieces and try to see if we can reproduce the diversity so we get the right picture, what we get is that no model today fully reproduces on its own the whole diversity of planets between solar system and exoplanets. On the left, you can see 4 population synthesis model. The two on the column on the left is planetesimal based. The column on the right is pebble based. Some models are better at reproducing the terrestrial planets, others are better to reproduce the cold giant planets. They all have different prediction for the hot Jupiters. So, is this something missing in the physics of the process or in our connection between the process and the environment? Because a lot of these models still assume a one-size-fits-all solar nebula model around a solar analog star, actually a solar twin star, which we know is not generally the case. So I was mentioning pebble and planetesimal accretion, so a very brief introductory note on these two processes. They both are mechanisms to accumulate solid bodies starting from the dust in disk and growing then to larger bodies that then accumulate and form the planets and the planetesimals. Because planetesimals are present also in pebble accretion. They are the seeds that will accrete the pebbles. The main difference is that in pebble accretion, you don't want planetesimal formation to be efficient because you want most of the mass in pebbles to have this continuous flux that feed your bodies where they are. In planetesimal accretion, conversely, since you have discrete units that need to collide over time, you want a lot of them and a very efficient planetesimal formation. When the planets grow, in both processes, it will end up in a point where it gets isolated from the surrounding solids. In pebble accretion is because at a certain point the planet will perturb the gas structure when it reaches the so-called pebble isolation mass, creates a dust trap, as you can see in the bottom left corner, and basically cut himself out from the flux of pebbles. And even if the planet migrates, it's still going to get cut out of the pebble because the trap will move with the planet. In planetesimal accretion, you still have an isolation mass, which is set by the gravitational reach. So when the planet clears all the region around it, it's not going to be able to clear anything. But if the planet has grown enough to migrate, then it will encounter more planetesimal and grow. So migration works differently in the two processes and is of assistance to grow in planetesimal accretion. The other main difference is pebble accretion works only within the gas disk because you need the aerodynamic drag to move the pebbles. Planetesimal accretion on longer time scales works only after the disk dispersal. So, for example, in the solar system, the terrestrial planet for a long time have been thought to be the results of planetesimal accretion because the radioactive dating of the Earth-Moon system gives a few tens mega-year as a time for formation of the Earth-Moon system. What happens when the planets get cut from the solid flux? At that point, it starts being more efficient in accreting gas. That doesn't mean it is absolutely efficient in capturing gas. It can be a very slow process, but it becomes a dominant growth process. And again, there is a difference between the two scenarios. Because in pebble accretion, because the planet is cut from the flux of pebbles, the main growth mode is the capture of gas. So the heavy elements that the planet will capture will mainly come from the gas. In planetesimal accretion, instead, planetesimal will be able to impact the planet and will do so. So we'll get a mixture of heavy element from the gas and planetesimal. In both scenarios, however, the key element is the interaction between the solids and the gas of the disk in order to control the formation process. But when we study exoplanets, we don't have the disk anymore. And as Camilla was introducing and Elisa also was mentioning yesterday, our proxy into the disk is the central star. And this is not limited only to composition, as we saw in the previous 2 days, but also to physical properties. So I know it's obvious for the audience here, but for people doing planet formation, sometimes it is not. Stars are different. There is a spread in masses, even in among different star-forming regions, as you see in the figure on the left, which is the histogram of star in 6 star-forming regions of different ages. There is a difference in the distribution of stellar masses that we can estimate. The empty red line that you see is the L1688 distribution for comparison. And then we have different metallicities, so different abundance of iron, which we use as a tracer of heavy elements, but is not exactly the same thing. And why it is important to know the mass and the metallicity? Because they control the total abundance of heavy elements available. The disk mass has been shown to be proportional, as the plot in the top left, to the star mass. There is a huge spread in this relationship. You see the vertical scale or the spread of the red dots, which are the dust masses with all the uncertainty of the case. In the L1688 star-forming region is huge. Is almost 2 orders of magnitude. But still, there is a proportionality. So at least we can estimate how much material there was in the disk from the mass of the star, or at least get an idea. While the metallicity controls the density, the local abundance per unit gas of the heavy elements. The other thing that we know is proportional to the stellar mass is the gas accretion rate. So the intensity through which the gas feeds into the star and govern the transport of material, because it is the main element that controls, together with aerodynamic drag, the drift of the pebbles. And this is important for two reasons. First of all, changing the disk mass intuitively changes the abundance of elements. And you can see, for example, in the population synthesis model on the left, different curves with the different colors are the same population synthesis model by pebble accretion working in disk with different masses. So the darker, the more mass. The dashed line is the effect of doubling the metallicity. And you can see the disk mass can change by an order of magnitude or more. Metallicity generally changes by a factor of a few, a top one order of magnitude if you spread the total range. So the effect of the disk mass is much more important than that of the metallicity from this point of view. Obviously, we cannot reconstruct one-to-one the mass of the disk. What we can do is basically estimate the average disk mass and then give an uncertainty. The gas accretion rate is important because, as I was saying, it feeds material, especially in pebble accretion. And again, the same population synthesis model on the left gives you the kind of planets that you can form in the classical mass semi-major axis diagram as a function of the time in which you put your seed into the flux of pebble. And what you can notice is that the later you move in time, so the later you put your seed, the darker the color and the lower the mass. You see that we go from, in the top we have the lighter color, so very early formed seed, and moving down we get the darker ones. That's because the gas accretion rate decays over time. Therefore, it is less strong if you put your seed at a later time. It's like I have a tap and I want to fill the bucket, and over time I'm closing the tap. Filling the same bucket will take a different amount of time. Again, this is a quantity that is connected to the stellar mass, but again, there is a huge spread, and the empty circle are just upper limits, so the range could be even larger than that. And this tells us an important thing, that time is an important dimension in planet formation, especially by pebble accretion, because it is very sensitive to the evolution of the disk. So we don't need to only sample where the planets start forming in the disk, but also when. And this is actually something that observational evidence confirms, or at least supports. So you already saw the plot on the top in Camilla's presentation. This is the relationship between the planetary radius and the stellar mass in planet host star. And there is this nice trend between the green, red, and blue lines that are increasing metallicity of the star. So less metal-rich star will form giant planets that are more rich comparatively in hydrogen and helium, so lighter element, larger radius for the same mass. And the more metallic you are, the higher the density of the material you capture, the less volume you need to get the same mass. Easy, nice, intuitive. Then you look at the mass plot, the one on the bottom. And you see there are attempts of correlation, and it's a mess. So there seems to be no correlation, but in reality there is an information hidden in this plot. If you look at the green points, or the green bars that are a bit more visible, you see that they are in the upper mass regimes of the planets. So giant planets forming in around low metallicity star are globally as massive as the most massive planets we form around high metallicity stars. And this is, we proposed back in 22, that it was an effect of time. So for low mass planets, we only see the planets that form in the very early phases, when there is a very strong flux of mass, your tap is completely open, and this compensated the low metallicity. And you can form your giants. As soon as the tap closes a bit, you don't form anything anymore. And you don't have the low mass giant planets. When you have metallicity, this compensates for the fact that I'm closing the tap. And therefore, I'm getting small mass giant planets. And that's why basically when you increase, you can see with the green and the blue, it's like the fit becomes lower. Like what? You get lower mass planets. No, you get a wider distribution, so the average value is lower. And if you compare it with the population synthesis results that we saw before, that's exactly what you will see. If you put your seeds in 10 to the 5 years into your disk, you get the highest masses. And this result tells you that this works the same in low metallicity and high metallicity stars. because the gas accretion rates has a larger variability than metallicity. Up to now, I only spoke about physics, which for a talk that is topic is the elements in planet formation might seem a bit off topic. And now we get into the composition. Because I was saying that we use metallicity to trace the abundance of heavy elements, but there's only iron, one element. And it was said in the introductory talks in the previous 2 days that in reality, the important planet-forming elements are 7. So we have nitrogen, carbon, and oxygen for the volatiles, and then we have silicon, magnesium, and iron for the rock-forming elements. And there is sulfur, that is the last element that produces mass. There is in reality another heavy element that gives a large contribution in mass, which is neon, but neon doesn't participate to planet formation, except for giant planets when you get it with the gas. And what was observed in the plot on the left is that low mass giant planets, roughly below 30 Earth masses, so 0.1 Jovian masses, which are the blue symbols, appear to be shifted towards stars with higher oxygen abundance, so the right part of the plot, because the oxygen over silicon ratio is the one on the x-axis, with respect to the giant planets from a previous work, which are the gray dot. Why is that? Because oxygen is the single element that contributes the most to the mass of solids. For the sun, oxygen contributes about 50% of the solid mass. Parts will go into the rocks and the rest into the ice when you form the solids. So increasing oxygen means increasing the dust-to-gas ratio, even if you keep the same amount of iron. And we tested this with a population synthesis model, which is the histogram on the right, which basically tells you we increase the amount of oxygen by a factor of 2, 0.3x. Yes, 0.3x. And you see the first 2 bars are the increase in total number of giant planets, and the total increase in the abundance of massive giants, 0.1 Jovian masses upward. The increase is modest, around 50%. Look at the small planets below 30th masses. They grow by 150%. And the small to massive ratio basically grow even largely. So why this? Because we are increasing the metallicity, and as I was telling you in the previous slide, we are increasing the abundance of heavy elements. So even if I'm closing my tap, the density of material that is coming out is still high enough to support the formation of planets. They will form later, so they can accrete less gas, because the tap in any case is being closed, but they still form. So composition is important also for the physics of planet formation. And that brings us to the compositional diversity of stars, because I'm not going to repeat what has been said better than what I could by Elisa and Camilla, but the point is we have different stars, and Camilla was showing this very nice 3D correlation between the abundance of carbon, oxygen, and nitrogen with respect to metallicity in star-forming star, in planet-host star. And the interesting bit that you can see in the plot is you can see the C over O ratio grows with metallicity. And the C over N ratio, which is the color scale in the right one, instead has an opposite trend. It decreases. You go to green for higher metallicity. This basically tells you that carbon grows faster than oxygen, and nitrogen grows faster than carbon. So you're changing your elemental ratio. And the star is the sun. The black cross. Meaning the solar abundances are not an absolute reference. And even if in exoplanet and in planetary formation, we tend to use the sun as a template, the prediction made using the sun as a template are not necessarily reliable. If I get a star around at 0.3 metallicity, it can have a C over O ratio that is 0.8. At 0.8, I measure the C over O ratio of the planet, it's 0.8. Okay, it's super solar, pebble accretion with the gas. In reality, it is stellar, which is generally the signipost of accretion of planetesimals. We actually have this with Jupiter, but I will show it in a later slide. So we have the elements of the star, and they control also some aspect of planet formation. But in the disk, we don't have elements, we have molecules. So we need to map how the composition of the star distributed the elements in the disk based on the pressure-temperature profile of the disk. And the classical view that everybody knows is that of the snow line. You move further out from the star, your temperature decreases, and at a certain point you hit a temperature where water condenses. And it is the transition between the red and the blue region in the infographic. From having only dust, you get dust plus ice. And this generally is not debated, but again, in a lot of cases, instead of fixing the snow line to the temperature, people think in terms of distances, like the famous 3 AU distance. That's only valid for a solar mass star with a solar luminosity around, with a solar nebula. The plot on the left shows you the temperature profile of 3 different disks that have been estimated through ALMA. And as you can see, they cross the horizontal dashed line at different points. So the position of your snow line can be at different places in the disk and also at different times, called disk cool down. But in this picture, where we have the snow line, we can do the same trick for all the elements. And generally, we do this for the light elements, like in comets. As you can see in the plot on the left, if you take the abundance of, this is relative to silicon, because silicon, it's always completely condensed in solids. You have the Earth, then you move to meteorites, and the abundance is increased. Then you go to comets, and there is an increase in abundance because you have the ice is condensing. And then when you compare it to the sun, you can see how much of the material or the element is in the solids. Like oxygen is almost completely in solid phase in comets. Carbon, not exactly. We think it is. Nitrogen is not. And there is uncertainty because it's the most volatile. And then if you convert these abundances, fractional abundances, into masses, you get something like the plot on the right, which tell you the condenser mass fraction, so the dust to gas ratio, where by dust I mean the real dust, the rocks and the ices, when you move away from the star at decreasing temperatures. Again, this is for the solar composition and one specific temperature profile. Your ziggurat will move to the left or the right and will miss some of the steps depending on what is your composition. But this picture is what people doing astrochemistry of disk call the inheritance scenario. So you form your molecules in the interstellar medium, a completely different pressure temperature condition. Your disk inherit them to star formation, and then you reprocess them in the disk. And the other element is that you have a very low irradiation, so you have an isolated disk. And this basically is the plot in the top left in the mosaic. The simplest possible chemical structure. If you move to the bottom left, you start having irradiation from outside sources. And you start seeing that the curves become more wavy, and in some cases you don't have the step-like function, but you have multiple peaks, meaning that you can have multiple snow lines. And you start seeing elements that should not be present, like O2, molecular oxygen. Then you can have flares, because stars can be active. And the flare is going to be a thermal wave crossing the disk, which might reset, that's the term they use, the chemical composition of the disk, top right. As you can see, you lose, for example, the water snow line, it shifts at 10 AU at this point, because you are dominated by molecular oxygen that remain in gas phase before. And you can make it even more complicated by adding external irradiation, bottom right. So you have high flux and reset, and it becomes a jumble. So again, when we think in terms of composition and mapping the composition of planets and disks, not all disks will be the same in terms of composition and thermal history, and there is no unequivocal way to say, oh, this is the composition of the planets informing this region of the disk. And disks, because they evolve in time in terms of the gas accretion rate, and this changes the accretional heating in the inner part of the disk, and the star changes luminosity over time, so the disk cool down, they evolve. So there is also no such thing as the composition of the disk. There is a composition at a given time in the life of the disk. And for example, these plots are 4 different regions of disk, like inside 2AU, inside the water snow line. Top right is 2 to 10, water to CO2. 1030 should be CO2CH4, and then 30 to 130 in this disk, specific disk, which is a large and cold one, you get CO and N2. As you can see, the inner region of the disk is a spaghetti plot. All the curves overlie on top of each other. These curves map the evolution of disk with different grain sizes from 0.1 micron, the size expected for star-forming region, interstellar medium, 20 micron, the starting grain size of disk, expected for disk, 100 micron, which is the large dust we think we see with ALMA, so not even pebbles. And you have a larger variation. In some cases, you see that instead of some curves, the color gets separated, so you have regions where you have different composition evolution depending on your inheritance over Z. But that's for another talk. The point is, you see the arrow time, so moving along the curve, one of these curves, you evolve in time in the disk, and the elemental ratio change. So it's not a straightforward one-to-one relationship. We need models, and basically it's like a retrieval. You get a range of solution and a certain uncertainty. But these are not only made by dust, pebbles, and gas. As I was saying, there is the planetesimal formation scenario, and we have some evidence suggesting that planetesimal exists. In the right plot, we have it from meteorites, which is the oldest evidence. So the one circle in the yellow, these are the iron meteorites, the first generation of planetesimal that form, geophysically evolved, differentiate, and formed an integral structure like the Earth. A metal core, a rocky mantle, and then a basaltic surface. And they form on a time scale of a few 10 to the 5 years. Because keep in mind, they don't only form. These dating measure when they differentiated, so when they geophysically evolved. So you need the time also to geophysically evolve in order to make this time span. And we see this in disk, because if you measure them, and it is the plot on the left, again the yellow region, because if you see class 01 disks that are still starting, and you try to estimate the abundance of dust, and then you get very young class 2 disk, the ones that we think of implicitly when we talk about disk, there is another of magnitude change in the abundance of dust. This can have observational explanation because it is very difficult to know if the dust is optically thick or thin. Same for the gas in reality. But there is a large decrease, and the mass that you have in this early class 2 disk is not enough to form planets because it is of the order of 10 Earth masses. So unless you have a 100% efficient process that forms only one planet, it is not enough. But, and the explanation for this is either the dust evolved to sizes we cannot see, and we will have this information with SKA that is going to measure much more reliably the dust in the centimeter size range, so we can know if what we see is just pebbles, what we don't see is pebbles. But they can also convert into planetesimal, in which case they remain invisible. So a non-detection with SKA will tell us something about planetesimals. And there's another information in this plot, which will be the subject of another talk, so I will just briefly mention it. You see in the top left plot that I circled a point that seems an outlier. That's the abundance of dust in disk in star-forming regions of 2 megayear old. The L1688 we were seeing before. And there seemed to be a resurgence. So you have that the disk at 2 million years have a higher abundance of dust than those at 1 million years. Not all of them, the dash is the median, and there is a huge range, but there seems to be this. It's not easy to explain this with pebbles, but planetesimal can do. And this is the flip coin of what was introduced yesterday with the disk transitioning between protoplanetary and debris disk. If you have planetesimal and you form a massive planet, you stir the disk, you start a collisional cascade, the same physical process that created the debris disk, in a moment in which there is a huge amount of mass around with respect to the debris disk. And what you get is dust. So at a certain point, you get this increase of dust if you have a large-scale disk. A debris disk inside the protoplanetary disk, if you want. And the fact that the peak is around 2 million years gives us an information, because in this disk around solar mass star, you need giant planets to stir enough dynamical excitation and produce this enough dust. And this is a signpost that the characteristic time scale with which you form giant planets is of the order of 1 to 2 million years. This is an indirect evidence, but the same process can be applied in the solar system to explain the other red circle. These are the chondrules. And I'm not going to go into detail, but we showed 2 months ago, actually, that the same process of collisional cascade can produce the chondrules if the planetesimal are stirred by Jupiter's formation. And the fact that the chondrules, the early formed one, at a very narrow range of time, matches exactly the time scale over which there is the peak production of chondrules stirred by Jupiter, which gives us a time scale of Jupiter formation of 1.8 megayear, which matches with the one we get from disk. So again, no proof because these are inverse models, but a strong indication that we are on the right way. So, okay. Planets, I mentioned, they migrate into disk. So until you are less than 1 Earth mass, which you will never see in a disk, you stay where you are. But if you become larger in mass than 1 Earth masses, you start migrating. And when you migrate, you cross different regions. And depending on your disk, for example, if you look at the brown and blue curve, the ones on the right, that's the planet starting at the same place in the disk, from the same seed in the same disk, just changing the metallicity. You can have a cold giant planet at a few AU or a warm giant planet inside 1 AU. And this changes where you accrete your material. In pebble accretion, you also have that the dust migrates and the ice sublimates when the cross-neutron line. So there is this process of enriching the gas in heavy elements. And if your planets accrete gas that is enriched in heavy elements, we'll get an envelope, your giant planets I'm talking about now, because they are the ones with the more direct connection with the disk. You will end up with a composition that is enriched in heavy elements. And you can see, for example, by the green circle points, these are planets starting at 30 AU and accreting this enriched gas, and they end up with a volatile to refractory ratio that is a factor of a few to tens supersolar. So this process is more efficient in getting heavy elements into volatile elements into the planets than refractories because you get them with the gas. If you have planetesimals, the story is different because then your planets move into the gas, but also into a sea of planetesimals. So you need embodied processes to study the efficiency of these. And the important bit in this simulation that I want to show is the bottom left plot. This is the fraction of mass accreted from different regions of the disk crossed by the planet. So every color is a different composition of the planetesimal, from rocky to enriched in volatile ices like CO2. And as you can see, it's not a flat line. It's not an average of what you get. It's a weighted average, the composition, depending on the efficiency with which the planet captures the elements from the different compositional region. And everybody knows about the C-overall ratio. And for once, I will follow what they suggest for public speaking, so not present the classical plot, not to propagate the bias. And there was this idea that was very clever and intuitive, that if I have different condensations of the volatile elements in different regions of the disk, I get a different signature for the planet forming there. This was done, however, starting from the star formation point of view 15 years ago. If we put the new information we have, new and old information we have for the solar system for meteorites, the Hayabusa and Osiris-Rex mission for asteroids, the Rosetta mission for comets, we get a different distribution than what we thought was the distribution of carbon and oxygen. Carbon and oxygen also have a refractory phase carrier. Oxygen, we know it goes into the rocks that are oxides. But there is also hydrated rocks, and they take a big chunk of oxygen, like 20%. And then there is refractory organic material, insoluble organic material, different names for the same things. Carbon or carbon-hydrogen chains that stay in rock form, so they are not volatile. If you count from these phases, the plot on the top tells you what is the C over O of planets forming, starting to form at 5, 10, 20, up to 130 AU. Green is for planets accreting only gas, purple for planets accreting gas and planetesimal. They are flat. You don't see migration because of the average. If you take nitrogen, which is more volatile, you have a high volatility contrast, and you can see the curves instead have divergence with migration. And the important bit about this is that if we measure things and we compute the ratios in units of the stellar abundances, so we normalize the ratios, accretion of gas and solids has different pattern. You see the colors are inverted. Blue, green, orange on the left, orange and red, green and blue to the right. So we get signatures when we normalize from the different formation processes. Last bit, 2 slides, and I'm done, is a word of caution about oxygen. Oxygen is a fun-loving element, so it goes with and reacts with every other element in disk and in atmosphere. In disk, if there is a thermal reset of the disk, oxygen goes in O2, remains in the gas phase, and what I want you to notice is in the 2 left plot, the blue and the red empty curves are the ones for a planet accreting only gas in inheritance, blue, and reset disk, red. And you see the curves are completely different. And in the top left, the C over O, the curves is supersolar above the horizontal line for inheritance, and below, subsolar, C over O, for the red one. So C over O can change a lot depending if you have inheritance or reset in the disk. And in atmosphere, especially if you go below 1000 Kelvin, you start forming dust, so silicates, using silicon, magnesium, and iron. And this sequesters oxygen. It goes into the dust that form the haze and the clouds. So if you don't account for these, you get a C over O wrong. And this is my concluding slide, because I thought better not to put take-home messages, because the field is very rapidly evolving, so everything I say is going to probably get old quickly. And the take-home messages in this slide are, we need multiple elements. We don't need just a C over O, because if you look at the left, the range of variation of C over O is at the most 2 to 3. That's a log scale. We need a contrast of volatility in the elemental ratio. And nitrogen for the volatiles is the best element you can get, because it's the most volatile of the 3. And if you use carbon, oxygen, and nitrogen, we can separate the paths of planet forming in different disks and through different mechanisms, the different symbols, if they form in the outer part of the disk. In the inner part of the disk, the first couple of AU, the situation is different because we also have the rock lines, at which point we want elements that are more refractory. One is sulfur, for example. And you can see in the bottom right, using data from a simulation by our group and Bertrand Bisch group, Ian Crossfield computed a carbon over carbon over sulfur ratio. And the top curves are the one for pebble accretion, the bottom ones are the one for planetesimal accretion, and they map into separate regions. And you also did the comparison with WASP-39b and the data from James Webb. As you can see, there is a difference, and they both don't match. So you want contrast in volatility and multiple elements. And all these ratios are normalized to the abundances of the star, otherwise you get biases if you use the sun. So that's the third message. You need to know the star and the planets, not just one of the two. And with this I conclude. Thank you for your patience.
Thank you so much, Diego, for this really fascinating and comprehensive talk. Questions? Yes.
Thanks, Diego. Very interesting. So you showed how the disk accretion increases with the stellar mass, and I think it was only reaching the data up to 1 point something. It was log scale. I couldn't see well. So my question is, with this pebble accretion or planetesimal accretion, if there is an upper limit for formation in the stellar mass for the formation of planets?
An upper limit to the formation of planets?
For the stellar mass. Because
It's the time scale of the lifetime of the disk. I don't have a number from the top of my head, but the shorter the time scale of the life of the disk because of the higher luminosity, the less time you have to form. If you go below 1 million year lifetime of the disk, chances of getting planets become very, very small, because you only get the really, really fast ones, and the shorter it is, the worse it is. So high luminosity star will have less longevity disk, and they will basically set the upper limit.
Question over there?
Thanks, Diego. More or less on the same subject. So you showed that the accretion rate and also the dust mass varies a lot for a given stellar mass. So by a factor of 100 or whatever the scatter, right? And the range of metallicities that we see in planet or stars is 1 Dx more or less the spread. So it's much smaller than the but we see a correlation with metallicity in presence of giant planets. So does this mean that the metallicity has a higher impact than the accretion rate or disk mass?
No, it means that what you need is the combination of the two, and you need to be above a certain abundance of the supply of material to the forming planet. Given that the accretion rate decays very fast in time, it is the most important factor at the beginning. After it goes below a certain threshold, it becomes metallicity more important. So it depends on the time scale in which you form planets. If the time scale that we see is, we think we see for giant planets is 1 to 2 mega a year, that's basically the time scale where you get a huge drop in the gas accretion rate and metallicity becomes more important. But you should also change the spectrum of the mass that you form. They are both important. It's the combination of the two.
Very quickly, because we're running out of time. Yeah.
Yeah. I think I disagree with this statement because what matters would be the overall budget of material that you have, and that is set by your initial disk mass. If the disk then accretes over time and you change your accretion rate by 3-4 orders of magnitude, it doesn't affect the initial budget, right? And the initial mass budget is essentially what sets the formation of planets, especially the initial solid budget. So I think the accretion rate in itself is not necessarily a tracer if you can build the cores by either pebble or planetesimal accretion. It should be the initial solid budget that we have available. And
yes,
that does not scale.
No, I agree. In fact, in the presentation, I said that you need the total mass of the disk, which gives you the total abundance, the absolute abundance. The metallicity gives you, for that abundance of gas, the density of solids. And the gas accretion rate controls how quickly, how efficiently the solids arrive to the planet. It's a combination of the three factors. I was just replying to this question about accretion rate and density, but there is also the dimension of mass. So there is a huge dispersion. Luckily for terrestrial planets, it's become probably less important, especially if they form by planetesimal accretion, because that's the amount of mass that you freeze in planetesimal that becomes the leading factor. And then it's a matter of if there is enough for forming detectable planets, or you stay with a debris belt.
Thank you.
Okay, let's thank Diego again. And now, well, perfect cue. We're now moving to the second talk of the day by Benjamin Bisht. And he will tell us about exploring star-planet disk connections, and in particular the limits of planetesimal formation and low metallicity.
Yeah, thank you very much. I will talk about the limits of planetesimal formation at low metallicity. As you know, my visit here is sponsored by the Cost Action. If you have more questions about this, feel free to ask. But now let's focus here on the science. So what we're using a code that can simulate a lot of different things. It's called ChemComp. Essentially, it's a 1D viscous disk evolution code. Includes a pebble, growth and drift, following the model from Birnstiel. We have pebble evaporation at these condensation lines, as Diego already introduced. So as the pebbles drift inwards, they would evaporate and release their volatiles into the disk. We're simple-minded people. We only have a simple chemical partitioning model, so we don't have a chemical evolution in our code. But I'll come back to this in a little bit. Then from a planetary side, we can grow our planets by pebble accretion, then followed by gas accretion, limited by essentially what the gas disk can provide. And the planets migrate, and the code is also publicly available, so you can just go into GitHub, download it. It's written in Python, so good for the younger generation. Good, so I want to introduce a key concept of this code, and this is related to pebble drift and the evolution. So what you see here in this plot is the radial velocity of the gas in the dashed line and of the dust as a function of the Stokes number. So the Stokes number is essentially the aerodynamic properties of the particles. So we have the small dust grains, the micrometer-sized dust grains. They are perfectly coupled to the gas. They follow the flow of the gas. Or if you have bigger pebbles, then they would actually decouple from the gas. They would lose their angular momentum via gas tract and drift inwards much, much faster than the dust. You see here, depending if you have a Stokes number of around 10 to the minus 1, you can be like 2.5 orders of magnitude faster going inwards than the gas. Now, we didn't include chemical evolution in our code because in this model from Eistrup and Henning from 2022, they modeled the inward drift of pebbles and traced the chemical composition of these pebbles. So the different colors gives you different elements, and the different line styles will give you different drift velocities. But most of the time, the pebbles actually drift very fast, and this is the this small dashed line. So you see as the pebble goes inwards, they don't really change their composition. Only at a certain point, they change the composition completely, and these are actually the evaporation fronts. So if you follow the blue line for water, you retain your water in your pebble, but then at some point in the inner regions of the disk, your disk becomes hot enough, and you release your water as a volatile into the disk. So we think that as long as the pebbles can drift freely through the disk, the drift essentially wins over the chemical reaction timescale, and you do not have to take this into account. However, the moment you have bumps in the disk and you could store the pebbles for a long time, then chemistry probably will start to matter. So the consequence of this inward drift is actually that you enrich the inner disk with water, for example, right? So in this plot, you see the time evolution of the water content in the gas phase as a function of orbital distance. In the outer region, you have no water vapor in the disk because everything is frozen out, so you have the water ice. And then as time goes on, the pebbles start to drift inwards, and then they evaporate and release their water vapor into the inner regions of the disk. And you see we can have a very, very large enrichment of water, factor 10, factor of 100 compared to initial water content. And this is directly related if you compare the drift velocity between gas and dust. So the dust pebbles, they go in a factor of 100 faster than the gas. So obviously you get an enrichment of your vapor by a factor of 100, because once your water ice evaporates, it's a gas, it's a vapor, so it will not drift fast, it will drift slowly. However, in time, you see there's a color gradient, and this is related to the fact that at some point your disk runs out of pebbles, so you cannot push more and more water ice-rich pebbles into the inner disk, and your water content goes down as a function of time. So essentially, the disk composition evolves over time. But now I want to focus a little bit on the formation of planetesimals at low metallicity. So in this figure from Bowley and Al, they look at the occurrence rates of planets as a function of Fe over H. You see we can make a lot of planets at high metallicity, but the moment you go to lower and lower metallicities, you actually see that you have less and less planets. And the question is, why is that? Or is this actually in agreement with our theory? So there's different models how you can make planetesimals. But essentially what all these models for planetesimal formation require is that you concentrate your pebbles in a certain position in order to make planetesimals. Now what we do is we follow this model from Trzaskowska et al. 2016, where the idea here is that the pebbles go inwards, then at the water ice line they can release their water ice, they become smaller dust grains, they drift slower, so you can actually accumulate a lot of particles in the inner disk region, essentially think of it like a traffic jam effect. And additionally, the water that is released by these pebbles can diffuse outwards, recondense onto the pebbles, and increase the pebble surface density in this region so that we can achieve a high solid-to-gas ratio that allows us to make a lot of planetesimals. Now, in addition, you see all these different models. They produce planetesimals at different regions. But they're all done for solar environments, solar metallicities. And what I want to do here is I want to look at low metallicity environments. So what we did is we run some simulations. We have the inward drift of the particles, and then we start to make planetesimals at the water ice line. So in this figure from Andama et al. 2024, we look here at the evolution, the time evolution of our dust and pebbles in the disk. So they start with a disk that has a relatively high mass, the pebbles drift inwards, they accumulate at the water ice line, and once you reach a high enough dust-to-gas ratio, we will start to make planetesimals. And you see here, so the different line styles correspond to different dust-to-gas ratios, so this is the real metallicity, and what you see is the moment you reach a metallicity of around 0.5%, we don't make any planetesimals anymore. If you have a higher dust-to-gas ratio, we can make planetesimals. Maybe not too many. Here's just a few Earth masses of planetesimals, but that's okay if you want to make super Earths. And additionally, of course, these planetesimals could continue to grow also by accreting pebbles. And you see here, actually, we have a relatively high pebble mass. Even at the late stages where we start to form planetesimals, we still have a pebble mass of 50, 60 Earth masses of pebbles. So these planets could actually start growing, even if you just make a few Earth masses of planetesimals. But now the question that we were interested in is, how does this overall picture actually change if you change the water abundance? Well, the first is the motivation. So how does the water abundance change as a function of Fe over H? So in this figure, we plotted the stellar host star abundances, the C over O ratio as a function of Fe over H. You see there's a trend with the C over O ratio that higher metallicity stars would have a large C over O ratio, while lower metallicity stars would have a low C over O ratio. But this has a direct consequence for the water content, as you see here. So for the high metallicity stars, we actually have a very low water content, and this is related to the fact that carbon would take a lot of oxygen to make CO, CO2, so we have less available for water. And as you go to lower and lower metallicity, we have a lower C over O ratio, and therefore we get more water. However, this line here is derived for this black line, so for the average. But you see there's a large spread actually in the data. So what we are doing now is we're actually varying the C over O ratio in our simulations to see how that influences the formation of planetesimals. And this is what we see here. So here, if you just focus here on the bottom row of the plot, we have here the different metallicities, dust to gas ratios, 0.7, 0.6, 0.5, and 0.4%. And we have here our three different C over O ratios that we test, where the mean C over O ratio corresponds directly to the value here, and the other one are just like values above and below. Now at this relatively high dust to gas ratio of 0.7%, we see actually all our simulations start to make planetesimals. But if you go to lower dust to gas ratios, you see that the simulation with the high C over O ratio doesn't make planetesimals anymore. Then if you go to an even lower dust to gas ratio, only the simulation with a low C over O ratio starts to make planetesimals. And this is related to the fact that this low C over O ratio means that we have more water, and more water allows us to make planetesimals more efficiently. And we can actually see this directly here in this plot. So in this plot, we show our different C over O ratios that we tested against the dust to gas ratio. And the numbers essentially gives you the amount of planetesimals in Earth masses that we form in these simulations. So the first thing is that you see there could be a possible trend with the formation of planetesimals, not only as a function of the dust to gas ratio, but also as a function of the C over O ratio. You see at these relatively low dust to gas ratios, you need a low or a C over O ratio to still make planetesimals. However, if you go to larger dust to gas ratios, sure, there's a difference with the amount of planetesimals that you make. But I mean, the moment you make 80 or 100 Earth masses in planetesimals, it doesn't matter, you will still make a giant planet because you have totally enough material to do this. But it could imply that for these low metallicity stars, that the planets around low metallicity stars should predominantly form around stars that have a lower C over O ratio. This is something that could in principle be tested by observations. Now this already brings me to my conclusion. So everything in the disk moves, gas, dust, pebbles, planets, nothing is static, all moves. The inward drifting pebbles, they will evaporate and then enrich the disk with water. We can use the formation of planetesimals at low metallicity to understand if the water iceland is the birthplace of planets, because if you find something else from an observational perspective about the occurrence rates of these planets, then of course our model might not be correct. And we make the prediction that the low metallicity planet host should harbor a low C over O ratio. And if you're interested in the model, ChemComp is a very versatile tool that can be used to study protoplanet disk evolution, planet formation. It's free of charge. You can just download it from GitHub and use it. We published a lot of codes about it. And of course, if you have questions about this code, you can of course always email me. And obviously, I want to acknowledge my sponsors from the cost action, and I'm happy to take any questions.
Thank you so much, Bertrand, for this great talk. Questions? Yeah.
Great talk. In your model, I saw that carbon is mostly in methane and nitrogen is in ammonia. How important is this assumption? Because, I mean, in comets, there are mostly in CO and N2.
Right. So in our original model from Schneider and Bitsch, indeed we put a lot of carbon into the methane, but actually in these models we actually have much less methane because we revised our initial distribution because we learn more as time goes on. So actually most of the carbon would actually sit in refractory carbon grains. Then we have a little bit of methane, and then of course the CO and CO2. The nitrogen in itself sits mostly in N2 in our simulation. We have a little bit of NH3, but in the end, for this type of models, it doesn't really matter too much because the nitrogen, even if it's in NH3, would evaporate beyond the water evaporation line, so it cannot contribute to the formation of planetesimals at the water ice line within this scenario. So for this, I think it doesn't really matter too much.
Okay, thank you.
Time for a quick question over there.
Thanks, Bertrand. So we could try to search for very small planets at low CO ratios in the thick disk, because these stars have higher oxygen than carbon. But then still there will be a limit in the iron abundance. So because as you go to lower and lower iron, then you have more difference between the oxygen and the carbon. So we want oxygen-rich stars. Then where we should put the limit in iron, in metallicity?
So in iron, probably it would be like a minus 0.4, 0.5, I guess. I mean, what we care here really about is the overall amount of material that we have. So the iron abundance in that sense doesn't really matter. It's really just a question of the overall amount of material, like, for example, also what Andrea was talking about yesterday. Because to make planetesimals, for example, we don't really care if it's silicate, magnesium, or iron. It doesn't matter. It's just the total amount of material that would matter. But then on top of that, we need a higher oxygen to have water. So it's really like if you look here, right, really look at the dust to gas ratio. It's not Fe/H. It's really the dust to gas ratio. So you could have stars that have a different iron abundances here because they just come out with the same overall amount of material because they compensate by, for example, having more oxygen.
Okay, let's thank Bertrand again.
Thank you.
So our next speaker is Daisy Turner from the University of Birmingham, and she will tell us about investigating star-planet compositional ties for systems with host stars of varying composition.
Hi, I'm Daisy Turner, and I'm from the University of Birmingham. I'm a PhD student there, and I work with Annelies Mortier. And today I'm going to be talking a little bit about investigating the compositional ties between stars and planets for systems of host stars of varying composition. So stars and planets, they're formed in the same environment, so it's often assumed that there is a relationship between their compositions. And many studies have found such relationships, one-to-one, things more complex than that. But a common feature of these studies is a lack of homogeneity in both the stellar and the planetary side, and also a relatively small sample size. So I work on expanding the sample, particularly with a focus on the homogeneity of both planetary values and stellar parameters as well. I have around a 50% increase in sample size compared to other studies that work on similar things. And because I'm measuring stellar abundances from such stars, it's important we get precise and accurate values. So I focus particularly on FGK stars and those that I consider bright. So in this context, that's those with a V magnitude of less than around 12. So here I show the approximate mass compositions of 3 solar system planets, Neptune, Mercury, and also Earth. And these are approximate, this is just a schematic. And typically when we're discussing the interiors of exoplanets, we make reference to the 4 main layers. So here, an iron core, silicate mantle, an icy layer, and also an atmospheric layer as well. So for rocky planets, this 2-layer assumption is a decent approximation, as it limits any sort of potential icy layers and atmospheres. So I limit my sample to anything with a planetary radius of less than around 4 Earth radii. And this allows me to study super-Earths and also some sub-Neptunes as well. And the particular abundances that I focus on the stellar side are selected based on the interior layers within these exoplanets, particularly the iron from the iron core and the silicates that reside within the mantle, so magnesium, silicon, and in some contexts, titanium as well. And all these elements are just those that are formed via the alpha process within stars. And we wish to look at systems that are have a span a wide range of this alpha to iron ratio in terms of the host stars, because this allows us to do a comprehensive study on planetary and stellar composition. So here I have plotted a population which is representative of the thin and thick disk stars within the Milky Way. On the x-axis we have our iron abundance, on the y-axis is this silicate to iron ratio. You can see above the dashed line here is the thick disk populations. These are the older, more metal poor stars, and anything below the dashed line are the thin disks, so these are the younger, more metal-rich stars. For the particular host stars in my sample, I'm looking in terms of subsolar metallicities initially anyway. And you can see that when we are looking in terms of this iron abundance and this alpha to iron ratio, we see that at these subsolar metallicities there is more variation in the alpha enrichment along this y-axis here. So by initially focusing on this, these subsolar regions, it allowed to do a study stars that occupy the entire sort of range, and which this is needed to do a comprehensive study. And as you can see that as we go to more iron poor stars, they typically are more alpha enhanced. So another way we can classify what thick disk versus thin disk populations is with kinematics. Here I've plotted my sample on top of this previous population of the Milky Way, and the chemical and kinematic populations are pretty consistent between them as well. You can also see that I've got covered both the thin and thick disk populations, pretty representative. So in total, as a summary of my entire population, I have around 53 stars hosting 75 planets. The initial planetary values from the sample were taken from the Planet S database presented by Park et al. In a 2024 paper. And in order to be included within this database, the planetary masses and radii have to have relative abundances of less than 25% and 8% respectively. So this ensures that we're studying well-characterized, precisely characterized systems. In the interest of homogeneity, from the stellar side, we are independently measuring anew all of these stellar abundances, and also masses and radii of these stars are being recalculated thanks to Alex Frackleton. And we use these new stellar values to recalculate new planetary masses and radii as well from the observables. Here I've plotted all of the sample in a mass radius diagram alongside some constant composition lines from Zheng and also Chen and Rogers. You can see that we have, yes, super Earths and sub-Neptunes within the sample as well. And these points are colored by a metric called the stellar iron mass fraction. And this is a proxy for essentially for stellar composition. It's defined as such. And it's essentially the ratio of iron within a star to iron and all of the sort of silicate molecules that we expect to find within planetary, exoplanetary mantles. This is calculated using the abundances that I measure from the stellar side using the Aries-Moog method. For comparison's sake, we can look at another study that has done this before. So again, on the x-axis, we have this stellar composition, this planetary iron mass, this stellar iron mass fraction, sorry. And on the y-axis is a proxy for stellar composition. So it's sort of a scaled density. And you can see that it's essentially to account for sort of planets of different masses and different compositions. We aim to fill in this low stellar iron mass fraction regime, particularly anything below around 29%, to see if relationships such as this still hold. So here I plot my super Earths for my sample, and this is anything that's below the radius valley, the system-dependent radius valley from Hohen van Allen. I'll address the elephant in the room now. The X abundances, the errors on them are rather large. So this is again the stellar iron mass fraction on the x-axis and the same scaled density value on the y-axis. The reason for these large errors is it includes the the fundamental and inherent errors that we get from measuring stellar abundances, also folding in errors on the solar abundances that are used to calculate these relative abundances as well, and from atomic parameters that are also included with our models. And we also filled in, again, below around 29% iron mass fraction, this low iron mass fraction region. We can also add in the sub-Neptunes now as well. So we can see that there are sort of two distinct populations. We have at these higher densities or higher scale densities, the super-Earths, and the low density region with the sub-Neptunes. But it is also apparent that this two-layer assumption that we made before of the planets being made up of just like a core and a mantle breaks down when we're starting to consider anything with an atmosphere. So these sub-Neptunes, it's a bit silly to just consider they're made up of a core and a mantle. So we can use interior modeling codes in this case of the study, like Planetic, described by Joanne Egger in a 2024 paper, to model the mass fractions of the interior layers of all the planets. So now this allows us to consider an iron core and a silicate mantle as before, but now we can also pay attention to this icy layer and an atmosphere. Again, this is a schematic. This isn't an accurate representation of the masses of these things in exoplanets. Okay, so we can now get a planetary iron mass fraction. Again, here I've plotted just the super-Earth, so anything below the radius valley. And we can see that they occupy pretty much the entire range of the planetary iron mass fraction that we expect for these rocky planets. But there's no discernible link from these data in this state between this stellar iron mass fraction and a planetary iron mass fraction. So now adding in the sub-Neptunes, we can see that they occupy this low planetary iron mass fraction. They gathered at these low values. This adds evidence or backs up previous evidence that the sub-Neptunes aren't just super-Earths with an atmosphere added on top, that they are fundamentally sort of different planets. And we can see this as well when we look in sort of radius valley space. So again, anything below this is a super-Earth, anything above this is a sub-Neptune. And we can see that as we look from the super-Earths all the way up to the sub-Neptunes, there's not a smooth gradient of this decreasing planetary iron mass fraction. They are distinct populations in terms of that parameter. So I'll go over my conclusions now. Thank you for listening. So essentially the link between stellar and planetary composition for, in particular, super-Earths and sub-Neptunes, if you include them all in one study, is too complex to be captured by a singular linear relationship. And most importantly, I think from this talk, the uncertainties on stellar abundances are often underestimated, and it's important to consider all the different factors that go into that. And also, four-layer treatment of planetary interiors, it provides deeper insights into the composition of super-Earths and sub-Neptunes and what we can say about their two distinct populations. Also, a shameless plug, I published a paper last week on the mass of an exovenus. It's Venus size, Venus mass, Gliese 12b, so please check that out if you've got time as well. Thank you. I'm happy to take questions.
Thank you very much, Daisy, for this very interesting talk. Questions? Well, perhaps then I have a question. Very interesting to see this separation between super-Earth and sub-Neptune. Do you think that perhaps in the future with more also measurements or better uncertainty, one can see even more classes among these two big classes?
It'd be interesting to look at, yeah. We're looking at using different ways of modelling the interiors, not just planetic, other different methods as well. So in the future, yeah, especially reducing these uncertainties, it'd be nice to investigate. I've not thought about it, but it'd be good to see. Yeah.
Great, thank you very much. There's a question there.
Yes, hello, thank you. Very nice talk and work, but could you say what are the uncertainties of your stellar abundances in DEX? I mean, you showed them as the iron mass fraction, but what were the original ones that you get from?
Typically, the ones that we're interested in, they're getting a relative mass fraction, a relative abundance error of around between 0.05 and 0.1 dex, I'd say. Off the top of my head, I can double check and get back to you.
Okay, so that's quite like normal.
Yeah.
But and what do you think is the most important thing to improve to get to bring down these uncertainties in the abundances?
For this particular metric, I'm not of stellar iron mass fraction because you have to include things like solar abundance, the error on the solar values and things like that. I'm not too sure if that metric, the error, can be reduced on it. Maybe it'd be better to consider different metrics. But in terms of the abundances themselves, reducing errors, I think those are the inherent ones. I don't know if they're possible to reduce, but thank you.
Excellent. Thank you so much, Daisy. Our next speaker is Giulia Ricciardi from ESO, and she will tell us about compact or large CO observations of the faintest planet-forming disks.
Oh my God. Can you hear me? Great. Okay, so hello everyone. My name is Giulia Ricciardi. I'm a second-year PhD student based at ESO in Germany under the supervision of Anna Miotello. And today I want to talk about the first project of my PhD. So now, thanks to ALMA, we have significantly enhanced the disk sample size by targeting many disks in many nearby star-forming regions. And now one of the main results, unfortunately carried out with short integration time, is that most of the sources seems to be fainter than expected in continuum and CO emission, resulting also in, maybe I can use this, in what seems small structures. Now, whether we are observing the tip of the emission of an extended disk with low surface brightness, or this structure are indeed radially compact, is not yet constrained. Nevertheless, it is crucial to distinguish between these two scenarios because of the implication on disk evolution. Now, the idea that faint could mean small is not new. In 2014, PLATO and others observing T Tauri disks found out that for about half of their population, they couldn't detect CO emission. And this also resulted in a very faint continuum emission. 2 years later, Berenfeld and others, observing another sample, this time in upper scope, they come out with the same result, also estimating that this faint emission is usually coming from an emitting area that is usually smaller than 40 AU. Now, the problem is that up to that point, the models were biased towards more extended and brighter disks. Now, just to give you an example, on the left, I'm showing you the models run with DALI in 2016 to explain the observations done in lupus. And as you can see, this grid of models were taught for extended structures with the critical radii bigger than 13 AU. But if we look at the plot, we see that we cannot explain the line luminosities for the 12 CO and the 13 CO observed in lupus. 5 years later, here on the right, they created a new grid of model, this time taught for intrinsically small structures, so with the critical radii lower than 15 AU. And it seems that finally we can somehow predict such low values. But I know what most of you are thinking, so let's talk about the elephant in the room, CO depletion. I must say it's appealing, and it's basically the reason why there is a gap of 5 years between the first grid and the second grid of models. For many years has been thought that this is the main responsible for these low values. But the truth is that after we studied this suspect for like many samples and many regions, the depletion factor that we need in order to get such low values are usually pretty high, like hundreds or thousands. So recently, it has been said that probably this is not the only reasonable, and also we have an alternative path, compact structures. Okay, but why do we care? Well, if we put all together, we ended up with a plot that more or less looks like this, where we have different colors for different disk masses, and the marker, that, the size of the dot that scales with the disk extend. So smaller the dot, smaller the disk. And we can clearly see two trends. In purple, the compact population, where we see that the 12CO and 13CO line luminosities scale linearly, meaning that the two tracers are optically thick, therefore CO emission scales with the emitting area, and if we see something faint, it's because it's small. On the other side, in magenta, let's say, the extended population, where we see that at some point, no, it's not visible, the trend deviates from the linear behavior, and it's because the 13CO becomes optically thin. So in this case, CO emission is proportional to the column density, and therefore if we see something faint, it's probably because we are observing an extended disks with low surface density. So now we have two scenarios that are key for different properties. In the first case, we can exploit the fact that CO emission scales with the emitting area. Therefore, we can use CO emission even though it's not resolved, meaning that we can ask for moderate resolution observation, to directly link the integrated flux with the disk extend. Instead, in the extended case, we can use CO emission for other things like gas masses. But if we want to get an idea of the disk extend, we must resolve CO emission. Now, keeping this in mind, in order to somehow address this open question, 2 years ago, Miotel and others asked to observe the faintest end of the disk population in lupus, that you can see here in red. And the idea was to go for lupus because it's low mass, low density. So in principle, we can neglect the external photoevaporation due to massive stars, but also the truncation due to encounters such as flybys. And also the sample was designed in order to neglect the disks in known multiple system. So in principle, we can also neglect truncation due to a presence of a companion. And just to give you an idea, if we go through this beautiful gallery for the continuum by Ensdel et al. 2018, you can see in brighter the final sample selected that already seems pretty small in the continuum. This is what the sample looks like in the gas instead. We have moment zero maps for the 12CO and the 13CO, and also in gas emission, it seems that we are seeing something faint. If we go through the maps, we see that the 12CO is always there, it seems small, and the 13CO is always fainter and not even detected all the time. So what I did was to go for fluxes first, so I could compare like my sample with the models, and then in order to confirm whatever, I went to the radii. So for the brightest sources in my sample, such this beautiful example, what I could do is to use a shift and stack technique that basically allows you to enhance the signal to noise, boosting the faint signal. And you ended up usually with an integrated spectrum here in purple that you can use to estimate the integrated flux, so what we want. For the faintest source instead, this technique simply fails because it's too, the sources are too faint. So we need to go for something simpler. And in this case, what I did was just to consider the moment zero maps, draw an elliptical mask on them as inclined and as big as the beam, and just extract the flux coming within that region. And finally, I can show you the results. So we have the models in the background in gray as a comparison, the sample by Ensdel et al., because it's still the most complete sample of lupus. And you can see as QT stars, my sample has triangles D detection only for the 12CO and has 2 crosses non-detection in both the molecules. And if you look at the location of my sample in this diagram, we can already say that it seems that 12CO and 13CO are optically thick. And we also have hints of potentially compact structures, because we see the blue sky stars that, and there is a good comparison with the compact grid model. But as I was saying, in order to confirm that, we need to go for the radii. But before I do so, spoiler, you will also see dust. And this is because we know now that dust evolution can affect CO chemistry, and therefore can affect the outer radius of the gas. That is what I'm interested in. So I must take into account this factor. And of course, there have been many studies about it. I'm here showing you the one by Trapman et al. 2019. And the 2 key things that I want you to remember, because are important for my result, is that when you consider dust and gas together, you must take into account that we have different optical depth effects, and this is usually because dust is coming from millimeter grains, so usually optically thin, and instead for the gas I'm considering CO emission, so usually optically thick. And that if we consider the size ratio, so the gas radius against the dust radius, we only have strong evidence of dust evolution if this value is bigger than 4. Okay, so before we jump to the results, let me just go through these slides. Basically, in order to get the gas radii, what I did was to consider the image plane, and this command by CASA that allows me to fit a 2-dimensional elliptical Gaussian, that among other things gives me the total fitted flux and the disk extent. So I define the radius as the disk extent that encloses the 68% of the total flux. And for the dust, I basically went from the image plane to the UV plane, and I used Galario to fit the millimeter emission. So let's jump to the results. I can finally say that these structures are compact. The gas radii are always lower than 40 AU. And if we see the plot here on the left, we can see that overall my sample seems to show a size ratio between 2 and 3, which is in agreement with what was found for lupus so far. But more importantly, that we never see a ratio bigger than 4, so we don't have strong evidence of dust evolution. If I show you the luminosity against the radius for the 12CO, we can see that there is a monotonic positive correlation, which is expected because, the 12CO is optically thick. And lastly, I want to show you the size ratio against other properties, such as stellar mass, sizes, disk masses, but we don't see any clear correlations here. So since I don't have time, I'm going to just leave you with the conclusion, and I'm more than happy to answer whatever question.
Thank you so much, Julia, for this very interesting talk and for being in time. Questions?
Hi, network. Is there any effort to compare with the older subfamily regions, like maybe upper scope, to see whether the dust evolution starts later or so?
I wish I could say yes, but the thing is that, you have to submit proposals for ALMA, and you have to be accepted in order to do this kind of comparison. Now, the sensitivity that we have for the older regions doesn't allow me to do a direct comparison, so no. But of course, it's very important.
Yep, a very nice talk. So I'm just wondering, so this radius of the CO divided by the radius of dust, if it's smaller than 4, essentially it implies that you don't have the dust evolution, you don't have the drift, but why is the ratio 4? Where does, could it not be 2 or 8 or?
In this paper, 1 second, so Trapman et al. 2019, basically there is a huge section where they discuss why it's 4, but basically the bottom line is that they ran different models and different simulations, and they saw that only for values bigger than this threshold, they could disentangle the dust evolution from the optical depth effects.
Okay, thank you.
Other questions? One here.
So in the conclusion slide, you mentioned that the small gas disk radius may be a challenge to the standard disk evolution model, but I thought that the compact gas disk radius is consistent with the wind-driven accretion models. So,
yeah, very good question. No, this is still a work in progress. What can I tell you is that so I was considering both the viscous case and the MHD driven theory. And for the viscous case, it seems that indeed we can predict this kind of compact structures, but the thing is that it really depends on the alpha parameters that you use. It's still a work in progress because I can compare directly with the models, so I can get an idea of what kind of alpha I need in order to get an RC of, let's say, 15 AU, which was the threshold in the models, at 2 megayears, so at the time of lupus, at the age of lupus. But the thing is that we need a relationship that links RC to RCO in order to compare this thing directly with my data. So I still don't know which range of alpha I can accept. It's reasonable to have like compact structures. And for MHD, it's a mess because you have to go into simulations. I'm not an expert, but what I can tell you is that, yes, in principle, there the mechanism is different because it allows you to have compact structure from the beginning, and you just keep the size more or less the same, just removing, mass. But you kind of need really stringent initial conditions. So like values that seems to not agree with like accretion rates or other parameters that you can observe. You're welcome.
Okay, let's thank Julia again. So the next talk will be given by Heather Johnson from the University from the University of Exeter, and she will tell us about the rise and fall of the giant planet occurrence rate.
Yeah, thank you. Hello everyone, I'm Heather Johnson from the University of Exeter, and I am going to be talking about the rise and fall of the giant planet occurrence rate, but I'm also going to be talking about the impact of stellar luminosity on giant planet formation. So as we know, we have a ton of recognized planets in the NASA archive, over 5,000 now, I believe. And there's also been statistical studies to sort of imply that there's, for at least every star in the Milky Way, there's at least one planet. However, only a very small proportion of these are giant planets. So why am I interested in giant planets? They contain the majority of the mass and the angular momentum within the planetary system. This means that they're responsible for shaping the architecture of planetary systems and of debris disks. We also think that they played a significant role in the dynamical evolution of our solar system, so perhaps aiding or hindering the habitability of Earth through volatile delivery. And most importantly, they are rare and only found around 10 to 20% of stars. So this is why I am also interested in intermediate mass stars. So the RV giant planet occurrence rate peaks in the range of intermediate mass stars around 1.7 solar masses. And we also know that intermediate mass stars evolve very differently from their low mass counterparts, which is what we've been hearing in the last few sessions today. So the radiation mechanisms are different. So they have convective versus radiative zones, and this means that the heating is different, and this then impacts the disk. So while giant planet formation is ongoing, we have this pre-main sequence stellar luminosity also happening concurrently, and this can affect disk temperature, structure, and also kind of dictate of what kind of planets can form in a system. So here is a cartoon of an HR diagram. So we have temperature on the x-axis, we have luminosity on the y-axis, we have the birth line right at the top, and then at the bottom we have the zero-age main sequence. And you can see for very low mass stars, like 0.5 solar masses or so, they remain fully convective throughout their lifetime. If we have something that's more close to our sun, we end up developing a radiative core, and it has a convective envelope surrounding it. And you can see that over time, well, at least during the pre-main sequence phase, it's dimming in luminosity and then remains fairly constant before it increases, developing this radiative core, and then that's when it enters the main sequence. Where we have something that's, you know, around 1.7, where we find this peak of the giant planet occurrence rate, and then even more massive, where we start to get the fall off of the giant planets as a function of stellar mass. We have these sort of stars that also initially dim with luminosity, but then they travel sort of horizontally across this HR diagram where they are increasing in luminosity, and this impacts the disk. So in the terms of the disk, we have a cartoon here where we have the star, we have the disk, and then we have, you know, all of our dust grains, which have some sort of volatiles usually frozen out onto the ices. Then we have, you know, a condensation line. Inward of that, everything is like evaporating off. And then also if we have a more luminous star, which is like heating the disk to a greater radial extent, that's going to push this snow line out to greater locations. And that's going to be really important in terms of composition of both rocky planets and of giant planets, where these giant planets are like actually accumulating the bulk of their gaseous content. So the paper that we were working on, we were basically comparing these fixed luminosity models to the pre-main sequence evolution models. So here we have radius on the x-axis, we have planet mass on the y-axis. The blue lines are roughly estimates of the water snow line, which is in the viscous part of the disk, so this is not hugely influenced by the luminosity of the star. And then we have the CO2 snow line, which is roughly just estimated from the temperature structure of the disk. And you can see that that's obviously fixed in this model because the luminosity is fixed, and this is how it's like correlated with the temperature. And the growth tracks here are color-coded by time. So you can see for the 1 solar mass star, we have like a very wide range of times at which these giant planets actually are accumulating the bulk of their masses. And then as we increase in stellar mass, we are making them faster and faster, basically. And then if we include the pre-main sequence evolution, we can see that this drastically changes both the locations at which giant planets can form successfully and the times at which they do so. So this is really interesting because if, for example, for the 2.4 solar mass star, you can see that these giant planets are accumulating the bulk of their mass much further out than, say, the 1 solar mass star. So there should be some sort of compositional difference that we can actually observe as like a sort of test bed for our model. So how is this actually happening? So if we have a fixed luminosity case, or for like our 1 solar mass star, which is staying, you know, fairly constant in stellar luminosity, we have like a very compressed disk. So you can see on the left-hand side, this is for like a low luminosity or like a stable luminosity zone, where we have the scale height of the gas, and then we have the scale height of the pebbles also correlated with that. However, if we're increasing the luminosity of the host star, which increases the temperature of the disk, this directly scales the scale height of the gas and pebbles, and that like kind of stretches everything out, and then that makes it harder for things like planet formation and mainly streaming instability to actually be able to condense downwards, and like basically directly affects the pebble-driven core accretion rate, so like the pebble accretion efficiency of these planets. So then it can take longer for them to form in a high luminosity environment. However, as we were hearing from Diego earlier today, we think that giant planets are forming on the timescale of 1.1 to 2 megayears. So that kind of implies that if we have a massive star that has a giant planet, they have to be forming like really early, because it becomes even more challenging in this high luminosity state. So we can also see this when we do some population synthesis modeling. So this is a very famous figure from Reffer et al. 2015. We have stellar mass on the x-axis. We have the giant planet occurrence rate on the y-axis. And you can see this rise, peak, and fall of the giant planet occurrence rate as a function of stellar mass. When we use this fixed luminosity case, and try and model it for the same 3 stellar masses that I've like marked on here, we do not get the same rise, peak, and fall. So clearly there is something else that we have to consider, ergo this pre-main sequence evolution. So I then combined, basically redid the model, recombined this with this pre-human sequence stellar luminosity evolution, and then also the stellar mass dependent accretion rates. So basically looking observationally at these three stellar masses and looking at the kind of spread of accretion rates that we get and then sampling from the model. So now you can see that we have radius on the x-axis and we have planet mass on the y-axis, and the color is for different planet masses. So you can see that for the red giant planets, we get far more occurring around the 1.7 solar mass star, which is great. So this actually works. We also get some interesting results from this, which is that the mean final mass and the mean final location of these giant planets increases with increasing stellar mass. So again, this is sort of implying a different compositional trend depending on stellar mass. Which we can then look at. So basically, I did this for every star in the Wolthoff sample, which is like an updated RV survey, which combined a bunch of them, looking at various intermediate, 1 to 4.5 solar mass stars, and looking for various giant planets. And we can basically then bin it based on stellar mass here. So these are for two slightly different models. But on the bottom half, you can see that this is the location at which these giant planets are accreting the bulk of their mass, so the runaway gas accretion phase. And then on the top, it's the time at which they are accreting the bulk of their mass. And you can see that we get this very nice correlation where around more massive stars, giant planets are gathering their material both further out from the host star and also faster. So they have to, if they are going to make these giant planets, they have to do so quickly. And this is great because this corresponds to some observational findings that we find from Madhudson and Wellbanks, which is giant planets around more massive stars tend to be oxygen poor but metal rich, and this is to do with like where they're accumulating the bulk of their material. I also had an MPhil student over the summer who was great, and she was looking at basically how this corresponds to the actual giant planets that they found in the Wolthoff sample. So of, I think it's 482 stars, they had 37 giant planets. And you can see here that they have stellar mass on the x-axis, and then we have the actual orbital radius of these giant planets, and then it's the density contour is basically my model because it's like a smooth disk, so it produces a bunch of giant planets depending on the initial conditions. But you can see that we get, you know, a sort of nice correlation with our model and like where we actually find those giant planets in the Wolthoff sample, which is super cool. And then she was also working on some data cuts in the Exoplanet archive, and she is looking for a PhD, so talk to me if you're interested. She was a very great student to work with. And yeah, finally you get a bonus slide of like what my current work is on, because I'm working on the dispersal of protoplanetary disks via external photoevaporation, basically trying to go from this giant planet forming phase of protoplanetary disks and evolve them all the way through to the debris disk stage. So at the moment I'm doing this via external photoevaporation, and you can see that there's like a photoevaporative wind that will like eat away at the outer edge of the disk and create this abundant widespread belt of planetesimals, which is very cool. My stellar luminosity paper is out. You can check it out here. It's been out for, I think, a couple of weeks now. So yeah, I would really appreciate it if you have any questions. And yeah, and I'll leave you with my conclusions, and I'm happy to take questions now.
Thanks so much, Heather, for this great talk. Questions? Okay, well. It's okay.
Okay. Thanks a lot for the presentation. So when you were modeling your formation around 1.7, 2.4 stellar masses, do you assume the same composition, metallicity?
No, we were using the spread of data, right? So this is what the actual data look like, right? So we have metallicity on the x-axis, we have stellar mass on the y-axis, and then we were basically doing the model for every one of the stars in these samples. For the example that I showed in my slide, that was just using a solar abundance, but it was just as a test bed for like to make sure it worked and have the nice plot.
When you were comparing the occurrence rate with the observations.
Oh, yeah, so they have this spread of metallicity with them, yeah.
Yes, thank you for the interesting talk. You mentioned that the formation of giant planets or of planets in general, is faster around more massive stars. Now, the lifetime of the disk is also shorter.
Yes.
Now, is the ratio between formation time of planets to disk lifetime the same, or is it different for different stars of different mass?
So when I was looking at this, I was basically looking at the different accretion rates, which is also like basically a function of the disk lifetime, right? So in essence, the disks have a higher accretion rate around these more massive stars, and so the disk lifetime is shorter because it just eats the material faster, right? So it's sort of a competitive process. However, we are forming all of the, we're like basically forming them through streaming instability and planting them at like a range of radii, but they're all formed, the seeds of the embryos are all planted at 0.1 megayears. So if ideally you have like a very high accretion rate and you have like an abundant amount of material, you could form them very easily around 5 solar masses, but it becomes then a competition between how fast the disk lives for. And yeah, the other thing as well is that our models are only using X-ray photoevaporation, right? So for the first few megayears when this process is going on, that's okay for the majority of stars that we're using, up to about 2.5 solar masses. However, beyond that, we're going to be like fundamentally in the FUV zone, which would also eat away the disk more rapidly as well. So yeah, it's very much a competition between the two stages.
Okay, well, let's thank Theda again.
Thank you.
And actually all the speakers in the morning so far. And we're now breaking for the coffee break, and we will reconvene at 11:30. Okay, we are ready to start. Hopefully most people will take a seat. Okay, perhaps we can start. So great pleasure to introduce the next speaker today, Jason Brown from UCL. He will tell about Bayesian constraints on planet formation parameters with simulation-based inference.
Brilliant. Thanks, Giovanna. Yeah, so as she said, my name is Jason. I'm a PhD student at UCL working with Mikhail Karma. And I'm going to be talking about my work in trying to develop a framework to constrain planet formation parameters with a technique known as simulation-based inference. Now, we've had a lot of talks at this conference so far about people working at the forefront of planet formation modeling. And these three figures on my title slide kind of highlight the aspects I try to bring together in my work. So we have extensive surveys of protoplanetary disks and exoplanets, and these help inform our theories of planet formation. And at the same time, with the advent of machine learning, we have this tool that is able to map these complicated, high-dimensional, nonlinear relationships. And maybe this provides an opportunity for us to explore the parameter space of planet formation. So the first question I want to ask is, why are planet formation parameters so hard to constrain in the first place? Well, one reason is that there are just so many of them. Planet formation is a very complicated process that has many moving parts, and each one of these moving parts will have some number of free parameters attributed to them. And what we mean by free parameters is either there's a theoretical uncertainty attached to this parameter, or simply that you cannot directly constrain this parameter from an observation alone. So one consequence of this is that with so many free parameters, you naturally get many degeneracies with your model, in a sense that many different combinations of these parameters may lead to the same observational outcome. And all these parameters that lead to this outcome, in some sense, are all equally correct, but what I want to argue in this talk is that maybe one way to characterize this degeneracy is in a probabilistic way, in the sense that even though they are all correct, maybe some of them are more likely to produce your outcome than other ones. So when working with probabilities, one thing that we often would be useful is to have large data sets to work with. So for this work, we use a population synthesis approach, which we spoke about a little bit today already. It's a low-fidelity simulation that easily produces large numbers of simulations very quickly. So the population synthesis model that we use in this work is known as SpongePop. It's something that's been developed at UCL and beyond for a couple of years now. My friend and colleague Anna will be talking about this in about 30 minutes or so, focusing mostly on the physical aspects of the disk model, the disk chemistry, and planet formation. In this talk, I mostly want to talk about using the data analysis to do some sort of statistical inference. Before I get into that, I thought I'd highlight the standard approach of population synthesis and how we use this to try and constrain planet formation parameters. So it normally looks something like this. You have a theoretical model that you want to test. You build a simulation around this. You sample some, you sample some initial conditions, and then you put this into your simulation, generate a synthetic observation, and do a statistical comparison, and you repeat this process until your statistical comparison looks close enough to the observation that you have. One of the key challenges in this, though, is this bottom section here of the statistical comparison. Often what this involves is reducing your synthetic population down into some summary statistics captured by one or two numbers. And a lot of great work has been done from this. But one of the features of this along the way is that you lose some information in reducing down this dimensionality. And what this means is that a few aspects become quite difficult to achieve, particularly meaningful uncertainty quantification. And if you change any part of your model, then you'll have to repeat this process again. And when you compare these models, it's also difficult to do that in a useful way. So I want to introduce an alternative method that I think may work through a Bayesian framework. Statistical inference is probably something you've heard at some point throughout your career. To me, what statistical inference means is this sentence here, using data to learn about underlying parameters of a probabilistic process. As a physicist, we can break this down in terms of your process being the physical model that you want to test. And this model has some number of free parameters attributed to it. And you want to try and constrain these parameters with your observational data, that's X. And these things are all joined together in Bayes' theorem here, which puts a probability distribution over your parameters. So this first term in this bottom equation is what is called a posterior distribution. This is a probability distribution over your parameters given the data that you see, and this is proportional to the likelihood, the probability of getting your data given the parameter, and this, this prior distribution here that you as a expert in the field will set for yourself. It is what you think the parameters are before you even see your, before you even see any data. So in the formation, planet formation context, it might look something like this. Your formation model is the thing that you're trying to test. You have maybe some sort of core accretion, disk migration or disk evolution. Each one of these components will have some number of free parameters attributed to them. The top line here is the likelihood. You take your parameters and you put it into your simulator and you get some sort of outcome. This outcome is distributed according to the likelihood. And then, but what we actually want to do in this work is the reverse direction, where we have a bunch of planet formation outcomes, which are your observations, and you want to infer what formation parameters led to those outcomes. And that is the posterior distribution. And these two things are linked by Bayes' theorem in the middle. Now, one of the challenges is that often in the physical sciences in general, neither the likelihood or the posterior distribution can be directly evaluated. And what I mean by this is that you can't write down an equation for it. If I give you a set of formation parameters, you cannot immediately tell me what the outcome will be. So instead, what we want to do is try and fill this space of theta and x, your parameters and observables, with your simulations. And we do this with our population synthesis because we can generate large numbers of simulations very quickly. And if you do that, maybe it looks like this purely illustrative example on the right. On the y-axis, you have your observables. On the x-axis, you have your parameters. And it might look like some complicated shape like this. And if you try to write out an equation for this, you'd spend a long time. So if you want to fill in this space, the first thing you have to do is sample from your prior distribution. If we do a toy example with SpongeBob, it might look something like this. You sample from your priors, maybe the disk radius, disk mass, temperature, and some MHD wind properties. I won't go too much into what the wind properties are, but you can roughly think of K as a mass loss term caused by the wind, and FW as an angular momentum term caused by the wind. And then you sample your priors, and it looks maybe something like this in the corner plot, where each blue dot corresponds to a sample. So what you do is you take your samples, you put this into your simulator, and you end up with a bunch of green points, which are observables. So this forms a space of your observables. In our case, is the orbital period, the planet mass, and the atmospheric C/O ratio. And the aim is to find a mapping between these two, but from a mapping from the blue points to the green points. But this is clearly a very difficult task. And this is where I want to introduce a concept called neural density estimation. This is a relatively recent machine learning framework that's been developed. And the idea is that you can take some known, some easy to sample from distribution and find a way to mold it into your target distribution. So without going into too much detail, you can think of it like this. It's a machine learning technique. Traditional density estimation methods would scale poorly to higher dimensions, so something like histogram binning or kernel density estimation. So we try to do this instead. You learn a set of transformations. These transformations have a bunch of transformation parameters attributed to them. And you try to optimize these parameters so that your transformed distribution is as close as possible to your target distribution through some sort of loss function. So if we do another test example, here we're going to use HG29458b, which has been talked about a bit at this conference already. It's a well-known hot Jupiter with a low C/O ratio, atmospheric C/O ratio. And if you imagine now this y-axis of our observables is a one-dimensional projection of our three dimensions of our observables, and this x-axis of your parameters is a one-dimensional projection of your 5 formation parameters, and pretend that your likelihood space looks something like this red stuff. The way that this would work is you might have noticed that the green plots have this purple line on them. These represent the HG2094588b observables. You would draw a line across it on, from your observable space, look at where this intersects with your simulated data. That would be these blue circles here. Project these down into your formation parameters, and then the probability density between these blue lines represents your posterior density that you learn through your neural density estimation. So that might look like something like this. You project it down, and you end up with this different blue posterior distribution here. Now, I don't want to go too much into what this posterior distribution is telling us. That would be a separate talk. But the key point is that this looks very different to your prior distribution, and it's telling you that you are learning something from this density estimation and doing inference on your observables. Now, one key point I want to get across as scientists is that we're interested in what is actually happening, not necessarily just the parameters themselves, but how does this influence the planet formation outcome. And this is a process known as posterior predictive checking. You can take your posterior distribution, or you take your observation first, and you do inference to get your posterior distribution. Then you take samples from your posterior distribution and put it back into your simulator and see how your simulator is actually dealing with this to get your planet. So I think this is a very powerful method. You can then look at diagrams like this, where each track here comes from a simulation where the input parameters are sampled from a posterior distribution. And then you can analyze this diagram. This is a mass period plane at the left, a mass C/O ratio plane on the right, and see what is going on and whether or not your results converge to your observation, and they do. And then by looking at these tracks separately, you can look at different formation scenarios for how HD 209458b may have formed. So that brings me to my conclusions. A lot of people in the room work on this aspect. You have surveys of clouds, disks, planets, and stars, made a lot of great formation models and parameters from this. And what we do in this work is we take these formation parameter models that have been made, generate populations with population synthesis that form the basis of our neural density estimation. We perform simulation-based inference from this and take our posterior distributions and put them back into our simulator to do scientific analysis and study the formation pathways. And I think if you do this enough times on a large enough sample, constrain enough planets in this way, maybe we can begin to understand why we even see these surveys in the first place on a population level. So I think that's all my time. Thank you very much for your attention, and I'll take any questions.
Thanks so much, Jason, for the great talk. Questions? Yes.
Thank you. For the plot that you showed in the previous slide, could you go back too much?
Can I go back?
I'm just wondering, in those all tracks, where does the observation lie?
Where does the, oh, sorry, I should have said, the observation is the orange circle.
I see.
Yeah, sorry, that's my mistake. I didn't include that. So the idea is that you take your posterior distribution and then you take the samples put into your simulator, and these tracks, although they're all different, they converge on the same result.
Right, but then this does not really help us understand the formation point, does it?
Understand what, sorry?
On the formation starting point, I guess, of the track.
The starting point?
Yeah, so the tracks are starting from the lower axis, is that right?
Yes. Yeah, you can think of it that way. So the orbital periods or the semi-major axis, you start at a given point in there, and then, yeah.
And since all of them are converging in that blue region, I cannot really track back to one particular track. Is
no,
that a fair
so
point
that
to
is,
say?
yeah, that is fair to say. That
Okay.
is one of the main points, is that these models have so many free parameters that they become degenerate.
Gotcha.
And that multiple tracks lead to the same outcome. But how do we capture that degeneracy accurately?
Gotcha, thanks.
Other question, Jason?
Yeah, really cool stuff. So my question is, how does it compare to the baseline? So I guess usually you would then use MC or nested sampling or something like this. So how does it compare, and when does it amortize? So does it, like, does training the model take as much time as the usual one? Is it amortizing for the first example, or do you need a couple of examples?
Yeah, that's a good question. So with something like, if you're going to use MC, you need to know the likelihood function. Same thing with nested sampling. I think the point here is that for models as complicated as this, the likelihood function is not something you could write down straight away. So you simulate it and then estimate it with this neural density estimation. As for amortization, one of the things is that these simulations that we train it on all have a host star, which is HD 209458. If you train it on a different star, you may have to, you will have to resimulate different data. But for an observation across this star, it is immediately amortized. But I think one thing that you could do actually is expand your training data set to cover a range of stellar parameters and then simulate a range of planets for each one of those stellar parameters, and then you would be amortized across all stars in that range. Yeah.
Okay, let's thank Jason again.
Thanks.
So our next speaker will be Nidhi Rohit Bangera, and she's from the Institute for Weltraumforschung, and she will tell us about unpacking disequilibrium chemistry in exoplanet atmospheres from CO constraints to solver photochemistry.
Thank you. Hi, I'm Nidhi Bangera. I'm a final year PhD student at the Space Research Institute of Austria. And yes, today I'll be talking about our use of 1D disequilibrium chemistry models to interpret the high-resolution spectroscopy data of an exo-Saturn WASP-69b. So, in the atmospheres of gaseous exoplanets, which are the targets of my interest, two key processes are expected to drive the chemistry out of equilibrium. So this would be mixing of material throughout the atmosphere, and since I do 1D disequilibrium chemistry, I'm interested in mixing in the vertical direction, and then photochemistry. So vertical mixing, or eddy diffusion, is the process by which material formed in the deeper layer of the atmosphere is mixed vertically faster than the local destruction reaction. So you end up with concentrations of species that are quenched to the levels produced in the deep atmospheric layers. Photochemistry is spurred on by the stellar XUV or cosmic rays and ends up with a diversity of chemistry in the upper layers of the atmosphere. Now, with observations with high resolution as well as James Webb, we've identified tracers of these processes in such atmospheres. For example, SO2 is a photochemically produced molecule in hydrogen-dominated atmospheres, and it was first observed in WASP-39b, following which there has been multiple observations in a few other gaseous exoplanets, I must add. For this talk, our target of interest is WASP-69b. So this is a Saturn-like exoplanet that has a sub-Jovian mass, a slightly larger than Jovian radius, making it quite puffy as a planet. It orbits a K-type star and has an equilibrium temperature of about 950 Kelvin. The interesting thing about this planet is that in the high-resolution spectroscopy data, the authors Gilly et al. Identified the presence of 5 key molecules, so water, methane, ammonia, acetylene, as well as carbon monoxide. So that makes it one of the most diverse chemistry that has been observed in gaseous exoplanets. Now, on the basis of the high methane, the strong methane signal, and on equilibrium chemistry modeling, these authors concluded that this atmosphere must be carbon-rich or have a CTO ratio of 2. However, if you look at the pressure temperature profile of this planet, so that's the orange curve here, we see that it crosses the COCH4 interconversion temperature in the deeper layers of the atmosphere and then passes along the N2NH3. So as I mentioned, quenching or vertical mixing, if you have a very strong vertical diffusion efficiency in this atmosphere, you can end up with quenched concentrations of CH4 and NH3 that are orders of magnitude away from equilibrium predictions. So this is an interesting target planet to study the effects of disequilibrium chemistry on, which is what we do. So I went on to use the atmospheric modeling code Argo. This is a 1D code. It solves for the continuity equation you see up there. So for each chemical species, the concentration is given by the production and loss reactions, as well as flux through the atmospheric layers. This uses as a chemical input a network called STAND, which includes both ion and neutral reactions for about 4,000 reactions, including about 300 chemical species. So we used this code to have a parameter space exploration for WASP-69b with 3 parameters. Firstly, KZZ, which is the vertical diffusion efficiency, was investigated. This is a poorly constrained parameter, not just on exoplanets, but also on solar system planets, which is why we chose to explore different strengths as well as shapes of the profile. So that's the 3 profiles you see up there that we explored. Secondly, the carbon to oxygen ratio, which was the parameter we were hoping to constrain. And then finally, the pressure temperature profile motivated by differences in pressure and temperature along the day side to the night side of the planet. So what is the effect of disequilibrium chemistry in this atmosphere? So we're looking at a sample atmosphere for WASP-69b here, and we have 3 columns showing you how the different molecules are affected. We see the concentrations in the x-axis and the pressure in the atmosphere in the y-axis, and the different line styles tell you whether the model was assuming chemical equilibrium, diffusion, or diffusion and photochemistry. In the first column, you see CO and N2, which show very little differences between chemical equilibrium assumption and disequilibrium. So these are relatively stable in this atmosphere. In the second column, you see CH4 and NH3, which are now quenched by vertical diffusion, 2 orders of magnitude higher than their equilibrium predictions. And then in the final column, you have C2H2 and HCN, which is further increased by photochemistry in these atmospheres. In the gray bar, you see the pressure regions that would have been probed by the high-resolution spectra, and 4 out of 6 of these molecules were inferred. So CO, CH4, NH3, as well as C2H2. 3 out of 4 of these are highly impacted by disequilibrium processes. So it is relevant to do disequilibrium chemistry analysis for this exoplanet. Now, we had 14 models with our parameter space, and we produced synthetic spectra for these models, which were then cross-correlated to the original high-res data. And those of you familiar with cross-correlations to high-res data can already probably see a problem. 8 out of 14 of these models show fits to the data. So this is not very good. It doesn't really point us conclusively in any direction. Do these 8 models show trends? So over here, we've got highlighted the 8 models that show fit to the data. And as you can see, we have both oxygen-rich as well as carbon-rich models that fit the data. We have differences in the temperature profile as well as in the KZZ values. So it doesn't really constrain. It shows you essentially the degeneracy of the different parameters, the free parameters that we have probed in recreating the spectra. However, what we can conclude here is that this atmosphere need not be carbon-rich, that certain parameter spaces within the oxygen-rich domain also would recreate the spectra. So this is our conclusion on the basis of this work. So far, I've told you that the KZZ parameter, so the eddy diffusion efficiency, is poorly constrained in these atmospheres. Are there any species that we can use as tracers? Well, essentially, because we don't fully know what the shape of this parameter is, it would be useful to have pressure-dependent species that could help us trace this. So if we could use it to trace the local KZZ, and one of the species we identify would be a photochemically produced species, such as C2H2. What happens is that you have a competition between the photochemistry, the photochemical production, and then the quenching of the reactions due to the eddy diffusion. So if you have a very strong vertical mixing, you end up producing less local photochemical species, which is what you see up here. So up there, the stronger you're mixing, the lower the C2H2 that you would end up producing. However, this is also dependent on the presence of the parent molecule, which is why I've shown CH4 here. So in this carbon-rich atmosphere, CH4 is not very strongly dependent on your KZZ, and therefore, what you are probing now is just the time scale of your photochemical reactions versus the time scale of the quenching itself. In an oxygen-rich atmosphere, that is no longer the case. So your concentration of the parent molecule itself is dependent on the deep atmosphere KZZ. So there is an additional degeneracy here. You can no longer use C2H2 to probe your local KZZ here. However, you may be able to use an oxygen-bearing photochemical species such as SO2. So you can use photochemical species to trace KZZ in the upper atmospheric layers, but the choice of this species is dependent on the ubiquitousness of the parent chemistry, parent molecule. Okay, finally, I would like to, there we go, talk about current work that I'm involved in, and this has to do with sulfur chemistry in these atmospheres. Sulfur is interesting for a few reasons, as has already been mentioned before. So the primary sulfur reservoir, H2S, remains in the gas phase in these atmospheres in temperature regions where the reservoirs for example, magnesium, silicon, iron condense out into clouds. So if you're able to trace H2S, you would be able to trace potentially the primordial sulfur elemental abundance in this. However, typically what you observe is not H2S, but SO2. And this is not your main sulfur reservoir. But SO2 does give you insights on photochemistry, so it does give you insights on a different chemical process in this atmosphere. CS2 has also been observed in a few exoplanets and has been foretold to be a photochemical species, but it is not evident through the modeling, through the chemical modeling yet. What we observed is that there is a lack of ion chemistry research for sulfur, and this is the gap that we were hoping to fill. So for this, I had to put together an ion chemistry network, which started with collecting kinetic reaction rates through literature sources, thermochemical data for the ions, which are not present in literature. So for this, my colleague Elena Lecoq-Molinos conducted DFT calculations of the Gibbs free energies for the ions. And then as a baseline, we also had these for the parent neutral species. And for the neutral species, we have now a comparison with literature values that are computed through lab experiments and so on. And we see we have about a 15 kilojoule per mole difference, but we do show the trend quite well. And we have investigated the effect of this 15 kilojoule per mole difference in our paper that is in prep. And then finally, the last data that had to be collected as we were interested in photochemistry is the photoionization cross-sections, which we also find through literature databases. Now, with all of this, there are some preliminary results that I can share. What you're looking here is the atmosphere of WASP-69b again, some of the more abundant chemical species. In bold is the chemistry without the inclusion of sulfur ions. In dashed line is the inclusion of sulfur ions. You see only one species is affected by the inclusion of sulfur ions, which is quite relieving, actually. It would be a bit worrying if there were more and at higher abundances. In this atmosphere, the sulfur ions are present at levels of 10 to the minus 30 in terms of concentration or so for the most part. And then in the very upper atmosphere, you have photoionization producing it or charge exchange reactions producing it to the levels of 10 to the minus 10, 10 to the minus 12. So this is the concentration part of the atmosphere that you would expect it to impact your neutral chemistry as well. And we see that it ends up impacting your CS chemistry in this case. The takeaway here is that the inclusion of ions is relevant for the most upper layers of the atmosphere. So if you're interested in high resolution or very upper atmospheric layers, it would be relevant to also include ion chemistry in your modeling. With that, I come to my takeaways. Essentially, it is relevant to include the impact of vertical diffusion and photochemistry, so disequilibrium modeling in your analysis of spectra. And we find that our cross-correlation of disequilibrium models to the high-res data changes the conclusion that this atmosphere has to be carbon-rich. It could also very well be oxygen-rich. We show that photochemical species would help you trace the local KZZ in the upper atmosphere, and finally that the inclusion of ion chemistry does impact also your neutrals in the very upper atmosphere. Thank you for your attention.
Thank you so much, Anita, for this very compelling talk. Questions? Yes.
Thank you for this very interesting talk. I'm now start to worry a little bit because if I want to model the origin of planets based on the atmospheric abundance, and then you say depending what model you use, it will go from carbon rich to carbon poor. Can I trust the data?
So that was a point I had with yours and Diego's talk as well, which is if we're trying to trace the C2O ratio, I assume we want the bulk C2O ratio, and what we get is firstly the atmospheric C2O ratio. So we're assuming firstly that we can go from one to the other, and then we also had mentions that the C2O ratio would change with cloud condensation and so on, and it changes based on your assumption for the interior temperature of the planet. So there is a lot of complexity that would help you determine using just your observables, just CO or CH4, what the actual C2O ratio or such should be. Can you trust your observations? Sure, but can you go from the observations to predictions for planet formation? A little bit more complex there, yeah.
Thank you.
Other questions? Yeah. There's a question there. Sorry, did you raise your hand? Okay, maybe not. So I have a question, actually. Very interesting. Do you include in your model some condensation?
Not in these models. So we have a separate model that takes into account cloud condensation. And what we end up doing is we deplete the elemental abundances to reflect that cloud condensation. But our model itself just does gas phase chemistry.
Okay, understood. Okay, if there are no other questions, let's thank Nidhi again. And our next speaker is Anna Thomas from UCL. And she will tell us about population synthesis to investigate the effect of volatile to refractory sulfur conversion on the production of hot and cold gas giants. I would imagine so.
Okay, lovely. Hello, my name's Anna. I'm a PhD student at UCL working with Mikhail Karma. And I was hoping to talk to you today a little bit about one of our first science cases with our planet population synthesis model, SpongePop, that was briefly mentioned by my friend and colleague Jason just a few talks ago. But before I start, I just want to say thank you to the organisers for letting me speak, and also thank you to our collaborators here at Tartu, but also at the University of Exeter, the University of Cambridge, and also the Mullard Space Science Laboratory. I hope I'm preaching to the choir here when I say that we think that giant planets are very important when it comes to studying atmospheric chemistry. They are great targets for direct imaging. The planet cut off one of the words, sorry about that. And atmospheric composition studies rely almost entirely on giant planets, particularly close-in giant planets, because it means that we can see their transmission spectra. Giant planets also cause direct observational feedback on their host disks, which means in some cases we can even see planet formation happening as it occurs, which helps inform planet formation models. But why sulfur is a little bit more of a difficult question. So sulfur in postplanetary disks is still a little bit misunderstood. And so when we trace sulfur back to the diffuse interstellar medium, we see that it has a far higher abundance in comparison to hydrogen than it does by the time that it's gone through the molecular cloud, the star formation process, and then to a protoplanetary disk. And when it starts in the diffuse interstellar medium, we also notice that it's basically 99% in the gas phase. But we assume that it's all in refractory by the time that we reach the protoplanetary disk. But now, in the age of ALMA, we know this isn't necessarily true. So, for example, this is HD 100546, and we see that even 5 million years assumed into its evolution, it still has gas phase sulfur in multiple different carriers that is surviving even far out into the disk. So why giant planets with sulfur? My talk actually follows on quite nicely from the last talk, because obviously in the age of JWST, and obviously with the launch of Ariel in a few years, we're going to be seeing a lot of more giant planets with their bulk compositions giving information about the sulfur and what carriers that they are carried by. So here are some examples on the screen, but also our very own Jupiter is an example of a planet with incredibly enhanced sulfur abundance in its upper atmosphere, roughly 3 times the solar level. So how do we intend to test this? SpongePop was, again, briefly introduced by my colleague earlier, but I want to talk a little bit about it before I got into how we decided to test this. So SpongePop is a population synthesis model that focuses on the chemical links between planets and their formation environments. So sponge obviously being the 6 key elements needed for life, so sulfur, phosphorus, oxygen, nitrogen, carbon, hydrogen. You may have heard it referred to as CNOPS, but sponge is a lot more fun to say. And then POP, because it's a planet population synthesis model, which you've heard a lot about today. But if you're still unclear about what a planet population synthesis model is, it's a model that synthesizes populations of planets. It's exactly what it says on the tin. So this is supposed to be a low fidelity but high speed model, and we have basically a bunch of interchanging working parts, like multiple gears in the machine that you can sort of chop and change to what you need. So I'm going to mainly talk about the disk structure and evolution module, as well as a little bit about the disk chemistry and the planet formation and migration, which has been my job since I started at UCL. So we have 3 disk models in our disk module in SpongePop that are all motivated by different dynamical processes and heating mechanisms. So we have a standard pure viscous case, which is just dominated by viscous heating, but we also have a viscous irradiated case where stellar irradiation instant on the disk is also motivating heating. And then we also have an MHD wind case, because obviously that's the new up and coming thing, where mass loss and angular momentum loss is motivated by an internal wind. But for the sake of this talk, I'm just going to focus on one of the disk models, which is the viscous irradiated case. So this is a surface density profile showing our initial surface density distributions for iron grains and iron pebbles, as well as our H2S surface density as well. And then we let our disk evolve. So this is showing multiple time steps of disk evolution, including pebble drift. And you see that there's a region around 1 AU where the disk conditions are favorable for FES formation. So between like 0.6 and 3 AU in this case, the conditions are just right for FES to be formed on our grains. This is because obviously it's not too hot for the sulfur to sublimate back into the gas phase, and also not too cold that the reaction rates are too slow to support efficient FES formation. We've chosen these two molecules. We've basically just assumed that all of our volatile sulfur is in one carrier and all of our refractories in the other. But this just covers our small grains. So how do we deal with planetesimals? Because SpongePop deals with both planetesimal and pebble accretion simultaneously. We deal with a surface density of planetesimals that basically starts from the inner edge of the disk to wherever the outer edge of the disk is at T0 of the disk, and then we split this into 4 zones. So when FES sublimates at 655 Kelvin roughly, we say that our planetesimals are entirely silicate-based and have no sulfur in them. But in that zone where FES formation is really efficient, we say that our planetesimals have a fraction of their mass allocated to sulfur. Outside of that zone, however, and to the H2S ice line, again, we say that we have really sulfur-poor planetesimals, and then beyond the H2S ice line at 54 Kelvin, we say that, again, our planetesimals have sulfur in the form of H2S ice. So again, going back to our dust grain surface densities, it's basically split into those 4 zones of no sulfur, sulfur, no sulfur, sulfur, in the solid phase at least. But this doesn't describe how our planetesimals are incorporated into our envelopes once they are accreted. So we have this free parameter called P ratio, which describes what fraction of the planetesimal is ablated into our gas giant atmosphere during the runaway gas accretion phase. So we have 3 values of this. P ratio equals 0, where absolutely none of our planetesimals contribute to our envelope, and they only contribute to the core, sulfur and all. Then we have our middle case of P ratio equals 0.5, where half of the mass and any subsequent sulfur they may be carrying is deposited into the envelope and core respectively. And then P ratio equals 1, where all mass and subsequent sulfur is deposited into the envelope. And obviously this is supposed to mimic late-stage planetesimal infall, which is supposed to be one of the leading theories behind Jupiter having its supersolar sulfur abundance. Say that 6 times fast. I just wanted to point out this set of evolution tracks in particular, because obviously this conference is all about linking planet formation environments and the stars that they're around to their final planet systems that they're creating. So in the case of these 3 evolution tracks, you have your mass in Earth masses on the y-axis, and then your planet position on the x-axis in terms of astronomical units. And then the color bar is representative of what mass of the core and envelope are sulfur, in comparison to their relative mass, obviously. And the input parameters for all of these disks and their planet starting conditions are identical. The only things here that have changed have been the disk model that they're being propagated in. So you can see that there's already an immediate difference between not only the final planets in terms of their physical properties, like their mass and location, but also in terms of bulk composition, bulk mass fraction of sulfur that they're holding. So, for example, I'm not sure how easy it is to see, but the dashed line representing the planet that grew up in the viscous irradiated disk has a slightly higher sulfur mass fraction in its envelope than its pure viscous counterpart, because it's done at least some of its runaway gas accretion in an area where H2S gas is still present and abundant. And then you have this very sad-looking circle representing the planet that grew up in the MHD wind-driven disk that has negligible or no sulfur because it's grown up, but it hasn't even reached a mass where its local disk conditions are good for exceeding its pebble isolation mass, So it hasn't even started envelope contraction or runaway gas accretion. So when we start to generate populations of this planet, again, I'm just going to do this for one of our disk models, our viscous irradiated, what do they start to look like, and can we see trends in the final atmospheric bulk abundances? So because all of these planets are formed in single planet disks and around sun-like stars, I've normalized this to Jupiter's sulfur abundance. because hopefully maybe we can learn a little bit about where Jupiter got the majority of its sulfur from. So in this case, this is our P ratio equals 0 case. So we have planetesimal accretion turned on, but none of these planetesimals are being ablated into their gas giant envelopes. And so they're only getting sulfur in their envelopes through the accretion of H2S gas. And you can see a trend between the outer planets, which are being formed in an area where H2S gas is still present, and compared to the darker crosses in the inner disk around 1AU, where they grew up in that area where refractory sulfur is more abundant in the pebbles, and so there's no gas phase sulfur for them to accrete. Our second case here is with our P ratio equals 0.5, so we have partial planetesimal ablation in our planets, and so you're starting to see in the outer disk some of the sulfur abundances of the gas giants around Jupiter's mass, but further out, starting to creep up towards Jupiter's sulfur abundance, because they are managing to accrete not only H2S gas from the outer disk, but they're also being supplemented by late-stage planetesimal infall of planetesimals that are holding H2S in the ice phase as well. You're seeing that trend of sulfur depletion in the inner disk, but it's to a lesser degree because these planets have either migrated from an area where H2S is still in the gas phase in a relative abundance, or because they're accreting sulfur-rich planetesimals in the area where FES formation is favored. And then we have our extreme case here. Ooh, did I zoom in? I did not mean to do that. Then we have our extreme case of P ratio equals 1. And for this case, we've kept our planetesimal accretion on, and we have total planetesimal ablation in our gas giant envelopes. But we have turned off the gas accretion for H2S here. So the planets are still accreting gas. Obviously, we're still seeing gas giants. But we've assumed that all of the sulfur is in the refractory for this particular set of models. And the trend seems to break down a little bit. So you're still seeing planets that are reaching Jupiter's sulfur abundance in their atmospheres, but ironically, even around Jupiter's location, you're seeing a lot of these grey markers, and these are representing planets that have accreted basically little to no sulfur because they've grown up primarily in a place where there's no sulfur in the refractory. So what can these populations, preliminary populations, tell us about gas giant formation histories? I'm sure it's no surprise to anyone that enhanced sulfur abundances in gas giants cannot be accounted for by pure gas accretion alone, when not considering core envelope mixing or photochemistry. Hot gas giant sulfur abundances can indicate whether they formed cold. So you might be able to tell from migration history whether a planet formed in an area where refractory sulfur was particularly depleted, or whether there was an abundance of gas phase sulfur. And finally, if we're talking about Jupiter in particular, Jupiter and other sulfur-rich cold gas giants may have been most likely supplemented by planetesimals that were sulfur-rich in the form of H2S ices. And thank you for your time.
Thanks so much, Hannah, for the great talk. Questions? Yes.
So in your model, the main solid carrier in the outer disk for sulfur is H2S, right?
Yes.
But from the solar system, we have that in the most primitive meteorites, CI, sulfur is all in the rock phase, and recent the Rosetta and the Hayabusa and the Osiris-Rex missions point to CI meteorites being also a template for the cometary dust, and therefore sulfur also in comets is mainly in the refractory phase rather than H2S, which would have a significant impact on the initial distribution of the sulfur.
Yes, I didn't want this to be a direct sort of solar system one-to-one. I just wanted to look at particularly an example of a sulfur enhancement in a gas giant planet. But yes, I agree with that. That makes a lot of sense.
Bertrand?
Yeah, so actually I had a similar question, so I'm going to ask this something different. So in your model, it seems you were very successful of forming giant planets outside of 20, 30 astronomical units. I mean, I guess these are of course driven by pebble accretion, but yet on the other hand, the cross tracks that you showed before, your planet migrated a lot. So I was wondering if what the viscosity is in your protoplanetary disk to set your migration velocity, essentially?
Right, yeah. So we sampled our alpha viscosity as a maximum of 10 to the minus 3. But aside from that, our average was pretty low, around 10 to the minus 4 instead. So you find that a lot of planets kind of stay in one area rather than migrating inwards. But these evolution tracks, these are for slightly higher alpha values, just because I wanted to demonstrate particularly the migration histories.
Thank you.
Okay, let's thank... sorry, there is a question there.
Thanks, Anna. This is really, really cool.
Oh, thank you.
So I was wondering, could we figure out whether a gas giant has been in an irradiated disk?
Externally irradiated, do you mean? I actually don't know what effect an externally irradiated disk would have on the sulfur chemistry in particular, so I can't comment on that.
I think that would be a really interesting
I think it would be too.
point to explore. Yeah. Let's chat.
We'll chat, okay.
Okay, let's thank Hannah again. So the next speaker will be Sebastian Payne from Queen Mary University London, and he will tell us about photoevaporated dust disk models and synthetic observations.
Hi, so I'm Sebastian Payne from Queen Mary, and yeah, I'll be talking about dust and externally photoevaporated winds. So just a brief summary to motivate all of this. So these externally photoevaporated disks sort of occur in regions where you have O and B stars radiating the gas, and this gas then drags out dust with it, creating sort of dust halo around these disks. And the goal of my PhD has been to sort of get constraints on the dust sizes and dust positions in this wind, and currently starting to work on getting synthetic observables from this. So a quick review of sort of external photoevaporation. So in an externally photoevaporated disk, you have this radiation which heats up the gas to the point where it sort of escapes from the disk. And this then drags out dust with it, sort of through aerodynamic drag. And this removes a lot of material from the disk, so sort of on orders of 1 to 10 million years, most of the mass and the size of the disk will be completely depleted. And the external part of the external photoevaporation is, instead of the sort of central star in the disk being responsible for this irradiation, it's the neighboring O and B stars in these stellar clusters that provide most of the radiation that does this heating. And you get these sort of telltale sort of teardrop ionization fronts, which make them sort of quite easy to spot that they're undergoing this external photoevaporation. So, as I said before, this happens mainly in stellar clusters where you have at least one or many O and B type stars. And since most sort of star formation and disk formation is thought to happen in these stellar clusters, it's quite important to see what the effect of this is on disks and their evolution. So, specifically looking at the dust, we see a lot of sort of observations where we can observe the disk, and then, I'm not sure how well you can see this, but sort of these long sort of tails of dust sort of blocking the light sort of further out from the disk, and this is dust that's been sort of dragged out from the disk by this external radiation. And yeah, so specifically this dust, the modeling of this dust is done by evolving these two equations where you've got gravity holding the dust in the disk, preventing it from escaping, and then aerodynamic drag as the gas is heated brings the dust out with it. And you get the sort of usual sort of relations of small dust being well coupled to the gas up to about a micron, and then the larger dust not really following the gas anymore. So in this case, even though the dust won't always follow the gas, some larger grains can be carried out still, but won't necessarily follow the gas streamlines and will stay closer to the midplane. And for the modeling, we can assume a very low density gas and dust, which allows us to basically ignore interactions between dust grains, so no collisions, no growth, no fragmentation, and also no back reaction on the dust from the gas, no back reaction on the gas from the dust, which allows us to sort of simplify the computations quite a lot. And we set up these disk models, sort of computing the radiation, hydrodynamics, and then placing the dust grains sort of around the disk, and then computing where all these dust grains end up. And we get a nice sort of map of all the dust sizes like this, where the two key takeaways are that as you sort of increase the polar angle, go above the disk surface, the size of the grains that can be sort of carried out by this radiation decreases and increases when you sort of get back to the midplane, which is similar to how a disk will have larger grains in the midplane, smaller grains in the dust and disk surface. And the other thing to notice is sort of in this region, sort of further out in the disk, you'll get some grains that will be radially entrained and stagnate in the wind and not sort of be carried out completely away from the disk, and will just sort of stay there and shield the disk from further radiation. But this only occurs in the midplane, where above the disk surface, if it's small enough to be carried up there, it will get entrained. So the next step was taking sort of this sort of model where you have all the dust sizes and putting it into RADMC, getting sort of synthetic observables from this. So some preliminary results of all this is, we put these disk models in RADMC, and we get sort of, we can compute SEDs, temperature plots, and as well as get the scattering and emissions from all the different dust grains. So we get these temperature structures where you get the sort of warmer dust above the disk, sort of cooler dust as it's sort of shielded from the disk below there. And this is sort of the example we used for this first set of synthetic images is sort of emulating a disk in a high radiation environment in the ONC, so about a parsec away from an ONB star. And excuse me, we get these sort of images which look quite promising to begin with. So we have the sort of same dust opacity sort of being reproduced by these in the sort of wings around the disk midplane. At this specific wavelength, we have sort of H-alpha emissions providing a nice sort of backlighting, which allows us to see this disk sort of in silhouette. And at different wavelengths, we sort of observe the sort of scattering from the host star shining above and below the disk. So the next step sort of in taking these images would be to reverse engineer the dust sizes that we had sort of input into the model and see if we can recover these. And the next thing we've sort of started looking at is comparing sort of the SEDs of when you have just a disk in isolation and a disk plus a wind. And what we've seen so far is that this introduces sort of a bump in the infrared and far infrared, most likely due to the presence of just more dust. But by the time you get to the millimeter, this bump sort of disappears. And so the future work of all this would be to, like I said before, sort of reverse engineer these dust sizes from the images. And then once we have that, look at a sort of population model of all different disk sizes, different radiation strengths, and see how we can sort of get good constraints on different dust sizes and different disk environments. So, in conclusion, the sort of external photoevaporation in these regions is quite important and will drag out not just gas but dust as well. And this dust is sort of largest at the midplane, smaller above, and you get this sort of radial size distribution as you go outwards, but only in the midplane. And sort of future incoming work would be to recover the dust sizes from these synthetic disks. So I'll take any questions now.
Thanks so much, Sebastian. Very nice talk. Questions? Yes.
very nice talk and very nice work. I'm wondering, sorry if I missed this, but what's your largest dust size in your model?
So,
do you reach centimeters or just millimeters in this?
So mainly just millimeter, and that only can sort of be pushed out about 100 AU. Yeah, once you get sort of above the disk, you get 10 micron, 1 micron. So this is sort of a maximum. We would expect maybe not to have that large amount of dust being carried all the way to the base of the wind. But yeah, the wind is strong enough to carry out quite large sizes.
Thank you.
Yeah, there is another question there.
Yeah.
Oh, okay. Well, there are two. Okay, Luca and then the other.
I've seen that among your to-do list there is add polarization.
Mm-hmm.
And I wanted to ask if you can give some more detail about that, in particular whether you want a continuum and line polarization or only one of them, and the widthband here I'm mostly interested in.
So I have not started looking at that at all, so probably something I could talk to you about in the break, because it's something I need to start looking into. Yeah.
Okay.
Yes. Yeah, thanks also for your talk. Maybe also I missed it, but what is the mass of the protostars that you're simulating, and then the mass of the disks?
So I think it's just a solar mass star with a, I want to say 10 to the -4 sort of solar mass disk, then 1% dust mass from there.
And are you planning to look at different stars and disks?
Yes.
Masses? Yeah.
Definitely, yeah. So we have a few other models with different disk sizes and I think different disk masses. So yeah, that's something we want to look at next.
Okay, let's thank Sebastian again. So the next speaker cannot attend, so we have as a last speaker of the morning, Luke Kite by Queen Mary University London, and they will tell us about chemical composition of externally irradiated disks.
Okay, hello everyone. My name's Luke. I'm a postdoc at Queen Mary University London. I'm going to talk a bit about externally irradiated disks, but I'd also like to speak to you about a new tool that we've developed for astrochemistry called SIMBA, which is a purely Python-based astrochemical solver and analysis code. So, okay. I think over the course of the last couple of days, we've already seen that chemical models are an essential tool in astrophysics because they help us interpret observations, constrain physical chemical conditions, and enable us to understand how molecular abundances evolve in time in a very wide variety of astrophysical environments. There's already a very wide range of astrochemical codes available, and many of these are extremely powerful. A lot of the time they include a lot of additional complexities, things like radiative transfer and molecular excitation. And typically this makes these codes very computationally expensive, and so they're usually written in very high performance languages like Fortran or C. This is great for optimization and for efficiency, but it does potentially introduce a very steep learning curve for newcomers to the field. It can sometimes mean that these codes are somewhat unintuitive to understand, and especially at a time when Python is becoming very much the most widely used language in astrophysics. So we wanted to take a look at whether we could develop a purely Python-based astrochemical tool, but retain the efficiency or close to the efficiency of codes written in these high-performance languages. So that's what we've developed SIMBA to do. SIMBA is a chemical solver that stands for Solver for Inferring Molecular Abundances in Astrophysical Environments. And to be more precise, it's actually a single point or zero-dimensional solver. So all that really means is that it takes in a small set of fixed parameters, just things like gas temperature and density, and so on. It then couples that with a chemical network, solves the rate equations, and as an output, you get molecular abundances with time. So we tried to develop this code around three main principles. The first is that it needs to be really easy to use. So this is just a typical example of how you might use the code. And you can see that you can initialize a model, run it, and then plot up some results in just a few lines of Python. It's very easy to incorporate this into Jupyter Notebook or something like that, or a much wider model that you might have that's Python-based already. We've also got very extensive documentation and tutorials online, and we've created a graphical user interface that lets you visualize in real time the outputs of the code, and I'll show you an example of that in a moment. The second key principle is that we wanted it to be very comprehensive. So all I really mean by that is that even though it's written in Python and is meant to be simple to understand and use, the actual chemical model that makes up the kind of backbone of the code still retains a high level of complexity. And we've based that around the very well-used established code DALI. So it includes a very wide range of chemical reactions and is compatible with well-used databases for astrochemistry like UMIST and KIDA. We've also fully benchmarked it against DALI so that we know that the outputs it gives are very robust and are valuable for real research applications. Finally, the last thing is that we've managed to make it efficient enough to use for real research purposes. So this typical model here, this is a model that contains maybe like 2,000 reactions, a few hundred species, and this will run in around 10 seconds on a regular MacBook laptop like this. But you can also set up much higher dimensional grids and parallelize the code quite easily yourself as well. Okay, so I'm going to just exit out of my presentation for a moment because I want to give you a quick demo of how you might use this user interface. It comes bundled with the pip installation and launches in your browser. It looks something like this. Basically has three panels. On the left, you can see an input form, and I've just populated that with some typical parameters from a protoplanetary disk model. You can click Run, and it will start executing the Python code in the background. You get a progress bar to update you in real time how it's coming along. Not so well. And what you should find that in around 10 seconds or so, the model runs and completes. So good, we've got some results. Right, the default view that you get straight away is just an interactive plot of abundances versus time. Here I'm just showing the top 8 species in this particular model for these conditions, but you can add as many species as you like or manually select from your chemical network. You've got a similar view if you want to investigate reaction rates. Again, you can look at the most efficient reactions or manually select from any species, any reaction in your network. And then finally, there's this nice view of a network diagram. So if I want to know something about the formation and destruction of a particular molecule, let's say let's look at atomic carbon, then you can immediately see the key reactions that go into forming and destroying that species, given the conditions that you've applied here. So the idea is that this tool is not really meant to compete with more complex models, but just to provide a kind of complementary tool that you can use to very quickly investigate the impact of changing parameters on the abundance of key molecules. Okay. So that was an example of how you can use the interface to investigate a single point model. But in reality, for research, we might want to extend things to higher dimensions and look at something that's more realistic in terms of physical structure. So I'm going to use an example inspired by the externally irradiated disks that Sebastian just talked about. This is where you have a protoplanetary disk in the vicinity of a nearby massive star. And this massive star has a very intense UV field that externally irradiates the disk from the outside in, sometimes launching a photoevaporative wind. So I'm just going to demonstrate how you might use a code like Simba to explore the chemical composition of a wind. The practicalities of this basically involve setting up a one-dimensional radial grid, and you can populate each grid cell with a different set of input conditions, different densities, different temperatures, the idea being that your overall grid matches the physical structure of the wind. And so in this case, you'd have the outer edge of the disk at one end, the UV source at the other, and the FUV radiation from the massive star would be incoming from right to left, launching a wind from left to right. Now, we populated this grid with parameters based on a very well-known physical model in the literature, and then investigated two chemically distinct models. The first is that what you might call a static model. This is a kind of typical method for computing chemistry, where you evolve the molecular abundances from some initial conditions for a fixed time frame in each grid cell independently. So each cell doesn't speak to the others, there's no material transport. But we also investigated what happens when you include dynamics. So we know the gas velocity of the photoevaporative flow, and we can incorporate that into the model by not only evolving the chemistry, but evolving the movement of the gas as it goes from the base of the wind on the left and flows through different conditions towards the UV source, like this. The main question then we're trying to answer just for this example is, do the dynamics matter for the chemistry? What's the difference? I'm going to show you some results just looking at one particular species in particular, which is water ice. So in this plot, I'm showing the water ice abundance on the y-axis and its position in the flow on the x-axis, starting at the disk and moving outwards. And this is a static model. You can see that in this case, you start with a very high water ice abundance at the disk outer edge, but as you move further out into the flow, the UV radiation dramatically increases, and at about 80 AU, almost all of the ice is destroyed, in this case by photodesorption. So UV photons are removing water ice from the grains and putting it back into the gas phase. Now, you can compare this to the dynamical model, and you see something quite different. What happens here is that the water ice survives much further into the flow, around 400 AU in this particular example. And this is because, although the water ice is still being photodesorbed by the external UV field, the timescale at which that happens is slower than the dynamical timescale of the gas. And so you can actually retain a much higher water ice reservoir just by considering the dynamics. And this has implications for observations and things like this. Although this is only one particular molecule, one of the immediate things that you might think about is the fact that if you lock up such a huge amount of oxygen in water ice for a considerable proportion of the flow, then you actually limit the amount of oxygen available for gas phase chemistry. And so this kind of trickles into the reservoirs available for gas phase reactions and really shifts the balance of what formation and destruction pathways you're seeing for other species. Okay, so we investigated this in much more detail in our code paper, which is now on archive if you're interested in that kind of thing. But for now, I just want to say thank you very much for listening. I'll leave you some of my summary points up here. Firstly, Simba, it's a very accessible and easy to use Python-based astrochemical solver, and easy to pip install and start using within a matter of minutes. Ideal for real research applications, but I think it's also a valuable tool for things like smaller, maybe like master's projects, and as an educational tool. And in this particular case, we gained some new insights into the chemistry of photoevaporative winds, comparing dynamics and static models. Thanks very much.
Thanks so much, Luke, for the excellent talk. Questions? Yeah, there is a question over there.
Hi, thanks. This is Aditya from Tartu Observatory. From the solver side of the point, at least from astrodynamics, with long-term horizon planning, you tend to get fixated with these floating point errors that come in, especially with Python-based solvers. So is Simba more like can it accommodate for those errors when you identify them, or do you estimate batch processing and then you club the entire solver together? Like, at what time scales do you start to imagine the errors would start to appear in your
I'm not sure what errors exactly you mean. You mean like numerical errors associated with the...
Yes, with solvers, yes.
I mean, I don't think I can give you much details on how much I know about that, to be honest, but all I can say is we've benchmarked the code very extensively against well-established code DALI, which uses C and has a and we've kind of investigated many thousands of cases over varying conditions, covering many orders of magnitude, and got excellent agreement. So numerically, I think the solver is robust.
Okay, great, thanks.
Other questions? Perhaps I have a quick question. Maybe you said it, so sorry if I didn't pick up. Is Simba on GitHub?
Yes, it is.
Okay.
Yeah. Oh, no, I didn't put it there, sorry. It is, I can share the link.
Okay,
later.
excellent.
Yeah.
Other questions? Well, if not, let's thank Luke again.
Thank you.
And more in general, all the speakers in the morning. And we are now closing the session, and we'll come back after lunch at 2 p.m.
Check, check, check. Yep. Check. Yep.
please take your seats. We have quite a ride ahead of us. It's a tight schedule, so I ask all presenters to try to be on time, and if you're not on time, I'm gonna kick you out. So that's as simple as that. All right, so we start this new session. My name is Luca Fossati. I work at the Space Research Institute. I'm one of the EXOHOST drivers here. And we start with the next invitee speaker, who is Vardana Dibekian from Porto. And please, go ahead.
Thank you, Luca. First of all, thanks also all the organizers for this really very nice conference. I've been enjoying it a lot. And thanks for inviting me and providing financial support for this. So today I will speak about the potential link between stellar and exoplanetary compositions. But before going into that, I would like to just comment about this slogan of know the star and know the planet. We see it everywhere so many times that I started to question, is it really true? If we know the star, do we know the planet or not? I think it's just a requirement to know the star. But if you know the star, it doesn't mean that you will know the planet. Let the people who work on disks or planets also do something. It's not everything depends on the stars. And Anna, if you are thinking to apply for a new grant, so you may decide to change the slogan a bit. Although I understand that it doesn't sound very positive because you have two don't, but some variation of it. But anyway, so this talk is going to be about how knowledge about the star can be useful for the characterization of the planets, to know the planets. So from the previous session, also in this session, we will hear that there is a clear link between the presence of planets and architecture of the planets and also stellar metallicity or composition of individual elements. But in this specific session, we are going to we are going to discuss better. Also, there is a link between the composition of the stars and planets, not only their formation, but architecture, but also their composition. And why we need stellar abundances? More direct. I guess everyone knows the answer, but I think it's always good to remember. So, in principle, the planets can be observed also directly, but these direct observations are more limited. We observe only very massive stars, and the parameter space that they cover is limited. So that's why we have to look at the properties of the information from the host stars, which are that can provide only observable information about the relative information from the disk. But we have to remember that we are speaking about the two quantities, stellar abundances and planet composition, that are not directly derivable. They are inferred quantities indirectly. So just to remember that we cannot get exact composition of the planets, but we get them from the radius and mass measurements mostly, and using some models, interior models. There are several tools, public, not public, and many groups that are working on this. But again, remember that all these interior compositions that we derive are based on assumptions and radius mass measurements of planets that are taken from the measurements of the derivation of the host star mass and radius. And the same for the stellar abundances. These are abundances that we cannot measure them directly, while the mass or radius of some stars we can derive in model-independent ways. So there is no way to do that for stellar surface abundances, as we have seen in the talks of Elisa and others in the previous sessions. I will not focus on this. So when we try to link the composition of the stars and planets, we make a a very important assumption, that the stellar atmospheres reflect the composition of the disk. Otherwise, I mean, this is the link. The disk composition is the link between the composition of planets and the host stars. So this is a key assumption. And one has to question whether the present-day stellar abundances that we observe in the surfaces of the stars, do they really reflect the composition of the primordial disk where they have been formed or not? So we know that there are internal processes in the stars that change the composition, atmospheric composition of the stars. Even if we forget about the variation inside the stars, the composition of the stars, as Masanobu was speaking about. So only in the surface, with time, the composition of different elements change with time. And this is because of several processes happening. There is usually we call them atomic diffusion, but you have basically because of the gravity they can sink, but because of the radiation they can also accelerate and go up. And there are rotational mixing. There are other parameters that don't have that much of physical meaning, like turbulent mixing, try to help to all these processes together to match the observations. But what we know is that there is a variation of abundances, of surface abundances with time, and this variation depends on the mass of the planets, and the stars, and basically how big is the convective envelope of theirs also. And this the variation would also be different for different elements because they have different molecular weights also. So we tried to see what would be the impact of this variation in the stellar abundances when we are trying to link the composition of stars and planets. So on this figure, I showed the difference between the initial iron abundance or primordial iron abundance minus the present-day iron abundance of around 25 or 30 stars. They are all FGK stars hosting rocky-like planets. And we use the model from Morgan-Dill that takes into account this atomic diffusion, radiative acceleration, turbulent mixing, calibrated for the sun to get the lithium abundance for the sun. And the crosses show the change. The ages are ages of the stars, and the crosses show the difference between the primordial and the present-day abundances for different stars. So you can see that the older the star is, the higher the difference between the primordial and present-day abundances. And the red error bars show the typical, the uncertainties of the iron abundance that we measure from the present-day composition. So you can see that for older stars, depending also on their temperature, the difference can be significantly larger than the errors or uncertainties that we provide for these stars. So this is also a function of temperature. And more or less the same structure we see if we look at the abundance of magnesium or silicon or oxygen and carbon. The good news is that most of the time we are interested in abundance ratios when trying to use this information to constrain the composition of planets. And we see because of the similarities in the behavior of the change, of the variation, the abundance ratios remain almost unchanged with time. So this is a good news for planet modelers who want to use the interior, the stellar constraints for the interior characterization. So another thing in principle that can affect the stellar composition, stellar present-day composition, is in principle planet formation. So from the early works when correlation between the presence of planets and giant planets and metallicity was found, they interpreted it as a self-enrichment because of the accretion of hydrogen and helium-poor gas into the stars that could enrich the metallicity of the host stars. And then there was this hypothesis that if there is some fractionation happening in the disk, and there is an accretion of fractionated material, then it would lead to a correlation with the condensation temperature. So here in Melendez et al. In 2009, they found the correlation between the abundance of the sun relative to the other solar twins in the solar neighborhood as a function of the condensation temperature. And their interpretation was that because of the formation of rocky planets in our solar system, these refractory elements remained in the rocky planets of the solar system. That's why we see this trend. While other solar twins maybe don't have these rocky planets, that's why they are not depleted in refractory elements. Well, some years after I proposed that this may be related just to the galactic chemical evolution, and some recent works also reached to similar conclusion that here maybe what we are seeing is that the age effect, so the other solar twins maybe have different ages, and if you also take into consideration the ages of the stars, maybe it's not sun is not chemically peculiar, except lithium. So another potential possibility of change of stellar surface abundances is planet engulfment. I mean, if galactic chemical evolution can be used to speak about the chemical peculiarity of the sun, if you observe binary stars that are similar in terms of the stellar properties, and you see a variation in their compositions, one versus the other, this cannot be explained with the galactic chemical evolution because these two stars are coeval. So maybe it's related to the planet engulfment or the trap of elements in some planets. And there were two interesting works recently published in Nature, Astronomy in Nature, where they concluded that 25% or 8% of the solar like stars in binaries can be polluted by the engulfment. Their composition can be affected by the engulfment of planets. Actually, there was a very recent theoretical work where they tried to simulate the formation of stars in open cluster, and they realized that in principle from 10 to 30% of the stars in open clusters can have a variation of element over hydrogen by 0.1 dex, which is similar to the engulfment of around 2 to 5 Earth mass planets. More than that, in a recent work with our student Barbara, we looked at the population synthesis results from the Bern model, and we tried to see which kind of planet engulf most, and when they engulf, and what is their composition using the planet population synthesis model. And then we also, using the stellar interior models, we tried to see what would be the impact of the engulfment on the composition of the host stars. So we looked at 3 cases. The engulfment happens at 8 million years after the pre-mean sequence, 0 age mean sequence, then 60 million years and 4.5 million years. And then we looked at 3 cases, engulfment of 2 Earth mass planets, 5 Earth mass planets, and 10 Earth mass planets. So basically, we see that if the engulfment of these planets happens quite early, like 8 million years or so, the effect is very small because everything gets mixed very quickly inside the stars because this is for one solar mass star. So because of the larger convective envelope, everything gets mixed and you don't see much of an effect. If the engulfment happens at 60 million years, which is this case, depending of course on the mass of the engulfed planet, you can have quite a big variation, but this will be changed with time. So the engulfed material, again, because of the atomic diffusion, everything what I was discussing in the previous, so this fluctuation will be reduced with time. And the same if the engulfment happens at later stages. Basically, in this work, we concluded that if in binary stars, we assume that we can detect a difference of 0.02 dex in metallicity, and we assume that we observe all these stars right after their engulfment within 1 gigayear or half a gigayear. So basically, we are just seeing observe them after engulfment. In this case, in this most optimistic case, only 20% of the stars in the Bern model population synthesis result we can explain with the planet engulfment. So in principle, we conclude that the planet engulfment should be a bit rare, and their impact on the stellar composition shouldn't be very high. Okay, now let's move to the main part of this presentation, which is the potential link between the composition of the stars and planets. Because The reason that we are exploring is because when we get the interior composition of the planets using the radius and mass, there is a degeneracy in the model. So different composition can explain the same density. But if you assume a given abundance ratio, for example, if the planets, rocky type planets, have the same abundance ratios of refractory elements like iron and magnesium as the sun, as their host star, then it can significantly reduce the degeneracy and improve the characterization of the interiors. So this was demonstrated in the work of Caroline Dorn in 2015. So basically, they show that if you have the mass and radius measurements, they use some synthetic planets, and then they use their models to, they knew internal composition of their synthetic planets, and they used their models trying to get the core mass fraction of the planets. And when they didn't put any constraint from the host star composition, they could get a very wide ranges of core mass fraction, some of them even unrealistic, while when they were assuming that the magnesium over iron ratio or silicon over iron ratio is the same as in the host star, they could significantly reduce the degeneracy and get a very good precision in the core mass fraction. But still the question is whether this assumption is correct and holds. So if we look at the sun or solar system, I mean, if we look at the bulk composition, we see that the sun and earth are very different. But if we look at the specific abundance ratios, like magnesium over silicon or iron over silicon, elements that have very similar condensation temperatures and they are refractory elements, we see that there is overall good agreement between photospheric composition of the sun and many of the rocky objects of our solar system, including the meteorites. The exception is Mercury, but as discussed in this conference, it may be related to the giant impact. So some other theoretical works also, where they try to look at the formation of planets in a given in disk with different composition, they reach to the conclusion that I'm speaking about this specific work where they show that the magnesium over silicon ratio in the stars and in their planets, independent they are rocky, icy, or giant, follows a one-to-one relation. The same for iron over silicon ratio. While you cannot say much about the carbon over oxygen ratio. It's almost independent of the composition of the disk because it depends exactly where it's formed. So similar results being obtained by Bond et al. In 2010 and 12. So the rest of my slides will follow some chronological order of these works. So more or less this work started at least in our group, in my opinion. So there was this very interesting paper by Dressing et al. In 2015 where they showed that based on the relatively small sample, they found that all the low mass planets up to 6 Earth masses, they follow the same, they all lie on the same composition line. They assume that they all should have Earth-like composition. Then we thought that, okay, if all these planets have the same composition, and if we assume that their composition reflects the composition of the host star should have also the same compositions. We managed to get spectra of 3 out of the 6 of the stars, and we tried to get the core mass fraction of the planet building blocks. So we used a very simple stoichiometric model, assuming if you have a given composition in your star, assume that this composition reflects the composition of the disk, which kind of compounds you would form. So saying like oxygen will go only to form these molecules, and magnesium here, this, and that. And then we calculated the iron mass fraction of the planet building blocks based on the composition of the host star. Basically, we found that, I mean, you can see the very large error bars and very large dispersion, but please focus on this part. So basically for the 3 stars, we found relatively similar composition to iron mass fraction to what we would obtain for using solar abundances. The exception was Kepler-10, and actually if you look, the Kepler-10b and Kepler-10c specialists, they appeared a bit upper from the line, so maybe we concluded that maybe they are a bit less dense than Earth. as we obtained for the host star composition. Then there were several very interesting works. For example, this work by Plotnikov and Valencia. So they looked at they using the interior models of planets, they characterized they obtained the iron over silicon and iron over magnesium ratios of the planets. Of the planets based on the radius and mass measurements. So these are the group of planets that are potentially rocky, and these are the planets that within the error bars, they cross the line that they can be rocky. So, but the main results of their analysis, and here in the red, they show that the distribution of these abundance ratios for all the planet host stars. Not the host of these planets, but in general, all the planet host stars. And you can see that in principle, the variation of these abundances in this small sample of planets is significantly larger, the range is significantly larger than what you get from the abundances of the host stars of all planets, giants, small, a few thousands. So it means that something happens in the disks, so it cannot be this large variation cannot be explained with the host star abundances, right? They also, in the sample, they had also derived abundances of 4 of the whatever number of the host stars, and then tried to see if there is a correlation between the host star abundance and the planet abundance, but the sample was too small to make a general conclusion. The following was work by Schulze and collaborators, and they analyzed 11 potentially rocky planets. They used their interior models to get the core mass fraction of the planets, and also using similar model as I described in Santos et al. They used abundances of the host stars to constrain to estimate the core mass fraction of the planet building blocks. And here you show their distributions. So basically, they found that for most of them, the core mass fraction of the planet and core mass fraction coming from the host star agree within 2 sigma. There were 2 exceptions, and they were potential super Mercuries. But in my opinion, when you are comparing, I mean, this is the way in principle to go to compare stars and planets on this. But if you have large uncertainties, and even if there is a correlation, you cannot get anything. So that's why we decide, I mean, if you have large uncertainties for any of the parameters, they will, obviously, by definition, they will agree within a given sigma, right? So we decided to look at this problem in a different way. So what we look is that we try to see if there is a correlation between the composition of the planets and the host stars, not individual ones, but in general. So first thing, what we did is we looked at the density of the planets as a function of this iron mass fraction calculated from the host stars. So this is not just the density based on the radius and mass, but the density of the planet divided by the density of a planet with the same mass, but assuming Earth-like composition. This is important because 2 planets with exactly the same composition but different masses will have different radius because of the mass contraction. So basically, you need to normalize it to somehow take into consideration this contraction effect. And we found a good correlation. Actually, we also, I think we had a sample of 22 planet and host stars, and we also modeled the interiors of these planets, and if I plot the iron mass fraction of the planets as a function of iron mass fraction of the stars, we see a similar correlation, but this correlation is a bit better, and in my opinion, it's better because there are no models involved on the y-axis. Otherwise, you have to assume some models to get the iron mass fraction. And in this paper, we identified 2 groups, super Mercuries and super Earths, and we found a correlation, linear correlation between these 2 quantities. Actually, because there seemed to be a bit of a separation between these 2 groups, we hypothesized maybe these are 2 different populations. We said that maybe super Mercuries are not formed through giant impacts, because if it's a giant impact, it's a stochastic process, and you wouldn't expect to have a gap between the 2 populations. Anyways, so basically in this work we found the correlation between the composition or density of the planets and the iron mass fraction coming from the host stars. And please remember that this is not iron abundance. This is iron mass fraction, which is more similar to the iron over magnesium ratio than iron abundance. But then, using a bit bigger sample, I believe, there was this work by Brinkman et al., and they argued that the correlation that we found between the core mass fraction of planets and the host stars depends on the method that you are using to feed the data. And if you don't consider uncertainties of the variables, you use like simple ordinary least square fitting or orthogonal distance regression models that take into consideration the uncertainties, you get different results. And this is true. And in a more recent work, we tried to, with an updated sample, we tried to see if there is a correlation between the iron mass fraction of the planets and their host stars, and we use different fitting methods, including the Bayesian inference or the weighted least squares. Basically, in all cases, we found that the slope changes significantly, but it's always significant, statistically significant, the slope. Actually, we didn't find this population of supermercuries, and previous work also indicated that maybe this was because of the data that we used, and some of the planets provided, they updated the parameters of some of the planets, and they didn't appear as supermercuries anymore. But there was an interesting comment by Schulze et al. That maybe the supermercuries shouldn't be considered the planets that have high iron mass fraction in general or high density, but those which have high iron mass fraction relative to what you would expect from the host star composition. For example, 40 or 50% in core mass fraction can be a planet with this core mass fraction can be considered as supermercury if it's around metal poor stars, where you would expect to have a very low core mass fractions. Yeah, but this is still ongoing debate, and there are works that, and Kevin will speak about this work, and that have a bit different conclusions. So going a bit further, we try to see if what the ratio of the planet iron mass fraction and stellar iron mass fraction, if it depends on the parameter of the parameters of the planets. So basically, we didn't find any correlation with the planetary mass, but we found a strong correlation with the radius of the planet. And the reason is very simple, because basically you use the density to model the interiors of the planets, and you have the cubic of radius in the density, while density depends on the mass just linearly. That's why we think there is this dependence on the radius. But you can see that if you look, for example, iron over magnesium ratio in the planet, and using the interior models, and in the star, this difference can be by a factor from 0.3 to 10. So it means that rocky planets may not have exactly the same iron over magnesium composition as their host stars. Yeah, there was also this recent work where they tried to look at the planet density as a function of the host star composition, in particular iron over magnesium over iron ratio, and they in addition to the FGK type stars that we analyzed in our sample, they added also a few M dwarfs, and then they conclude that this helps to improve the statistics, the correlation. And actually, I was a bit surprised that they found a correlation with planet density, just the density, using density. Although in the paper they also found a correlation between the uncompressed density and this quantity, which to me makes more sense, because the 2021 paper I was presenting, actually I started to work on it in 2018 and 2020. I was writing part of it, and then I stopped because I was not finding any correlation. I was about to submit a paper saying that there is no correlation, but I was using planet density before realizing that it's not a good parameter to consider because of the contraction, as I was explaining. Anyway, even if you use uncontracted planet density, you see a correlation as well. So there have been few more works, follow-up works, trying to see if the planet core mass fraction or iron mass fraction also correlates with the age. And then there was this work where they found a correlation with age. And a more recent one, they tried to, they modeled the galaxy. They followed a simple model of galactic chemical evolution, and then assuming a given composition, different parts of the galaxy, and from this composition they made planets, and then they used interior models of their planets to get the iron mass fraction of their planets, and they saw that in principle the prediction using galactic chemical evolution and planet formation models, you should expect that the core mass fraction of the planets should change with time. So basically at the early universe or early galaxy, the core mass fraction of planets mostly should be lower than what we should have today. Okay, I'm finishing. Okay, but I mean, personally, I think if there is a correlation between composition of the planets and composition of the stars, and because of the galactic chemical evolution, that abundances or abundance ratios change also with age. So in principle, this is pretty much expected to have a correlation between the composition of planets and ages of the stars. So what we should do more, I think, what is very important, and Kevin will speak about that, is to use homogeneous parameters, not only for the host stars that we were using in our works, but also for the planets, because the data, at least we were using in our works, were taken from NASA Exoplanet Archive, and the radius and mass were derived by different groups. So there was an inconsistency. And also we should try to improve if possible, improve the precision of the radius and mass measurements. Here in this work, they studied what would be the impact of different uncertainties on mass and radius on the derived iron mass fraction, uncertainty of the derived iron mass fraction. Of course, there is an intrinsic error of about 5% in iron core mass fraction, so independent how precise your radius and mass is because of the degeneracies that I was speaking about. Just a comment a bit on this. When the authors looked at the core mass fraction of planets based on the radius and mass measurement as a function of metallicity, I believe there was a comment that this somehow disagrees with the results in our work. I don't think that there is a disagreement, because what we were looking is, again, as I stressed, that we were looking at the iron mass fraction, which is more iron over magnesium than metallicity. Actually, if you look at this density or iron mass fraction as a function of metallicity, we wouldn't see also a correlation. In principle, there are other windows to study the star-planet chemical connection. One of them is to look at the binary stars, where one of the stars has a planet, the other one doesn't have a planet. Maybe this could help us to see what would be the impact of planet formation or planet engulfment on the composition, or looking at the polluted white dwarfs, especially if they are in binary system. If one of the components is a main sequence stars, you know what to expect, and then you see the material of the composition of the polluted material, and then you comparing them, maybe you will get something. And this is my last slide. Just I want to stress that we need to have better models, so you see interior models of planets. We need to have homogeneous data, as precise as possible, and if possibly accurate radius and mass measurements, and a lot of planets around metal poor stars, I would say, because this is the region that we are missing. And PLATO, I believe, will be super useful in this regard. So thank you for your attention.
Thank you, Adam. Questions? There.
Thank you for this very nice overview. I have a question about your first point, that the stellar abundance varies with time, but the key elemental ratios remained unchanged because you focused more on the rocky refractory components. Is also true for oxygen over silicon, for example? It also remains?
Yes, very similar. I mean, again, I'm speaking about AFGK type dwarfs in the main sequence. When they evolve further, the changes can be significant. when they reach to the red giant branch, then it's again becomes like primordial.
Thank you.
We have a question here.
Thank you. You cite these old works basically saying all low-mass planets have the structure of the Earth. In principle, I mean, when you measure mass and radius of a planet, each point has a large scatter. But is there statistically a relation that one can say the data that we have is consistent or inconsistent with the assumption that most planets have the structure like the Earth? Statistically.
Let me. So this is the iron mass fraction, and it varies from 10% to 80%. I can calculate the sigma and the mean and
exactly. That's
yeah, I think
so that would be like 3 sigma detection that it's inconsistent with Earth-like composition.
No, I think most of, I mean, we see that a bunch of them are, most of them are around 30 or whatever, similar to the Earth, most of them. But the stars are also, the stars have also composition that are not very far from the Earth, solar composition.
Questions? We still have some time. I have a question. Do we then know of any true solar twin on which we can, true solar twins, on which we can redo the experimental methods that
It depends how you
true
define
solar twins,
true.
also
What is
in age.
Yeah, there are a few. Well, this is an interesting discussion. What is really true solar twin? Because the astroseismologists have their own definition. What is a solar twin by astroseismology, right? They should have the same oscillations or whatever. So, but I think there are few, yes, that have very similar parameters as the sun. And if you consider the age, then sun becomes similar to those.
And
except
that experiment has been done using these stars?
Yeah, there was this paper I mentioned, but it was. Yeah, I can send you the.
Okay. Someone else? Yes, here.
Thanks, Vaden, for a very nice talk. I was curious about the engulfed planets you were mentioning. So you were talking about the change in the metallicity, or the iron abundance, yes. So you said it's hard to detect, but is there like do you have an estimation of how long you would see this change of?
This is exactly that. This is, for example, in this case, the engulfment of 10 Earth mass planet, 10 Earth mass planet with a composition that on average 10 Earth mass planets have. If you have an engulfment on at 60 million years, this will be the change in iron abundance. And this is how it varies with time. So you see that when it reaches to 1 gigayear, so you have the effect, it becomes a half. So at 4 gigayears, it will be 0.02 or 0.03 tex, which is the limit of the precision that we have.
Yeah, I was mostly looking at if that happens during at 4 gigayears. Then it lasts maybe a bit less long.
And I think it's because it's in log, it appears quicker, but I think it's just because of the scale.
So maybe it would be also interesting because there are these star-planet interaction in terms of the rotation of the star that might be changing. So having both measurements of change in the metallicity and in the rotation of the star compared to a normal evolution, that could bring two independent constraints on the fact that there's an engulfment. I don't know if the people are looking at this, but maybe.
It's also quick, right?
Yeah.
Quickly they go. Okay.
I think actually it's quicker than the metallicity, but.
Okay, thanks.
Let's thank our speaker again. So it's my pleasure to introduce Yoshi Eschen from the University of Warwick.
This is working, cool. Okay. Hello, I'm Yoshi, like in the Mario game. I'm a first-year PhD student at the University of Warwick, and I'm currently at on the ING studentship on La Palma. So actually right now I'm just like not really doing research, but I'm happy to show you what I've done in my first year so far. And this is basically about decoding cell abundance's influence on planetary composition. And Valan already gave a really good intro to all of this, so I'll just like kind of skip my intro, like make it very quick. So we know there's some kind of link between planets and stars, and we can see this, for example, also when we look at the proto-sun and Earth, which in this paper was produced by Haiyang Wang, the plot. And if this is universal, we have a very similar link also for exoplanets and their host stars. Hence, planets around metal-poor stars should have less refractory elements and hence be less dense, as we've seen in the plot from Vadan, which I also reproduced on this slide here. So if we go to the low iron stellar mass fraction, we have a lower density of the planets. This metric also represents these metal-poor stars, as Vadan has said. However, also what really pops out in this plot is that we have a lack of planets around these metal-poor stars. So the majority of planets orbiting stars are very similar to our own sun. And so we basically try to fill up this space of planets orbiting metal-poor stars. For this, we started looking at the public APOGEE DR17 sample. We applied some cuts, so we mainly have FG, K, and M stars here only in the sample. And also we had like some quality cuts and so on. And I just like plotted them here on an alpha, FE, and FEH diagram. And then I computed the kinematic probabilities to be in the thin disk. So all the thin disk stars here are shown in this turquoise. All the other ones are in purple. We did the same for the thick disk and also for the halo. These kinematic probabilities are interesting because we think that thick disk stars are more metal poor, while thin disk stars are more metal rich, which is basically due to the formation. In the old times of the Milky Ways, there just wasn't much iron around because that had to be produced by type 1a supernova, which just didn't happen for old stars. Hence, we're interested in these thick disk stars up here, or even the halo stars, which also was shown in Daisy's talk earlier on. So we then just like plotted the planets that we can cross-match with apogee on here, which all lie in this like lower cluster, and also kinematically they're all in the or like the majority of them is in the thin disk. So there's only like very, very few well-characterized thick disk systems. Again, that's kind of where we aim to study thick disk metal-poor stars to see if trends actually hold. To now actually find these stars, we developed some machine learning code and tried to actually identify the clusters based on stellar abundances. So we've previously just like seen based on kinematics, we can kind of see if a star is metal poor and alpha enhanced, but we then moved on to doing this with machine learning and developed a tool that is identifying the three clusters, the thin disk, the thick disk, and the halo, based on where they lie on this alpha FE, FEH diagram. And here I'm just like plotting the probability that a star is chemically in the thin disk based on our machine learning. And so everything that's green cyan on here means our code is saying it's thin disk, which looks fairly similar to what we've seen with the kinematics if we looked at the trend. The same goes for thick disk and also for halo, which is quite nice. So then I just like created a plot overall to show the stars that have a probability high of 70% to fall into one of these clusters. So there's no real white lines in between. They're not perfectly in each cluster. We have some scatter in between. But this is just like the stars where we can tell quite well. And this basically now allows us actually to identify targets kinematically or chemically that are in the thin, thick disk, or halo. To now actually just move on identifying more of these metal-poor thick disk stars, I wanted to just like show some more recent discoveries where we also tried to do some material structure modeling. And the first thick disk target we have is TOI 2345, which was accepted and on the archive this week. It's a slightly metal-poor and alpha-enhanced K-dwarf, which has a kinematic thickness probability of 85%. So I plotted it on the tumor diagram here as well. Everything in purple here are thickness stars, and we can see it falls quite nicely into the purple region. It is orbited by two planets, a super-Earth and a sub-Neptune. The super-Earth is at a very short orbital period, while the sub-Neptune is at a longer orbital period. And then, with also getting some HARPS-RVs, we could quite nicely determine the mass to a 4 and 3 sigma precision. This then enabled us to do interior structure modeling. For this, we used Planetic, which also was introduced by Daisy earlier on, which is a tool developed by Joanne Egger, and that uses deep neural networks to determine the planet's interior structure. And it takes into account the stellar abundance links. And it considers a few different links, so either it's just like the proper stellar abundances, they can be iron enriched, or they can just kind of be uniformly distributed. And what we also then did was we added a devolatilization prior for the stellar abundances, which is done by EXOHOST, which was proposed by Wang et al. In 2019, which is kind of more applied to rocky planets. So it's basically kind of devolatilizing the star and only leaving the abundances that a rocky planet should have. So this is what the results look like. This is our planetic results, and we can see for our slightly metal-poor star and the thick disk here for the super-Earth, we have a small core, we have a quite big mantle, and not much of an envelope, which is also expected because it's also an ultra-short orbital period. The thing that's quite interesting is that A1 and A4, which is the stellar abundances, and A1 and A4 is the EXOHOST devolatilization, they are very, very similar. They agree really well on the core and mantle. However, if we actually use EXOHOST, we are able to constrain our core and mantle mass fractions slightly better, which is quite nice. But yeah, nothing new here besides that we're better to constrain it and we have a small core as expected. We then moved on to another thick disk system, which is TOI 4311, which is also a K-dwarf, also slightly metal poor and alpha enhanced. And again, also kinematically lies in the thick disk, also shown by the purple area on the tumor diagram. We got K-ops and test data on this one. The paper isn't out yet, so I can't show the K-ops data. However, it enabled us to also determine the radius quite well, and then also with HARPS data, we were able to constrain the mass very well. From our machine learning, we were then also finally able to actually identify more quite exciting targets, and the one that is most exciting right now is the target I'm showing here, which we are currently observing. And just to kind of link this back to the clusters I've shown before, on our alpha FE, FEH diagram, it lies very, very much in my thick disk cluster. So that's a very exciting target. And also in the tumor diagram, it lies very, very far out in the purple area. And we color-coded here also just by the metallicity, and it's also very, very metal poor. So we'll get data on this soon, and we're quite excited to see what we'll get from also analyzing this interior structure if we get more insights. Just to conclude all of this, we have a lack of planets orbiting metal-poor stars. We are using machine learning to identify chemical clusters, and combining these chemical clusters with kinematic galactic properties, we can identify new systems to just make up for the lack around metal-poor stars. We currently have ongoing observations, and that will hopefully enable us to explore trends in the future towards these metal-poor stars. Thanks a lot.
Thank you, Yoshi. Questions? Yes.
Very nice work. So I didn't understand very well. So you selected first the stars that are metal poor and alpha enhanced from APOGEE, and then these are the ones you are following with radial velocities?
Yes. So we select using the GMM from the two clusters, and then we can also select kinematically. So we have different methods, or we can combine them. And so the target I finally showed is combined. The ones before we were mainly doing through kinematics.
And how many do you have that are following?
So we have quite a few exciting targets that we're actively following. Right now is this one, but we put a lot more proposals in.
Okay.
Right now.
And you
fingers crossed.
And you plan to do your own stellar characterization with the HARPS data?
Yes, we do plan this. So for 2345 and 4311 I showed, we did our stellar characterization with the Hubs data. Thanks, Vardan, as well. I'm pretty sure he was on the team. And yeah, for the ones we currently have in, we'll also do our own stellar characterization to also confirm some abundances. Yeah.
More questions? Okay, good. Then let's thank our speaker again. So our next speaker is Maria Zantacchi from INA Farcetri in Italy.
Hello everyone, I am Maria Zantacchi. I work at the Osservatorio Astrofisico di Arcetri, and today I will present our work on the results of the preparation of the Ariel space mission, and what can we say about this planet population if we look at the galactic point of view. Okay, we know very well, we have seen these plots many, many times today. I'm very happy that our disk is mainly divided into two components, that they are chemically separated, and this is reflecting its different formation history, the thick disk and the thin disk, with different alpha over iron abundances and iron abundances. And since we know very well that metallicity is one of the key drivers for planet formation, we can assume that the galactic chemical evolution can profoundly affect the planet demographics across the galaxy. So there are recent theoretical works that they want to study this. And for example, in the upper plot on the left-hand side, Bertrand et al. Have used planet population synthesis models and a Milky Way analog, and they tried to calculate occurrence rates of different planets in different galactic components, and they find that giant planets are more common around thin disk stars and bulge stars, while Earths are more common around the thick disk and halo. Later, or actually not, 1 year ago, Nielsen et al. Used a different disk and chemical model to infer compositions this time, and using abundances from the ground-based spectroscopic surveys. They find similar things, that giant super-Earths and gaseous planets are more common around alpha-poor stars, while rocky and Earths are common in all populations, and there are several works on this subject. But I wanted to see this problem using the observer's point of view and taking advantage the very good data that we are obtaining for the preparation of Ariel. Ariel, it will be discussed also tomorrow in extents, that is a medium-sized exoplanet mission that will observe, we study the composition and will observe their atmospheres of around 1,000 known planets. The Stellar Characterization Working Group that I participate has the goal to provide a precise characterization of the host for a variety of spectral types. And to do that, we have deployed a long-term observational campaign using high-resolution spectrographs and high-signal-to-noise data, where we'll deliver atmospheric parameters, activity indices, abundances for several elements, masses, radii, and abundances in a homogeneous way. So far, we have delivered a catalog with 358 solar-type stars with high-resolution spectroscopy based on 2 different methods that they cover different parameter space. The first method is the equivalent width, that is based on the measurement of iron lines, where the iron is derived based on a curve growth approach, temperature, and surface gravity based on the ionization and the excitation-ionization balance. Where this method is not very efficient is when we have rotation. You can see in this plot the effect of rotation in 6 of our stars with similar parameters. So when we increase rotation, the lines become shallower, so the equivalent width cannot be measured efficiently. So we use a spectral synthesis that is based on the that the parameters are derived based on the fit between an observed and a synthetic spectrum. And both methods use a similar methodology, where the parameters are derived in a three-step process. So at the first run, we have a pure spectroscopic analysis where we get the temperature, gravity, metallicity, and some velocities. While in the second step, we fix gravity because it's one of the most difficult parameters to constrain spectroscopically, using Gaia astrometry and photometry as well. Then, once we have these parameters fixed, we rerun again, and we obtain our final parameters. And as you see in these HR diagrams below, we have the different results in the different runs, and we see that the run 2, we have a much better agreement, in particular for the cool stars for the sample, where the parameters fall very well on the isochrones. But one very important thing of this type of works, as mentioned in the whole conference, is to guarantee homogeneity is very important. So we use different methods, and we have to guarantee consistency. So we try to follow them as close as possible using the same ingredients. For example, the radiative transfer codes, atomic data, and the model atmospheres were the same. And we use the same prescription of surface gravity. Also, the masses read in both methods were derived using the isochrone fitting. Other things that they can introduce inconsistency is the use of different spectrographs. We cannot derive all stars, 1,000 stars with the same, because some stars are in the north-south and have different magnitudes. So we use different spectrographs of different resolutions with different configurations. So I have tested some spectra of the highest resolution, these HARPS-like instruments, and the lowest resolution that is FEROS-like. Actually, FEROS has the lowest resolution in our sample. And we can see that by comparing the parameters, we have very good consistency. So we can we have calmed ourselves down for this problem. Also performed many comparisons. I don't have time here between the two methods, and the parameters agree very well. So finally, we have derived the parameters for the 358 stars that have their parameters exploded in this HR diagram, and their planetary parameters are below. They have not included in our analysis non-LTFS and 3D model atmospheres, but these are things that in this sample, in this parameter space, are not very important, at least for the Arion abundances. Now, we want to look further into this sample and see where our stars lie in the galaxy. So I plot here the galactic coordinates, and this is the solar neighborhood, essentially. But if I plot the whole NASA exoplanet catalog, the stars will not be further than here, until it's a solar type. We are limited by the detection methods themselves, that they are very close by. But when we look at the kinematic separation, we can see that we have some representation of the thin and thick disk. So we look deeper in their chemistry in that, and we find that they obviously have some the differences in the iron abundances that you see in this histogram, and in the plot below, that is the cumulative distribution function, you see in the solid lines, in the purple and the green, the aerial sample. So they are separated, and in the dashed line of stars with no planets. So they have different iron abundances, being the planet host being more iron rich. The other thing that I want to point out, that was shown also in some talks before, is to see what type of planets these the thing that the disk have. Is there any difference in their masses? So I show the distribution of the of the planetary masses in this plot, and below the cumulative distribution function. And we find that more massive planets are located in the thin disk, and these are also the iron rich. So we know very well that the stars are generally a younger population. So we could assume that as stars get more chemically enriched over time, the formation of more massive planets can be enhanced as well. Of course, we have to consider that this is a very small sample, and we have to consider detection biases that this sample suffers. These planets have been selected from the RV and the transit methods combined. But I have to say a few words about the future, that there are some missions related to the detection of exoplanets in large demographics, namely TESS, PLATO, and Gaia, and also Roman. In particular, Roman will observe planets in different galactocentric distances going into the bulge. So this will be very interesting if you want to see planets outside our neighborhood, in comparison to TESS or Kepler, for example. I wanted to point out also that this type of studies can be, we can follow up this spectroscopical, the hosts, with the few new facilities, and I want to point out the Wide Field Spectroscopic Telescope that is a proposed facility for the 2040s. So I'm assuming that the high resolution setup will be useful for this audience because they can characterize the planet hosts, especially in the very faint ones. So we can characterize them in terms of their chemistry. And Katia Biazzo and I are coordinating this working group related to planets and their environment. So if you are interested, please contact us. And I will leave you with my conclusions. Thank you.
Questions?
Very clear.
Yes, we have a question here.
Thank you so much for a very amazing talk. About the elements that are important for planets, like light elements, nitrogen, how do you measure nitrogen?
I don't. If this facility operates, it will be in 2040. So I'm not the one that is calculating the abundances. There are other people appropriate in this room. But this facility will have a high resolution spectrum of 40,000. So this will be observable. So you can measurable, so.
Yeah, but so probably from some molecules, because the nitrogen atomic line probably are not detectable in even 40,000. So probably some molecular lines, like CN lines.
CN,
maybe,
yes,
yeah.
exactly.
Thank you. Sorry.
Are there more questions? Then I use my power again. Can you go back to where you explain how you determine the parameters?
Yes.
At the beginning. Yes, here. So you fix a log-G that comes from spectroscopy, and then with that you use the evolutionary tracks to get, and the temperature to get the mass and the radius, so that you get luminosity, you have the temperature, you have the mass, and then you get log-G back.
Yes.
And then that's what you throw in again, you fix, and you redetermine.
Yes.
But don't you intrinsically expect that you're obviously going to get closer and closer to what your evolutionary tracks are telling you?
Yes, but we are chasing it, But the thing is that gravity, it's even better constrained like this, because if you see the first plot run 0, we have a problem of constraining it very well, constraining well for the cool stars. So this is the best we can do.
And how much the choice of a certain set of tracks, there are many tracks on the market, how much that choice impact is the result?
I don't know. We use the parsec isochrones. Yes.
Okay. Camilla?
Just to comment on that, the choice was given by doing a hare and hound exercise on the isochron grid with 4 different methods. So we have done that contemporary at the same time, and then in the end we decided for params. And then now we are doing the test of like trying to understand how much it converges towards the model. But at the same time, the grid has been tested with globular clusters, so you have like the results for the mass and the radii that are consistent with what has been already observed.
Question here.
Thank you, Maria, for your nice talk. Can you comment on these fast rotators? Do we have many of them, and what we can derive, what kind of abundances, if the rotation is like 20 kilometers per second?
Yes, this will be this will be a problem for the people that they will derive them. It's you can see visually that it's very difficult. So you have to you will do synthesis for sure. So you need to know the lines very well. Actually, yes, we have a lot. We have even faster rotators than these A-type stars. So it's another work that will be present. Actually, there is a poster outside, and abundances are doable for this type of stars. So impressive.
I think there are tricks that you can use to get equivalent widths for those stars, but we can talk about that.
Okay.
Okay, no more questions. Okay, let's thank Maria again. Thank you. Our next speaker is Kevin Schlafmann from Johns Hopkins University.
Great, thank you very much. So I'm going to tell you about a connection between stars, planets, and their disks that hasn't yet been touched on at this meeting. In particular, this has been a project that was substantially executed by 2 of my former junior colleagues at Johns Hopkins University, Alejandra Ross, a undergraduate alumna, and Enrique Reggiani, formerly a postdoctoral scholar at JHU. This work has been accepted for publication and is on the archive. So we've already seen diagrams like this. There is a diversity of the internal structure of the terrestrial planets in our own solar system. Earth and Venus are very similar to the extent that we can tell. Of course, we don't know very much about Venus because of its inhospitable surface. Mars is a smaller planet with potentially a smaller core, and Mercury seems potentially a little bit different. It has a larger iron core, which perhaps has something to do with a giant impact, although of course there are different ideas about that. So this has already been emphasized so far in this conference that if you want to infer the most precise properties for an exoplanet, one first needs to infer the most precise properties for its host star. And in particular, if one seeks to execute a statistical analysis, one needs to do this job in a homogeneous way that hopefully also has the capability to produce the most both accurate and precise individual stellar parameters. The reason, of course, is because we can measure transit depths from light curves using, say, precise long-term space-based photometry. The observable is the transit depth. To turn that into the thing that we seek, the planetary radius, one needs to know the stellar radius. Likewise, if we would like to infer the mass of that transiting planet, then we can measure the Doppler semi-amplitude and the eccentricity of that orbit. But to infer the mass, we need to know the mass of the star. And so again, to get the most precise and accurate planetary masses and radii, it's first necessary to infer the most precise and accurate stellar radii. So this is an example of a planetary system OWL returned to Kepler 105 b and c. So this, then, is typically what one does to interpret these hopefully precisely and accurately inferred planetary masses and radii. One puts them in a mass radius diagram like this. I've illustrated an example using the solar system terrestrial planets. Other than Mercury, they all seem like they fall on the Earth mass line. Now, what if I were to next plot a very famous terrestrial exoplanet, but that has been analyzed by multiple groups and have potentially arrived at different answers? What will it tell me about the insight into that exoplanet system? So now if I plot 7 different inferences for the exoplanet Kepler-10b, this was the first terrestrial exoplanet discovered by the Kepler Space Telescope, the insight that one would take away from the published planetary masses and radii would differ. One could infer that this planet is very close to a rocky planet. One could also infer that this planet is much closer to being a supermercury. So even amongst different groups, there's a significant dispersion. And so if one were to just go to the NASA Exoplanet Archive, download the planetary parameters, you could be subject to this effect. And it could make it difficult to study the distribution of terrestrial interior planet properties over the exoplanet population. So we have done this, as well as Vardan already showed this had been done before. There is this question about whether there's a relationship between either the iron mass fraction as Vardan defined it, or potentially the iron mass fraction here, where we're just saying the total amount of iron relative to the solar value. There's this debate, first of all, is there a relationship in the terrestrial planet sample? And how many of these things might be represented by, say, supermercury type structures versus things that are more typical like we have for the Earth? So to do this, one needs to infer accurate and precise stellar properties. We've heard a lot of discussion about this so far at this meeting. My colleagues and I, we have a slightly different take. So what we first do is we synthesize all of the observed photometry from ultraviolet to the mid-infrared. We take the Gaia parallax. We take what we know about interstellar extinction. And we fit the mist grid of stellar evolution models to those data to get an initial set of stellar parameters: effective temperature, surface gravity, metallicity, and also mass and radius. We next then go to the high-resolution stellar spectrum that has, of course, been normalized to the one-dimensional spectrum. We measure equivalent widths for iron lines and also the species of interest. And then we sample from our isochrone posterior effective temperature and surface gravity pairs, which we then impose on the spectroscopic analysis. And then we seek just to remove the trend in reduced equivalent width via varying the microturbulence to get the iron abundance. We then have a set of TF, log G, and metallicity triplets, which we then go back and refit include in the likelihood in our isochrone fit, and then we iterate this process a few times. So doing things this way allows us to get the most precise temperature values by using all of the multi-wavelength photometry, which provides very strong temperature constraints. It allows us to include the Gaia parallax to improve our surface gravity inferences. And then the solutions that we obtain, that is the TF log G metallicity pairs along with the stellar masses and radii, are guaranteed to be physically self-consistent. That is, they result from the solutions of the stellar structure equations. Then once we have these updated stellar masses and radii, we take the planetary observables, that is the transit depth, the Doppler semi-amplitude and eccentricity, with our homogeneously, accurately, and precisely inferred stellar properties to calculate updated planetary masses and radii. Once we've done that, then we can examine some of these trends that have been examined before. On the left, you see our result using the methodology we think is most robust, where we have taken our updated planetary masses and radii. We've used the Plotnikov and Valencia super-Earth code to infer the core mass fractions based upon our updated mass and radius inferences. And we find that there is a positive but not statistically significant trend between the iron mass fraction as we've defined it. And we also have done something similar, not just for our results, also for the results that Vardan published, and then also for a completely independent analysis of completely different H-band spectra from APOGEE DR17, and a completely independent spectral synthesis calculation published by John Brewer. So in all of these cases, we've taken the published stellar parameters and we've included them in our analysis approach. And the conclusion is that sometimes it appears there is a statistically significant support for this relationship in the case of the Brewer stellar parameters, but in other times there is a positive relationship, but not necessarily a statistically significant relationship. So again, at least in this exercise, it seems like there's a need for further study and more data. But there's a lot more interesting things one can do with these data. You don't need just to limit the analysis to these sorts of plots, which we've seen before. And in particular, we sought to contextualize these results in the exoplanet architecture of each of these planetary systems. So when we plot our results on these mass radius diagrams, there's two things which we found to show up very strongly. First of all, the planetary systems WASP-47 and 55 Cancri they're special in the sense that they're the two most metal-rich stars in our sample. They both have multiple giant planets orbiting just outside the orbit of the terrestrial planet that we studied in this way. And they seem to be too low density to be explained even by a pure rock composition. The other interesting thing which shows up is this Kepler-36 system, which you can see here, also here on this diagram, and then in John Brewer, also Kepler-105c. And so these are colored differently because these are planets that are currently in, or were likely formerly in, mean motion resonances. And I'll tell you why you should care about mean motion resonances in just a moment. So one of the things that was anticipated before Kepler was that the systems of small planets would be found in low-order mean motion resonances. A mean motion resonance is a situation where there are two planets that are adjacently in the exoplanet system architecture, and the outer one has an integer multiple orbital period of the inner planet, say 2 to 1, 3 to 2, something like that. And so convergent type 1 migration in parent protoplanetary disks was predicted to produce systems that were consistently in low-order mean motion resonances. Kepler went out and it made these observations, and it turned out this was not found. And so there's been a very active area of research to try and understand what is it about the parent protoplanetary disks or possibly subsequent evolution that removed these systems from the predicted resonances that were expected from their formation. So what we have found is that the planetary systems in mean motion resonances consistently have core mass fractions which are less than 0, which in this case means that they are inconsistent with pure rock composition. Alternatively, for every planetary system outside of this subpopulation in the 55 Cancri WASP-47e subpopulation I already mentioned, our entire population is fully consistent with a Earth-like core mass fraction, as you can see here, and this is independent of the spectroscopic parameter analysis approach. We find this result. We also find the result using other spectroscopic stellar parameters. We also find that these ultra-short period planets with multiple Jupiter mass companions represented by 55 Cancri E and WASP-47e have mean core mass fractions that are significantly less than what could be achieved by pure rock. And so we hypothesized that those planets were once mini-Neptunes that, due to tidally induced orbital migration, ultimately lost their envelopes due to a combination of installation and Roche-Loeb overflow. So we find that the occurrence of Mercury-type planets in our sample, there turned out to be 1 of 24. The posterior on the occurrence you can see on this diagram. This actually overlaps at the 1 sigma level with the posterior that would result from the occurrence of Mercury-type planets in our own solar system, which of course is 1 in 4. So it doesn't seem like there is a distinct class of Mercury-type planets in the galaxy. It's also been suggested, as Vardan mentioned, that there has been this proposed relationship between the internal structure, the core mass fractions of these terrestrial planets, and the age of the system. And of course, there were speculations in the articles that published this that that was the case. If you look at this diagram, it looks like maybe this is significantly related to WASP-47e and 55 Cancri E, which, as I've just argued, come from a qualitatively different formation mechanism. But there's an even better explanation than that. So transit surveys typically tend to be transit depth limited. That is, they're good at finding planets of a given radius, and that doesn't say anything about the mass. To get the mass, one needs to use Doppler measurements to identify the Doppler semi-amplitude. And that can be quite challenging for small Doppler semi-amplitudes if the star is young and active. So you can see here is a published model for how the radial velocity jitter for a solar-type star changes as a function of age. That is, it becomes less with time. And the horizontal lines indicate the Doppler semi-amplitude produced by differing core mass fractions for planets of a fixed radius, which is how these how these transit surveys are executed. So young stars, it's possible to see core mass fractions it's only possible to see the most dense planets because they produce the largest Doppler semi-amplitudes. And to see the planets with the smallest core mass fractions, one has to wait several gigayears for the star to become more cooperative. And so you don't see the low core mass fraction planets until the stars have had a chance to age and become more cooperative. So my conclusions are that the core masses of terrestrial planets increase with host star metallicity, but this effect is not a consequence of the existence of a distinct population of supermercuries. Terrestrial exoplanets in mean motion resonances have low core mass fractions, which we interpret as significant water content, which we understand to be the result of their disk-driven migration from much wider separations in their parent protoplanetary disks. That is, they formed much further from their host star than most of the planets in these samples. 55 Cancri E and WASP 47E are different because they were the cores of mini-Neptunes, and they're low density because there's lots of volatile things entrained in their interiors because they were the cores of mini-Neptunes for billions of years. And finally, these conclusions are robust to stellar parameter inference approach because we got the same answers from our approach and also from 2 independent analyses.
Questions? Here.
Okay. Have you tried to analyze a sample that is purely defined by transits and not by published measurements of the masses?
So this is entirely transit-based survey because you need a transit. All of these things were found initially by transits.
Yes, initially. But have you tried also to include planets that do not have published masses at all?
Well, we couldn't do this analysis if we didn't have published masses. That's a prerequisite to the internal structure.
So I'm a bit worried about publication bias. These are mostly at the edge of detectability. So if a group does follow-up and gets a 4 or 5 sigma detection, they publish. And if they get 2 or 3 sigmas, perhaps the attempt to do the planet disappears in some drawer and doesn't get published. So you may have a bias towards heavier measured masses just because those have been published, that the 2 sigma outliers in higher mass have been published and the others have not been published. So by going to a sample that has published masses, you may have that problem. And it's very difficult to overcome unless you have a complete knowledge about what people tried and ended up at 2 or 3 sigmas also.
Yeah, so I understand the bias, but there is nothing that we can do about that because we need a precise mass to even discuss the internal structure. Otherwise, what's the point?
Yeah. And yeah, unless you go back and find out whether the groups that have publications also have other things in their drawers. And this goes back to what I think I commented earlier. It's not so much comment towards you, but towards people who do these observations, also to publish the non-detections, because that is important for such statistical analyses, to also have those that ended up not as significant detections.
And I agree with that comment.
More questions? I use my superpower again. Some of the systems that are in resonance, they have TTVs as well.
That's right. So they have TTVs, and that's part of what allowed their masses to be inferred. They tend to be at wider separations than the rest of the planets in the sample. Not much wider.
Get the mass then.
So the mass. So in these 2 cases, the mass is from transit timing variation. So if you take the transit timing variations, you fit them with a photodynamical model, and that's what produces the masses.
Right. Their TTV masses, not RV masses.
That's right.
Okay.
So we did the same thing. We took the TTV mass. TTV inferences are, of course, similar in the mass ratio, and so we updated the mass of the star in the transit timing analysis.
Yeah. Okay. No, there is a question there.
Yeah, I was wondering, how do you know if this Kepler-36b is in a that it was formerly in a mean motion resonance? Is the system directly in a mean motion resonance, or how would you identify that it was likely in a former mean motion resonance?
So first of all, Konstantin Batygin and one of his graduate students published this heuristic based upon closeness to the period ratio. I think it was within 0.6% to being wide of the period ratio, as being those are the things that are consistent with resonance. So then also, I didn't have time to talk about this, but another one of my junior colleagues and I, we published an article where we argued that one of the reasons why we don't see things in mean motion resonance is because they've been dragged out of mean motion resonance by interactions with the tidal interactions with their host stars. So we published an observational fact that in the Kepler field, the things that are plausibly resonant are systematically younger than the multis which are not plausibly resonant. And then that work has been followed up by Fei Dai and his collaborators, who have shown that if one looks at the youngest planetary systems, the occurrence of things that are, again, plausibly resonant, it's of course almost impossible to establish if you don't have precise eccentricities that something is resonant. But for the things that are plausibly resonant, the occurrence of resonant systems in the youngest age bin, which they have is between 10 and 100 million years, is like 80%. So the combination of that inference, our inference, that it probably is the case that most things close to resonance started out in resonance and have moved away from resonance due to some process that we have ideas about, Fei has some ideas about, but it's not exactly clear what's going on. It's just that it is happening.
Thank you.
That's fine, Kevin, again. So the last speaker before the coffee break is Alexandra Ledmetz from Tartu Observatory.
Okay. Yeah, hello, my name is Alexandra Ledmetz. I'm from here. I'm hoping it will get put up soon. But today I will tell you about stellar abundance anomalies in A and F type stars and how we can explain this maybe with planetary contamination. Yes. Okay. We know there is closing gas giants, or we call them ultra-hot Jupiters, and they receive intense stellar radiation that heats up their upper atmospheres and drives their hydrodynamic escape. And this can lead to comet-like tails, as we have seen in systems such as, like previously also told, HD 209458b, WASP-12b, and KELT-9b. And those tails can also be forward tails or backwards tails. And some of the escaping gas then from the atmospheres may remain gravitationally bound within the system, raising the question of what happens to this material next. And if part of this escaping material falls back onto the star, then it can alter the stellar surface composition. And this process is called photospheric contamination. It was also mentioned yesterday, but with protoplanetary disks. And this idea was first proposed by Jura 2012, but it was further investigated by Cermin and Kama 2018. And they suggested that this could serve as an indirect way to probe planetary atmospheric composition. And they looked into this with KELT-9b in Kama et al. 2022, and they saw that there, in this example, we have the elements and then stellar abundances. And there's also elements that are with B up here shown. yes, up here is within the KELT-9b atmosphere that has been observed. And here are basically the abundances in the stellar abundances of KELT-9. And they see there is nothing like different, so it isn't happening in this case. But why did they actually look into KELT-9b? Is because they found that stellar connecting zone test limits the survival of these accreted signatures. So they found that the AF-type stars are the best. They have thin connecting zones, so the contamination can persist. They could have strong UV or EUV flux, and it can drive then a bigger evaporation rate. And then there has been shown a range of abundance peculiarities in A and F type stars. So they're a very good place to test whether these contaminations can happen. And in my point of view, I really like to look into the planetary interactions. And this study is actually preliminary, so we focus right now on 4 research questions. Under what stellar and planetary conditions can contamination occur? Which atmospheric species are most likely to escape and be accreted onto the star? And for that, I have already done an analysis, and I have a poster outside if you want to know more about it. And now the current focus is which of ultra-hot Jupiter systems are the best contamination candidates. And finally, are these imprints detectable with current or future instruments, and are detectable in UV, optical, or infrared? So I mentioned already about what I have looked into which species escape and can be accreted. So I have also a little plot here, which basically tells you the beta ratio. And the beta ratio is ratio between radiation pressure force and stellar gravity. And here is also the equation. If you want to know more what goes into it, you can ask me later. And below is the graph. And on the y-axis, there is a beta ratio. And on the x-axis is a range of stellar affected temperatures. And we also have here different kinds of molecules for each of these scenarios of debris disk, hot Jupiters, and rocky planets. And if you look into the hot Jupiter case, for example, KELT-9, then we can see that if we look up here, then we have the radiation-dominated regime. And for example, if you look for here red, this is sodium, we can see that this is in radiation-dominated regime, so it will be pushed away from the star. But if you look down below, this is gravity-dominated regime, and here we have, for example, nitrogen, and we also have oxygen that can be like pulled towards the star. And for many A-type or F-type stars, beta tends to exceed 1, and for like late F stars, heavier species can fall below unity, and these results support the working picture of this work that contamination is most likely around moderately irradiated F-type systems. And how do we actually go about to analyze? Our approach starts with identifying suitable A and F stars hosting close-in jazz science. We then compile their elemental abundances, homogeneously derived planetary parameters and stellar parameters, which is right now the current work. And then in the future, we will try to estimate the EOE flux, construct a zero-line baseline for metallicity, and then finally compare abundance ratios between high and low EUV groups to test for this contamination. So as a first step, we have defined a sample of around 30 ultra-hot Jupiters where we have defined ultra-hot Jupiters as they have equilibrium temperatures above 2000 Kelvin, and orbital separation under 0.07 astronomical units. And they are orbiting F and A type stars, which has the temperature between 6500 and 8500 Kelvin. We didn't include KELT 9 because it has already been analyzed. And yes, and this plot we show the distance compared to the stellar effective temperature. And we also have here 4 zones, you can say. And in the orange and green zone, we have these dust sublimation zones where we have refractory species can remain gaseous, so they are more likely to escape. Then in the red, we have Hill sphere, which is the stability limit for bound atmospheres. In blue, we have Roche fluid limit, which if the planet is closer to the star, then it can have a direct overflow channels. But we also have here this gray region, which is theoretically the best region for this contamination to happen. And we actually have one system here, which is pretty good. Yes, and we have already derived some of the uniformly stellar parameters, and we have here the iron over hydrogen ratio compared to the stellar temperature, effective temperature, and we can see there is a range of them. They are not very close. So it can say in like first approximation that there can be differences, and we are doing now more into going to analyze different species. Okay, and we also looked into the photospheric contamination fraction, which is a CAMSTAR framework developed by Jeremy Nakama 2018 to estimate how much planetary material could accumulate in the stellar photosphere. Here we have the stellar mass compared to the rotational velocity, and here in the colors we have the accretion fraction. It basically says if the fraction is equal to 1, then all the stellar photosphere is contaminated, and if it's equal to 0, then it's not. And we can see that, and we also have a detection limit set by in Jeremy Nakama 2018 article, and we can see that it's 10 to the minus 6. And if we see these numbers here where they range the colors, then we can see that we are actually pretty good in the detection limit. But we can't get over the challenges. We need, of course, the homogeneous abundances. We are working right now on that. Then EUV estimations, because the direct EUV data is not available for many of those stars or any of them. Then model generations and detection threshold. So next steps right now is to analyze all targets. We have right now some of them. Then try to estimate the EUV fluxes. Maybe from literature, there are something we can try. Then integrate CAMSTAR predictions to all homogeneously derived parameters, because previously I took from NASA Exoplanet Archive, so they're not homogeneously derived. And then maybe do a follow-up observations of these very likely systems with high resolution spectroscopy. So this is my summary, and I can just skip and say thank you for listening. And if you have any questions, you are welcome to ask.
Thank you, Alexander. Questions?
Just curious, what is the system in the sweet spot? It's a secret?
You can say it's a secret because, yeah, it's very preliminary, and I didn't want to bring out any systems particularly. But if you know your parameters, you can actually guess those. So.
Yeah, very, very cool. I'm wondering if there's then the complementarity, like when you could trace the atmosphere of the planet, like with James Webb or something, and then you have at the same time the contamination of the stars. Is this something that is worthwhile to do, or is it like essentially like a complementary technique where you don't need to go to like a factor 20 oversubscription of James Webb?
One idea.
Yeah. Yeah. You can ask later. I haven't much thought about still for the observational part, but I think it could be done without using the James Webb telescope. It's because if I look right now in the literature of the how much resolution you need to characterize the stellar chemical composition, then you can also do it on ground-based observatories.
Cool, thank you.
Not all of these A stars are single. Some of them have companions which are solar-like stars. Perhaps you could also check the abundance of the other component that doesn't have the planet, and then compare the abundance of the A stars relative to this companion star to see the excess more clearer.
Yeah, that is also, I think I have taken it into account, and I am planning to incorporate that also into it. So we.
A super quick question? Yes. Super quick question and super quick answer.
Just a comment on the previous question. I think what you said makes sense. JWST might not help us, but ground-based does, because we can trace the dynamics of the gas, which will be different from the rotation of the star itself. So, I agree.
Yes. Thank you.
Let's thank Alessandra again. And reconvene in 20 minutes.
to you told her, right?
It's also 45. So she should fit online around now.
Yeah.
Miguel Kama is not here, but Corinne Folsom is here. No, he's not here. Okay. His affiliation is but to attend the conference or something. Then the days.
He's not here. No.
Okay.
Yeah. He also works remotely.
Okay. Okay. It's unfortunate, but okay. Thank you.
Alex, sorry, there is something. Can I say? In the beginning of the session, can you put a QR code for voting for posters on a screen? Because people are not. We have a slide. Yeah. You can put it. You can put it now, but.
You have this slide.
Me peame Zoomi testima homseks.
Let's vote. No, I missed it. I didn't vote, yeah. I put it like I can help you. Want to see my presentation?
I sent her an email now. Did you want to check your slides? Hey, sorry. Hi. Did you want to check your slides? Or
Do I have to check your slides? Yeah, can we?
I'm not sure. Were you asking to check?
I was asking, but I said it's okay. It's a normal PDF. But yeah, no, as long as I have it. Okay. Okay, good. Thanks.
Yeah. Yes. You can use this.
Okay, so the slides I changed it with the. Okay. Ah, it's there already. Ah, okay. So that laser is on this. Thank you.
He's turning white slowly. White and white.
This is the receipt for the credit card, right? Do you also make a receipt for the dinner? And do all the investment, I mean something that say, hey, it's for the special.
We're going to have to ask the financial
Ketu, can you check if you send the email
No,
to the right
and
person?
I would have happy if they gave us the per diem, but because
She hasn't joined.
the lunch here, they say, no, we're going to earn too much money.
So where is the dinner tonight? I don't know how to go. Or is the information somewhere? I didn't check. The webpage? Isn't the webpage the information? Where is the restaurant, the dinner tonight? It's in the webpage? Ah, okay. It's last time I checked, I think it was not written and then
There's a Google Maps link as well.
Okay. Okay. It's a walking distance or?
It's like 30 minutes walk.
Okay. From here. That's good. We are all the day sitting, so
Yeah.
walking a bit is nice.
Yeah.
Thank you.
It is the same email.
She hasn't joined yet.
But I don't know why she hasn't joined.
These people are so annoying.
Otherwise, I can write to you. I can write to her that, yeah. But I mean, I can write to her that the coffee break is ending, like quite 8 minutes, 5 minutes. So the next time to try is after 2 weeks.
Then we have to wait longer. Let me check if we see this. No?
Please come in, sit down. We have a very long session ahead of us. And we all want to go to the conference dinner. So, one quick announcement. You see a QR code here. Please vote for the best poster. Now.
Can't start my talk if you don't do it.
Thank you. We begin, and we get back to disks. And our first speaker of this session is Antonio Garuffi from ENAF Bologna in Italy.
Hi everybody, please vote again. I can start my talk if you don't vote, I was told, so yeah. So this is an attempt to actually summarize 15 years of disk imaging in 15 minutes. It's going to be tough, but I'll try my best. So the first headline is here. In 15 years, we have imaged around 300 disks, okay? It's a little bit less, but we are close. How many protoplanets have we found? Much less. As some of you know, it's probably around 2. The one you see that. And I think there's a talk by Danielle later on, actually talking about PDS 70, which is sitting there. I'll try to leave you with 3 main results about this. Try to connect basically the star and the planets for this conference. But before that, I'd like to start with, remind ourselves, or, well, give you somehow the observational point of view of this slide, which you have seen many times. It's basically the long journey toward the formation of planets, starting from the ISM. That's green. And if you actually focus on the observational point of view, which is mine as an observer, we have basically the problem that the most difficult part toward the growth of the dust is actually unobservable. We don't have any significant emission from 1 meter-sized particle or 1 kilometer-sized particle, right? We can easily probe the micron-sized grain, the millimeter-sized grain, and then the planet. But we have an intermediate size, which is basically we are blind, okay? And that's the problem, because that's the most critical part. No? As we have heard from Diego today, all these processes happening. Actually, the pebble accretion is somehow the most critical one, because we aren't even sure whether it's actually the pebble accretion or some other more traditional methods, those that actually allow us to actually overcome the meter barrier. So observationally, how do we observe these different components? Focusing on the dust for this talk. Micron-sized grains are probed in micro-sized wavelengths, so in the visible or near infrared, okay? Millimeter-sized grains are probed in the millimeter. So basically, we have ALMA. Keep in mind that the fantastic results by ALMA are actually accompanied by the near-infrared direct imaging that has been done over the last 15 years, collecting actually a larger number of disks even than ALMA at high resolution, at spatial resolution. And then again, if you want to see the planets, near-infrared contrast is again one of the best way to go, because you can directly see the thermal emission from the planet, which is actually significantly emitting because it's still contracting. So this is another way to look at the disk, focusing on different components. So you clearly see the gas, and you clearly see the larger and larger grains. Keep in mind, again, with ALMA, you are sensitive to larger grains close to the midplane somehow. Maybe not really on the midplane, in the midplane, but close to the midplane. In the near-infrared, you are sensitive to micron-sized grain, but these are actually at higher altitude, right? So you can clearly see basically this structure here, which is basically the micron-sized grain are going with the gas. So somehow what we see in the near-infrared images, that's what you are going to see in the remaining 10 minutes or so, is basically the single photon from the star that gets scattered by the surface of the disk toward you. So it's a completely different process from the millimeter emission, which is basically a thermal emission from this kind of orange large grains here. Even larger, SKA in 2030, the pebbles finally. But that's another story. Let's focus on the near-infrared, which is my science. And in particular, a few years ago, in 2020, actually in 2021, we were granted the chapter to summarize what had been done from 2010 to basically 2020 at the time. It was led by Miriam Benesti, a chapter in the Protostar and Planet 7, a big conference, for those in the star formation and planet formation community, the most important conference. And I tried to, I would actually to copy-paste basically some of the abstract that we put in the chapter, where I think it's the best way to summarize it. So breakthrough progress has been made in high contrast imaging, in near-infrared contrast imaging, that's what you are seeing here. The morphological substructure are seen in basically all infrared bright disks, and are believed to be the result of disk evolution processes, and in particular, which is one of the most interesting ones, in particular regarding the interaction between disk and planets. So are all these substructure here due to planets? Maybe not. Are some of these substructure due to planets? Maybe yes, right? We believe at least some of these are due to planets, and we want to actually see how this substructure evolved throughout the disk evolution, because that would tell us a lot about the planet formation. So that's one of the best strategies to actually study the planet formation. We don't have many protoplanets detected, so this is one of the best ways for now is to study the disk evolution. And this is basically what has been done numerically. This is a slide from the chapter by Miriam, where you could clearly see that the latest generation instrument, in particular as European, the VLT sphere in Chile, has allowed us to basically grow the number of individual disks detected and characterized by a large number here until we get to 130 in 2023. And then some colleagues actually asked me to update this slide because, you know, by now it's 2025, almost 26. So I updated, I kept the same scale now for your reference so that you can clearly see that the last bar is actually getting to the roof of our library here. So that's very, very high. It's actually increasing quite well now. So we have a very large number of objects, 300 disks. What are we going to do with these amazing images that we have? So one thing is to really try to relate all these properties, so the presence of, for example, spirals, rings, cavities, shadows, and so on, with other properties, for example, the stellar properties. No? You want to know your star, right, in this conference, so you want to relate these properties with your star, but also with the environment. No? So, for example, the presence of UV field and so on, or with the disk properties as well, the disk mass, the disk height, for example, the disk extent, and so on. So try to relate all this. Of course, we have to characterize the star. So once again, know your star, know your disk in this case, or vice versa. So you can see this is the whole sample, actually. This is the latest paper that we are trying to publish soon, where you can see the different forming regions. No? We have a very large number of sources from Taurus, from Chameleon, from Orion, from Upper Scope, and nearby regions. And the good thing is that actually the individual age estimation works pretty okay, I would say. Many people are skeptical about that, legitimately. But overall, I think when you flag some particular cases for many reasons, actually, I'm not going too much into the detail, then we are left actually with the age that we expect from that region. So my point of view is that we can trust individual age more than what some people believe, but that's of course to be discussed. So what do we do now with all this sample and all these ages and stellar mass that we have? One thing is, of course, related. The first thing is the cavity. These cavities were the first substructure discovered because it's easiest somehow to be imaged, and that's the inner part of a disk could be simply devoid of dust or somehow depleted of dust and gas, as you can see in the example. PDS-70, for example, is one of the examples here. There are many more. And one thing to keep in mind is that, first of all, this is the near-infrared brightness, so we can simply measure our brightness here from the image in relation with the star, actually, because it's scattered light again, no? And you can see basically when the old disk and the old disk exist, we have a number of disks. If we believe the age, these Peter Pan disks are actually indeed 15 mega-year-old, so they do exist, according to us at least. And all these disks are bright, okay? We don't have very old disks that are actually faint, they are all bright. So the possible explanation is that all of the old disks have a cavity. If you have a cavity, then a photon is free to travel to the outer part of the disk and be directly illuminated, and so it's bright. If you have the inner disk, so no cavity, then basically the outer part of the disk is self-shadowed. This is why if you have a cavity, the disk is bright. And the old disk, they all have a cavity. As you can see here, we have a very large fraction of old disks with a cavity. So my speculation about this, so this is about 5–10% of the disk that can make it to live so long because they can actually open a cavity. So from the planet community, what can you think of? Is this not maybe the fraction of those stars that will form a giant planet? It's maybe even lower than that, according to some of you. But, you know, the idea is that we are really probing the disk that can actually form giant planets, 5–10%, at least some of this. And the good thing is that if you can live so long, then you have more time to form planets, but also more time to migrate planets, no, in a sense. So whether this would be hot Jupiters, I of course have no idea. But keep in mind that living 15 mega-year is much better than living 3 mega-year if you want to form a planet and migrate it toward the star. Ambient material, that's the new, it's the fourth component, I think, star, planet, disk, but then we have to also add the environment, and I think Madelise is going to talk about this in particular, maybe even Karina, I don't know, but there's certainly a shift of paradigm in our community toward not considering disk isolated box anymore, but definitely in interaction with environment. 20% of the disks, 20% are in interaction with environment. At the moment, it means that maybe there have been interaction with the environment 1 mega-year ago. So everything says, actually everything tells us that most of the disks are in interaction with the environment throughout their lives. So there's something to keep in mind when we look at the mass, for example, available for planet formation. That's the mass at that time. But we have to consider we have additional mass coming toward the planet. Fresh material, the chemistry is also changing, right? The chemistry of this incoming streamer would be different from the chemistry here. So know your star, know your environment, know your planets probably, because this is going to change during the planet formation. And this is probably the most interesting plot that I want to show you about the interaction with the environment. You basically have on the y-axis the near-infrared excess from the ACD, and that's mainly, telling you about the very hot dust close to the star, right, the 1 AU or so, where you will have your hot Jupiters. And on the x-axis, you actually have stellar variability, so basically the amplitude of the light curve that you have from your star. You can see they kind of correlate, but most interesting, all the sources that we see being in interaction with the environment from the picture that I showed you before, most of these are actually sitting here. So there's a correlation between the near-infrared excess, so something at 1 AU, close to the star, with something that is like a 300 AU, 500 AU, right, the ambient emission. And the same for the stellar variability. So we are putting together something at 500 AU and 1 AU, right? All in all, ambient material, the presence of these spirals, look at the crosses here, they are clearly segregated from the rings. Rings in disk and spirals in disk are clearly separated by this kind of random 2 parameters that have nothing to do with spirals and rings, right? So this is surprising. So ambient material, these spirals, shadows, near-infrared excess, accretion rate, and stellar variability are all connected. So what is that? This is the interpretation I have, is that in some cases we have a medium which is accreting the disk, altering the disk morphology in a way to form spirals, for example. So in this scenario that I'm proposing, we are proposing, spirals would be mainly formed by the perturbation from the ambient material down to the star and then accreting onto the star, providing stellar variability and so on. So it's all connected. But once again, the star is directly related to the environment, okay? So the way planets will form depends on the environment. The star knows about the outer disk, this is work by Mikkel Kama that we also follow up about this. Finally, the last thing I want to tell you is about the location of this disk in their regions. Okay, we heard a lot, about planet formation depends on where in the galaxy, but also maybe where in the cloud. This is Taurus. This is Taurus, so you can see that the green points here, the bright disks, are actually segregated with respect to the faint disks. So it seems that there is a segregation of disk morphologies even within the cloud, right? So maybe the planet formation occurred in a different way. And this is another attempt. This is upper scope, but very similar results. The brightest disks are in the north and to the east. And these are typically faint. So somehow the disk evolution, the planet formation depends on where in the clouds this is actually happening. We're doing the same in Ophiuchus, we're doing the same in Lupus, we're doing the same in Corona Australis, we're doing the same in Chameleon, we're doing the same in Rai. It's just to brag a little bit, but also more importantly to say that we are definitely looking at the full sample now to try to understand how this actually occurs. So take-home messages, the 3 results that I mentioned in the beginning. Near-infrared imaging of 300 disks over 10 years enabled the demographics. First, probably we have the family of disks, 5–10% to be discussed, that can actually form relatively massive planets, right? That can keep actually the dust there for 10–50 mega a year. The disk morphologies are definitely driven by the star location in the clouds. So not only, bulge or thick disk, a thin disk, but maybe even only where in the cloud the planet formation occurs. And finally, the late accretion from the environment alters the disk traction, provides fresh material for planet formation, and maybe impact the star too. So again, once again, know your star, know your environment, know your planet. And with this, I conclude. Thank you very much.
We have time for one quick question there. And the quick answer, please.
Okay.
Thank you for this fantastic overview. I have the question, so if you say alt-right disks with a cavity do perhaps host the giant planets, where are the giant planets then? Because we don't see them.
Yes, and then the endeavor is to find these planets, right? So the big question is, why are we not finding these planets?
Yes.
And that's a long answer that I cannot give you now, but somehow we are confident that in the future we will be finding these planets.
Okay.
Super quick.
Thank you for the fantastic talk. So I had a question about those cavities. I mean, when you're mentioning, for instance, DM tau, we know that the DM tau cavity is around 70 AU. Do you think it's a giant planet that's carving this cavity, or more like other effects like photoevaporation or even accretion problem happening in there?
If you ask me, it's a planet. So spirals are not due to planets, cavities are, my interpretation.
Okay, and it might be that we don't find the planet because of some projection effect, or?
Or they are very close to the star, or they are still kind of embedded, and therefore we are using the wrong wavelength, like a sphere, which is still affected by the wavelength, and so the extinction is maybe much larger than we think.
Okay, thank you so much.
Was I short enough? Yeah.
Let's thank Antonio again.
Thank you.
Next speaker is Karina Mauko from ESO.
So, hello, everyone. First of all, I want to thank the organizer for giving me the opportunity to talk today on this talk. It's been really interesting. And I will be talking about protoplanetary disks, but affected by external photooperation. So for those who doesn't know me, I'm Karina Mauko. I'm a postdoc at ESO in Garching, Germany. Just for a few more weeks, actually, because I'm then going back to Mexico for a tenure track position there. So that's where I'm going to be. If you want to know me or visit me, I will be happy to do that. But my research is, again, in protoplanetary disks, but with the specific focus of the effect of massive stars in the evolution of protoplanetary disks. And I do that from an observational perspective. So you have seen this plot before. We know that the stars form from the collapse of molecular clouds, but this very simple approach always assumes that these are formed in isolation. But we know that this is not entirely true. We know that most of the stars, actually, in most of the planets, are formed in cluster environments, so with massive stars that can affect the evolution of protoplanetary disks. So we know that these massive stars can affect the evolution of this by dispersing this disk from the upside in. And that will affect, of course, the mass of the disk, the radii of the disk, and also the properties that can planets form there or not. So it's very important to understand this process and to characterize it, because we even know or believe that our sun actually was formed in one of these clusters with massive stars. So if we want to understand the formation of the solar system, we need to take into account this process. So we wanted to do this, testing this process, and for that we choose this John cluster in Orion, which is the Sigma Orionis cluster. You can see here that it's very close to one of the belt stars in the constellation of Orion. And this is very interesting cluster because at the center it has this multiple massive OB system dominated by this O9.5 star that we believe that might be producing this external photooperation in the disks that are close by. And for that, we did the first larger scale survey of the cluster by using interferometric observations with ALMA and also spectroscopy. So the first work was published in 2023, and for that we use a sample of 50 stars observed with X-shooter. You can see here the distribution in the plane of the sky of our sources, and you can see that we prove different radial, at least projected separations from the massive system, which is in the center here, the star, and you can see also in color the strength of the FUV field that we usually parameterize it by this G0 parameter here. And this is just the strength of the FUV field in the ISM. So you can see for the stars that are very close to the massive system, to Sigma Ori, the bluish points here, it can have or be exposed to FUV fields as high as 10 to the 5 the FUV field of the ISM. So that is very high, and we believe that this might affect the evolution of these disks. So we use X-shooter to characterize the stars and also the accretion, and we use ALMA to estimate the disk dose mass. So here you can see the disk dose mass distribution as a function of projected separation from the massive system. And what you can see is that we found this increasing trend. So sources that are farther away from the massive systems are also higher in dose mass. But the sources that are very close, so inside 0.5 parsecs from sigma Ori, they are very low in dose mass. And that, we believe, is a sign of external photooperation because these are being dispersed faster than the ones that are further out because of the influence of this massive star. And since we have EXOHOST and also ALMA, we can estimate the disk lifetime, so we can get the masses from ALMA and the mass accretion rate from EXOHOST, as Lara was saying in the first day using Frappé. And what we found is that, in average, the disk lifetime, which is the key parameter if you want to understand the evolution of protoplanetary disks, is around 1 million years for the cluster. But we know that this cluster is usually, estimated age is between 3 and 5 million years. So we find that these lifetimes are very short, and it's even more striking in the inner parts, where we have this lifetime less than 1 million years. So the first results that we found in this paper is that these small dose masses, and specifically here, the most irradiated stars, and also these shorter disk lifetimes, are suggesting that this OB massive system is affecting the disk by externally photooperating them. But of course, if we want to study a little bit more this process, we need to characterize the winds that this process produces, because the disks are being dispersed by these winds. And for that, we go and we study the optical forbidden lines and also the line ratios. So that's what we did next in this paper published early this year. We had a subsample of almost 20 stars with high-resolution observations taken with Mike, the Mike spectrographers in Las Campanas Observatory, and we basically focus on 3 optical forbidden lines, so the oxygen 1, the nitrogen 2, and the sulfur 2 lines for these sources, and we fit the line profiles with multiple Gaussian components, as you can see here in different colors. And we did that with the StarMelt package, which is a package that was created by a former postdoc at ESO, Justin Campbell-White, and it's a very good package if you need to fit emission lines and also correct by telluric contamination, so I really recommend that. So we know that the high velocity component, which is the green components here, which are peaking at peak velocities larger than 40 kilometers per second, are related with the microjets or the jets from the star. But I wanted to focus on the low velocity component, which is the one that is related to photooperating winds. So the peak velocities of these lines should be around the systemic velocity of the star, so 0 here. And you see that sometimes it is a single component, but sometimes it has multiple components as well, for instance here. And we have a broad component, which is the red component here, is mainly thought that it's coming from the inner part, so MHD winds probably because you have wider winds. But the narrow component here is probably related to the photooperating wind because it's generated in the surface of the disk and it's a slow wind. So I focus on the low velocity component. So since we have the fitting of the lines, we can start getting characteristics of these lines. First, we focus on the oxygen 1, and we got here the luminosity of the oxygen 1, again, as a function of the FUV field strength, which is similar to the projected separation. So in this case, the stars that are most irradiated are here on the right of this plot. And what you can see here is that we also compare with models of external photooperation for this line. And you can see that for the most irradiated sources, these are consistent, the luminosities, as consistent with the models of external photooperation. But once we are getting farther away from sigma Ori, we do not get the luminosities expected for external photooperation. Actually, you can see that the distribution of the luminosity is basically constant, so independent of the FUV field. And if you compare with the luminosity in low mass star forming regions, so regions where do not have any OB massive stars, so no external photooperation happening there, we see that the ranges of the luminosities are the same. So this, what it's telling us is that the oxygen 1 line, it is produced externally because we also see it in droplets in Orion, but it's also contaminated by internal photooperation. So you cannot really study external photooperation only using this line. And for that, we have to go with line ratios. So for that, we estimated the line ratio using these 2 lines, so the nitrogen 2 and the sulfur 2 lines, which are more highly ionized species. And here I show you the ratio of the nitrogen 2 to the sulfur 2, as, again, as a function of the projected separation. And what we expect if external photooperation is happening here, first is to have a trend with projected separation, but also we expect higher values than regions that are low mass stars. So this is what we found. Here are more or less the range of values for Taurus, so not irradiated disks. And you can see that our sources are consistent with higher ratios, and also we can even see a trend more or less with the distance from the massive stars. So these are the most irradiated regions. But of course, we need more data because we are only constraining here by upper limits. But you can see that these particular lines are very bright in Proplitz, and you're going to see more about this ratio in the next talk of Marilise. She's going to even show this more strikingly with the Orion Proplitz. But the conclusion that we have from this paper is that this particular line ratio seems to be a very good observational diagnostic to characterize it and to identify external photooperation only, independently from the internal photooperation, which is something that we want because we want to study planet formation and star formation in more representative environments. So we have to go to even more massive regions where you cannot really resolve the Proplitz. So you're going to have only these integrated fluxes and ratios. So that is a very good thing that we found in this paper. And lastly, we also find a puzzling result in Sigma Orionis. So if you go and see again the distribution of the dust masses that I showed before, but now you focus on the more massive stars compared to the lowest mass star in the cluster, so less than 0.4 solar masses, you can see here that the more massive stars close to Sigma Ori, so the most irradiated ones, actually have more lower dose masses than the less massive stars at these similar projected separations. And that is puzzling because we always assume that external photooperation is more effective in low mass stars because of the lower gravitational potential. So in this case, that is something that we found in Sigma Orionis, and we have to try to explain this. But I think one direction that we can look forward to try to explain this is to find the relation between the disk radii and the stellar mass, because we know that these two parameters are correlated. And for that, I think that the population studies of disks in low mass star forming regions where no irradiation is happening can get very handy to try to understand this by comparing this with more massive regions. And that is where population studies like the one of DECO, which is an ALMA large program, comes in. We are targeting 80 disks in 4 different star-forming regions, like listed here. And we're tackling the very typical disks. So that is a very good survey to compare with. And my contribution in this large program is the characterization of the dose continuum. So for that, I'm fitting the visibilities of the ALMA observations of all these sources. I'm getting the geometry of the disk and also the disk radii. So here I show you a preliminary result of the disk radii as a function of the stellar mass for the 80 sources that we have in DECO. And you can see that the stellar radii goes as the square root of the stellar mass. And if we want to study external photooperation, then we have to focus on the gravitational radius, which is the radius defined beyond which the material is unbound, so you can disperse very rapidly the disks. And we compare these two radii, this radii and the gravitational radius for the DECO sample, you see that this ratio is larger than 1, which is something that you expect for no irradiating regions. So it's very interesting to try to compare this with Sigma Orionis. So unfortunately, Orion is far away. We don't have high resolution observations for most of the sources, but we have this paper recently last year where they observed 8 sources with high resolution. So if we take their radii, the dose radii, and we compare that relationship with Sigma Orionis, you can see that the relationship is stepper. Of course, we have uncertainties and everything, but you have a more stepper relationship. And if you compare the disk radii with the gravitational radius, then this ratio is less than 1. And that's exactly what you expect if external photooperation is happening. Of course, we need more observations for the most irradiated sources in Sigma Orionis and also for the lower mass star to try to understand what we found, but that is something that we can do in the future. So I leave you with my conclusions, and I'm very happy to take any questions. Thank you.
Questions? There.
Hi, thank you for the nice talk. I was wondering, do you know how old the massive stars are compared to the low mass star forming cluster? So like, is it a situation where these low mass stars have been subjected to the external photoevaporation for their whole life, or have they kind of like moved into position afterwards?
Yeah, that is a very good question. I didn't talk about it because of time, but there was this super recent paper just a couple of weeks back of Gavin Coleman And what they found is that probably this particular cluster is, I mean, Sigma Orionis, the massive OV system, is a stellar flyby. So it's actually just going through Sigma Orionis right now, and that's why we observe these indications of external photo operation. So in that regard, what I can tell is that this massive star is probably like 1 million years or so. That's what they put on the paper. And it's just entering the cluster right now. So yeah, it's definitely younger than the rest of the population.
Okay, thank you.
Yep.
Let's thank Karina. Super fast as well. Okay, let's thank Karina again. Congratulations on your tenure track. Next speaker is Marilise Aro, also from ESO.
All right. Yes, hi everyone. I'm Marilise, and I'm at the end of my PhD, which I have carried out together with Carlo Manara and Karina Mauko. And I'm grateful to the organizers for hosting such a lovely conference and giving me the opportunity to return to Tartu, where no one is confused by the double I in my name. And my talk is focusing on observations with MUSE. And here, to start out, is a plot of the distribution of UV luminosities of star-forming regions as a function of the number of member stars. And this is just a visualization to what Karina already described as the motivation for observing external photo-operative winds, as these environments are the birthplaces of the majority of stars and planets, and also likely the solar system. But we have talked about different types of photo operation today, so this is again a plot to just make it very clear that in low UV environments, the dominant wind is the internal one, starting from the central star. And in external photo operation, there is, in addition, the effect of the massive stars. And these massive stars then lead to externally irradiated disks, which we call proplyds. And in addition to the other presentations today, which already described the mechanism behind proplyds, here we have a cartoon showing the structure of the proplyds. And you can notice here that the low mass star in the center of the disk is located in the center of these systems, which are mostly clouds of ionized gas. The proplyds allow us to study how the environment affects the evolution of disks and their ability to form the planets, and they're observed in various forbidden emission lines. But the same applies to internal winds as well, which also lead to these kind of emission lines. So the question arises, which lines or line ratios allow us to disentangle these two effects? The first proplyds were discovered in the Orion Nebula cluster with the Hubble Space Telescope. And here you can see a selection of a few targets that were presented with Hubble observations. Now, here we have the same targets as observed with MUSE in the narrow field mode. So MUSE is an integral field spectrograph. And compared to Hubble, we are now probing the entire optical wavelength range, well, close to. And this gives us this gallery of forbidden emission lines. The novel part of this dataset really is that we can now spatially distinguish different parts of these systems. And you can see here the ionization front of the proplyd, the disk, and the tail. So we can really pinpoint where does each emission arise from inside the system. In our sample, we have observed 12 proplyds in the ONC, which you can see with the insets here in this plot. And they are located at different distances from the main UV source, that is θ1 or C in here. And we first presented a study based on, or focusing mostly on the ionization front radii, which is illustrated in here. And this is a very useful parameter. So, for example, we were able to study the stratification of the ionization, which I presented already in the cartoon in the beginning, where we have the neutral flow starting from close to the disk and the more highly ionized flow being further from the disk and closer to the UV source. And this is very useful as an input for models which describe the behavior and the structure of the proplyds. And also we studied different correlations, for example, the increase of these radii as a function of the projected separation. And so the radii are larger in a larger projected separation as expected. And we also were able to empirically derive the mass loss rate of proplyds thanks to this parameter, which is very important in the evolution of proplyds. And when we combine these observations with ALMA data, which gives us the disk mass, we're able to derive the lifetime of these objects. And here you can see the mass loss rate of the proplyds on the y-axis and the disk mass from ALMA on the x-axis. And the lifetimes of these objects are extremely brief, which also makes them very fascinating to study. Next, we focused instead on the disk. Now, we have already covered a lot of studies of disks with ALMA, of course, but what about MUSE? We detected a neutral forbidden emission line of carbon at 8727 angstroms, and this is detected in each of the proplyds in our sample. To study this emission line more in detail, we again used an overlap with ALMA, which is presented here for one target in the color map. So you can see the disk dust emission there. And I also compared the carbon 1 line with 2 oxygen lines that are known to be emitted from near the disk. So this allows us to see where do the different emission lines lie with respect to the disk. And you can see here that, for example, the oxygen 1 lines are coinciding with the disk. So you can see them in here. And the oxygen 1 6300 line also coincides with the ionization front. However, when we look into the carbon 1 emission, it coincides with the disk most clearly. And now you can see that we have added a new tracer to the study of proplyds, as this one isolates really the emission from around the disk without no contamination from other parts. And these oxygen 1 lines that I mentioned are very common in low UV environments due to the internal photoevaporation. And we looked into whether this is, what is the case for the C1 line. So we carried out this X-shooter test where we saw whether the carbon 1 line arises in the spectrum, is detected in the spectra there. And there was only one tentative detection out of 77 spectra. So the carbon 1 line really does arise mainly in the high UV environment. And this empirically matches with the model predictions presented by Koikoetxea last year, which, and they reported that this line is emitted via FUV pumping, so we do need this external irradiation for the line to be emitted. And this makes it a great signature for this process. Now, coming to the latest project, the motivation was, in addition to disentangle these internal and external winds, via this time line ratios, so which Karina already mentioned. And this is important. It's important to get additional tracers, especially in the case when we move into faraway regions where we can't necessarily resolve the structure and the shape of the proplyd. And for example, when we need to rely just on the spectra, it's good to also look into the line ratios. And another question that motivated the latest project was whether we can use MUSE data to derive the physical properties of the proplyds. And for this study, I carried out further data analysis, which I will skip here because I'm running a bit short of time, but it included extinction correction and background subtraction. And in here, I am plotting two different ratios. I'm plotting the data points as a function of the UV field strength. So here we have the ratio values for 3 different regions, and therefore 3 different UV field strengths. We have the sigma Orionis targets in pink and the ONC targets in blue. And in this case, I integrated the emission from across all of the proplit. And we can see that for the case of O1 6300 and S2 ratio, the ratios are spread kind of all over this parameter space. But when it comes to the ratio of N2 to S2, we can see that each region is covering their own space in this plot, with the ONC targets really standing out here with the highest ratios. And this makes it observationally another very promising tracer of, or not even just promising, but very useful tracer of external photo operation. And the line ratios are also extremely useful as the diagnostics of electron densities and temperatures. And below I am plotting these diagnostic contour plots showing the temperature and density and the ratios that they lead to. And I measured the ratios from MUSE, and I just plotted examples of free targets to see where the ratios of measured from MUSE lie in these theoretical plots. And this helps us to approximately constrain the densities for the proplets. And for example, we can also see that for the largest proplet, the density is lowest, which we do expect. Now, I leave the conclusions here on this slide, and I wanted to show the perks of being based at ESO, which is the Science Communication Department, who made this incredible animation of a MUSE data cube, which really describes the power of the integral field spectroscopy. And I also left a QR code with the link to my papers, and I wanted to say that this is actually my last talk as a PhD student, and I will be defending my PhD in 11 days. I will continue after ESO at Imperial College London, working with James Owen. And yeah, I'm looking forward for your questions. Thank you.
Questions?
I can play the illustration again if I distracted you too much with my talk.
No, then I'll ask you a question. Can you, so there are regions where there are no known massive stars in the same place where the disks are found, but there may be massive stars around that one can trace back where they came from. They may have been ejected.
That's true.
Is there any of such cases?
Not that I know of. I've never heard about this before.
That could allow one to study what happens after the star is gone, essentially. Because the star was there, and it's not there anymore since a certain amount of time, and we know how much time that is, because we know the distance.
I haven't really heard about this kind of a disk, like the system migration, because do you mean that the disk has kind of left?
No. The massive star has left the
other way around.
The birth environment.
Okay. Mm-hmm. I will have to think about it. Well, we can discuss after the talk, but yeah, I'm not entirely sure I understood the point. Yeah.
Well, massive stars tend to get ejected easily from the cluster where they're born. There are runaway stars and things like that.
That's true. But no, I've never really heard about this before. Yeah, okay. This kind of perspective. That's interesting, yeah. Okay.
All right, let's thank Marie-Lise again.
Thanks.
Next speaker is Daniel Daza-Valdebenito from University of Copenhagen.
Hi everyone, I'm Daniel Daza-Valdebenito. Thanks for giving me the chance to present my work. I'm a PhD student at the University of Copenhagen, and I will present my master project on PDS-70 under the supervision of Philip Weber, Simon Casasus, and Troels Haugboot. So I would like to start by showing this beautiful sample of transitional disk or protoplanetary disk with gaps observed with ALMA. As you can see, many of these disks present some substructures, and I highlight here my beloved PDS-70 because this protoplanetary disk presents a gap, a shoulder, spiral arm, and a vortex. Before to show the models, I want to go to briefly under the concept of planet-disk interaction, how we can form these substructures. So first, I want to address the vortices. Vortices are formed in the gas and act as dust trap, preventing the radial drift. Vortices are formed when through the Rossby wave instability, and which occurs when you have a steep gradient in the gas density, so then you get a minimum in the gas velocity field. You can observe them as emission clamps, or you can study them using the potential vorticity, the vortensity, which is the curve of the velocity of the gas over the density. Then the other ones are gaps and shoulder. In the context of planet-disk interactions, gaps are formed through when you have an embedded massive planet, and this planet exerts torques, pushing the gas outwards, creating a ring. And if this density profile is slightly inclined, as in PDS-70, you get some dust segregation as a consequence of drag forces. So then the small dust between nanometers to micrometer follow the the gas profile, and the large dust, millimeter to centimeters, accumulate in the pressure bump. So then you have this kind of shoulder shape. And also, if in the observations in PDS-70, we observe this shoulder as an inner ring inside the main ring. Now, keep going with PDS-70. It has drawn considerable attention because it remains the only protoplanetary disk with 2 protoplanets detected through direct imaging. Sorry if I mistake with current protoplanets. But here I have the PDS-70b, we observe detect with the sphere, and PDS-70b and C at the right, observe with the H-alpha emission map. Now the motivation for this project are these 4 ALMA observations, band 3, band 4, and band 7, and band 9. And as we know that PDS-70 has 2 protoplanets, we want to model through multi-wavelength aerodynamical and relative transfer simulation if we can reproduce the substructure in PDS-70 through planet-disk interactions. So very quickly about the hydrodynamical simulations, we use a standard profile from previous models, and also we use the code Fargo 3D, but we run 2D simulations. And for the disk parameters, I want to claim that we are using 10 times the mass of the gas compared to previous models. And also we have these parameters with a C sub-index, which represent parameters that we derive from proper observations. And also we use a viscosity of 10 at -3. About dust, we use 4 sizes of dust from 10 micrometers, 100 micrometers, 1 millimeter, and 1 centimeter. We use a number density of 3.5, which comes from the IMF, and we add the dust as concentric rings. And also we have planet accretion in Fargo 3D, which is not native in the code, but I want to point briefly that we use the Hill radius to accrete material, and between the 90% to the 100% of the Hill radius, we don't accrete this material to create an artificial CPD. Now going with the benchmark of the hydrodynamical simulation, and very quickly, and we obtain the expected 2-to-1 mean motion resonance, and also both planets migrate inwards and remain with a moderate eccentricity. For the benchmark in the planet mass, we have masses between the range, the observational range, which is 5 to 11 Jupiter masses, but our accretion rates are overestimated by a factor of 10 to 100 because we are using higher masses. In the case of the surface density distribution for dust, we can see that in small dust, we have a leak into the gap, and also a spiral shape in the 0.1 millimeter dust that connect the disk with the outer planet, and in the large dust, we have an effective dust trapping. Finally, in the radial profiles, I just want to claim that we have a wide gap of 45 AU created by the planets, and the dust is effectively segregated. We obtain the shoulder. Then, for the radiative transfer setup, what we do here is using radium C3D. We add a new grain size of 1 micrometer to create an inner disk in this protoplanetary disk, and also to add a gas dynamic into the images. We extend our simulation from 2D to 3D, and we add D-sharp compositions with Optool, and the process is calculate the temperature. With this, we calculate the images of the radiation fields, and then we convolve with the observational beams to create our final images. In these results of the synthetic images, we can compare the observations with the simulations. First, we can note that we can create a CPD in band 7 and band 9. Band 7 is very great. In band 9, it's very bad, because we don't observe this CPD in the observations. And I refer the paper of my classmate, Oriana Dominguez, if you are wondering why we don't observe this CPD. But we can conclude that an isothermal approximation for band 9 is not very good. We can also get the shoulder, which is quite great, and with the intensity, but for the ring, we overestimate the intensity because we have a lot of dust and mass in the ring. We also, we don't get the vortex in the simulation. However, using a viscosity of 10 at -3 is very good to create a qualitative comparison of the shoulder in the disk. If we go further with the analysis of the synthetic images, we can check the radial profiles. And here I want to focus on the band 9 because we see a double peak, which is very interesting. And this double peak means that we are tracing a temperature structure and a density structure. The temperature structure is because as we have a very big gap, the small dust is directly irradiated by the star, so it's very hot, and we have this peak in the band 9 that traces the small dust. But then we have the second peak that traces the density and the density of the ring, which is normal in disk. In band 7, band 4, and band 3, we can see the shoulder in our simulations and observations. However, we see a less present shoulder in simulations because, again, we have a lot of dust in the ring. Okay, but at this moment, it's very nice that we have the shoulder, what happened with the vortex. And it's very nice that we can recreate the vortex if we decrease the viscosity to 10 at -4 to create a steeper gradient in the surface density. And we could create this, only change this parameter, but the problem is when we go with the radiative transfer images, we see that in the millimetric images it's very good. We obtain the vortex with the disk, but then band 7 and band 9 are completely a mess and overestimate the ring intensity a lot, and also we lost the shoulder. So at this moment, we have the shoulder with a given viscosity and the vortex with another viscosity. What we can do, and the idea comes from the temperature. So if we look at the temperature of the disk of our fiducial model, we can see that we follow a power law in the black line, which comes from the Fargo 3D and the hydro. But then if we look at the temperature of all the system from radium C, from the radiative transfer, we note that we have like a tangential profile instead of a power law. So we have a very hot inner part of the disk, thank you, and very cold outer part of the disk. So what we do is take all this profile and put in the hydro, because it's very difficult to create a variable alpha in the hydro, but the viscosity is proportional to the temperature, and we can do the same and mimic the process. And we try this, and we test this idea and work really well. So in this new model, it's all the same. And we can now test the temperature, and now the profile from the hydro is the profile temperature, the tangential profile temperature, so it's working good. Also, if we look at the dust segregation and the shoulder, also we can see that it's very good. We have a better segregation than before, but in this case, we decrease the mass of the gas to archival values, and here we can see that as we have less mass, the stock number is bigger, and the large particles suffer radial drift. But at least we have the shoulder, right? Then if we look at the vortex in the same setup, we can see that we can obtain the shoulder at the same time, which is very good. This is what I want to do like since the last year. I was very happy when I get both. But it's very faint, and that's why this vortex cannot prevent the radial drift of the system. But we have both. And as nothing is perfect in astronomy, if we go to the radiative transfer, as we decrease a lot the gas surface density, we decrease the intensity of the disk. So we don't get the same disk, even if we have both structures here. And then what we can do is something, it's like cheat a bit, and increase manually without post-processing the dust masses for each species. And what we can obtain is, again, a very good images with both substructures with similar intensities. But the problem here now it's like our disk is very, very cold. So as it's very cold, the shoulder it's not completely irradiate, and we don't have the emission from the shoulder that we need to get. So that's my project. I leave you with my conclusions. I'm really happy to take any questions you may have. Thank you.
Thank you. Questions? No questions? Curiosity. Did you have problems having the model converging?
Yes, mainly something that I realized, it's like I was using D# for the composition of dust. D# is not very good in PDF70, so it's better some calculations from Ricci 2010. Then I tried this, and the problem was I had problem with the millimetric intensities, then I have problem with the submillimetric intensities with Ricci. So I think that is the main problem with the conversions, the dust composition on PDF70. So I'm really happy if anyone knows about any paper, any recent paper about the disk composition, the dust composition of PDF70, or I encourage you to try to elucidate the composition of this system, because it seems very interesting to study. Yeah. Thank you so much.
Daniel again. The next speaker is Timi Hantran, I hope I pronounced it correctly, from the Center for Astrophysics Research in Lyon. No, they have to. I do that? Sorry. No, it will come automatically. They have to do that.
Oh, sorry. So, hello everyone. My name is Han. I'm a PhD student from Lyon. Today, my talk will be about direct imaging of a particular system, which is HD 142527. Together with PDS70, these are the two systems that have been observed a lot in scatter light. as you can see in the first talk of this session. So let's get started. First of all, I would like to note that some of my slides contain unsubmitted results, so thank you for not sharing them out of the conference. So first of all, HD 142527 is a Herbig F-type star at a distance of 159 parsec. It has a very young age and medium mass. The system has been well studied due to its particular components and structure, and it has multiple hints of planet formation. So here I'm showing you some of the latest imaging results in scatter light using simple IFS and ERDIS, the three subsystems of E-ELT sphere. And I also use data from these three subsystems. So as you can see, the most striking component of the system would be the outer disk at a distance of 130 AU. It has been seen with numerous spirals and shadows. These two shadows are attributed to an inner planet extending up to 30 AU. There is a very large cavity up to 100 AU in the system, and it has also a confirmed M-type companion B that is located very close to the star. So as you can see, of a distance of almost 160 parsec, the angular separation between B and the star is very close. As you can see here, it's around 0.06 arcseconds, so sometimes it's very challenging to directly image B. So B had been believed to carve the large-scale structure of the system, creating this very large cavity and the outer disk with all the spirals. However, with the latest astrometry monitor over around a decade, the orbit of B has been very well constrained, and the authors say that with this very compact orbit, B cannot be solely responsible for the large-scale structure of the system. So interested in looking if there are unseen features or undetected planets that can help us understand the structure and the dynamics of the system, we want to look closer into the inner region of the system, and to do that we use PACO and REX-PACO, the two new post-processing algorithms that have been developed in our lab by our colleagues. So PACO and REX-PACO have been proved to be able to push the sensitivity of imaging systems so that we can have detections of point source objects and reconstruction of extended objects with high reliability, and they are ideal. These two algorithms are ideal in our case because we want to look very close to the star where the noise dominates. Here I'm showing you the reconstruction maps of all the observations that I did in near-infrared and in H-alpha. So in infrared, we look into YJH and K bands, and in simple H-alpha bands. And we have two epochs in the archive for the near-infrared, both in 2016. And we have new observations this year in 2025, 9 years later. Similarly, for H-alpha, we observed the system 9 years ago and now. So the colors here encode for the wavelength. So blue, the bluer the shorter, the redder the longer. And I put in all the panels the same ellipse is for visual comparison. And we can see that B is detected in all the epochs, all the wavelengths here. and its presence in HN-FA confirms that it's accreting, and its accretion rate is around in the order of 10 to the minus 10 solar mass per year. And B has moved already, as you can see here, like clockwisely, more than half of its orbit. But apart from B, we know B already. Apart from B, we detected a new signal, very red, in near infrared, as we can see in the archive epochs, and also a tentative detection of a very red signal that might be CC, the candidate companion, as we call it, in the new epoch. There's also a very faint signal close to CC in the archival epochs, but because it varies with spectral channels and with time, so we doubt that it's just dust of material around, but CC seems very stable across both the epochs in the archive and both in H and K bands, except that in the latest epoch, it appears, if it's a CC here, it appears very close to B, and B seems like 100 times brighter than CC, so it outshines CC, and we cannot really retrieve the photometry of CC to compare. So in simple, we don't detect CC. It might be because CC is not accreting, or because it's too faint in this particular band. However, we do have some signals resembling these structures, and I will show you more about this later. I put the contrast curves of all the observations and the CC detection here. So by converting these contrast curves to mass limits, we have the first hint of mass of the CC, which must be at least around 20 Jupiter masses. And we also retrieved some low resolution spectrum of all the signals of interest, including CC over here. And we can see that CC appears very red comparing to all the panels we have here. And there's a big discrepancy between the two epochs in the archive. This could be because in the second epoch in 2016, CC and the dust signal are very close, so it's also challenging to distinguish between CC and dust. But in the first epoch of 2016, we could entangle between these signals. We also put the position of CC and CMD, and in JH, CC, not surprisingly, is very red, but in K1 and K2, CC appears to follow the evolution tracks and gives us also a hint about its mass from 20 to 50 Jupiter mass, conformed with what we saw before. We also tried the SED feeding of CC because it's very red, so we accounted by assuming a disk for the infrared excess and also the extinction, and we can say that we have the estimated mass of CC from 2000 to 3000 temperature and mass of it could be around 30 Jupiter mass also. Well, I would like to go to here first and I go back there. So we also observed some spiral-like structure in HN-FA, as I showed you before. But before it was also with continuum emission, so we didn't see well. So here is a line emission, H alpha, and we can see this kind of structure seems to evolve with time, and it rotates, but its speed also moves also with the radius of with the separation with the star. So first, we speculate that this is accretion flows going into the star, because as we know, H alpha tracks the hot gas accretion, and also this conforms also with the ANMA observations, in which we observe non-Keplerian motion, gamma motion, and also due to vortex, might be due to Rossby wave instability. So going back, this is what we try to do to have more information of CC, because we don't have much, don't have enough data points to constrain its orbit. So we try to run the simulations to have estimation about its parameter space, and it seems to be that CC could be quite farther away with lower eccentricity, or closer with higher eccentricity, and it could last up to 0.3 mega-year in this case. So yeah, just to summarize, I just present our discovery of the CC and its tentative detection that we have with our observation this year, together with the observations of accretion flows that evolves through time of the system. Thanks for your attention.
Questions? We have a question there.
Lovely work. Just to be a little bit a devil's advocate now, what are your best arguments to support that this is a companion candidate and not maybe a disk feature, scattered light? Because one of the images you show, it seems to be really a little bit elongated, no? So the first impression I had by looking at the image, okay, this is a scattered light from this component, and the fact that, you know, the flux is brighter when B is approaching may support that, but maybe you have...
Thank you for your question. We also, yes, we noticed that in the tentative detection, CC seems to be very elongated. It could be also due to the faint signal that we also observed in archival epochs of CC, which appears also very red also. And well, for now, we don't have better speculations rather than that does material closely stays in this specific location, which is very active and dusty of the system.
Okay, thank you.
Time for one more question. Okay, let's thank Anne again. Thank you. Next speaker is Susanna Jonzig from University of Leeds.
Hi everyone, I'm Susanna Jonchik. I'm a third-year PhD student at the University of Leeds. I'd like to thank the organisers for giving me the time to present my work today. And I'd like to talk to you about CO depletion in MHD wind-driven protoplanetary disks. I'd like to begin by talking about the importance of disk composition. Protoplanetary disks are the birthplaces of planets, So the mix of gas, ice, and dust they contain will determine the types of planets that can form, whether they end up rocky, gaseous, or icy. Certain molecules such as CO2, methane, water, and organic molecules are key precursors to life. So the snow lines of these molecules can provide us with an indication as to where habitable worlds could form. And they provide a direct link to the molecular spectra we observe from exoplanets. An important concept is the carbon budget, which describes how carbon is split amongst gas phase species, solid ices, and dust grains in the disk. In the interstellar medium, most of the carbon in the gas phase is in CO, with a relative abundance of about 10 to the minus 4 relative to hydrogen. CO is important as it's the most widely used tracer of gas mass, telling us how much material is available to form planets. And comparing CO emission to continuum observations allows us to track gas-dust differences in substructures, as we can see in the CO maps from the MAP survey in the top panel, and the continuum observations from the D-Sharp survey in the bottom panel. As the C/O ratio in gas and solids affects planet atmospheres, any changes in the CO abundance within disks would have significant consequences for planet formation and composition. But ALMA surveys present us with a puzzle. They show that CO is often depleted in protoplanetary disks by factors of 10 to 100 compared to the interstellar medium. This figure shows CO depletion plotted as a function of disk radius. And we can see that in all 5 disks, there is significant depletion. There are 2 possible explanations for this depletion. The first is the sequestration of CO into the midplanes of protoplanetary disks. This occurs as dust grains grow and settle. They can lock CO ice into the midplanes. But this temperature is particularly sensitive to temperature, grain size, and disk location. The second process is the chemical reprocessing of CO into less volatile molecules. But this requires sufficient ionization, for instance from cosmic rays, and typically operates too slowly to explain the observed depletion timescales. So the key issue in both scenarios is the timescales. ALMA surveys show significant CO depletion, even in young disks. This plot shows a CO abundance as a function of age. And we can see that TW Hydra is around 8 million years old and shows CO depletion of about 100 relative to the interstellar medium. IM Loop is only 1 million years old, but also shows significant CO depletion. So these observations suggest a timescale of around 1 million years for the onset of significant depletion, which is much faster than most models currently predict. To understand this discrepancy, it's useful to compare the timescales of different processes acting within the disk. Freeze-out occurs very quickly, taking only minutes to days, but the key limitation is how quickly CO-rich gas can be transported to regions where it's cool enough for freeze-out to occur. Vertical mixing takes about 10 to the 4 to 10 to the 5 years, and chemical conversion and grain growth both take 10 to the 5 to 10 to the 6 years. Radial mixing is slower, taking 10 to the 6 years, and photodissociation can take anywhere from hours to years, depending on radiation levels. Zhang et al. 2019 showed that vertical mixing plays a crucial role in CO depletion, as the timescale is not negligible compared to disk lifetimes. And CO emission arises from the warm surface layers, where freeze-out doesn't occur, as we can see in the CO emission surfaces in the bottom figure. In these upper layers, chemical processing would be the main pathway for CO depletion. So why does timescale matter? Most current models find that neither dust growth nor chemical processing alone can reproduce CO depletion levels on the right timescales. Some models, such as those of Kreit et al. 2020 and Van Klepper et al. 2022, have managed to achieve the expected levels, but only with all of the processes combined and strong turbulence. When turbulence is weak, the timescales simply become too long. So this motivates us to consider additional processes, particularly the role of magnetically driven winds. ALMA observations of thin millimeter dust layers near the midplanes suggest weak turbulence, with alpha values less than 10 to the minus 3 and possibly even less than 10 to the minus 4. We can see this in the top figure, where the color scale is the dust image by HST, and the contours show the dust image by ALMA. So this points towards an important role for MHD winds in the outer disk. In wind-driven disks, weak turbulence would limit CO diffusion to the midplane, but at the same time, the winds would carry away CO-rich gas. So the question becomes which effect dominates. We currently have two models for the evolution of protoplanetary disks. The first is the viscous model, where angular momentum is transported outwards while mass flows inwards. And this replenishes the outer disk with CO-rich gas over time. And this is often parametrized with the alpha viscosity model. The second model is the MHD wind-driven model, where angular momentum is extracted vertically by magnetized winds, and mass flows inwards. In this case, gas is removed along the field lines, extracting CO-rich gas. But this means that the outer disk would not be replenished, as in the viscous case, which could possibly shorten the CO depletion timescales. So to study the effect of MHD winds on CO depletion, we use 1D dynamic models of the vertical structure, incorporating turbulence, vertical settling, dust coagulation and fragmentation, ice adsorption and desorption, and MHD winds for those models. We use the QDISC code to run the models, and we model a full distribution of grain sizes. Winds are modeled using constant vertical mass flux, with stronger winds producing faster removal of gas. In the viscous disks, diffusion is the main mode of transport. And the disk temperature is updated self-consistently throughout our simulations. So here I show some results at 100 AU from a solar mass star with strong turbulence, so alpha of 10 to the minus 3, and a strong wind for the MHD case, which corresponds to a mass loss rate of around 10 to the minus 9 solar masses per megayear. On the left, we have temperature plotted as a function of vertical scale heights. And we see over time that the mid-plane temperature in both disks remains similar, as this is only due to the reprocessed radiation. But the wind-driven disk shows cooler surface layers due to a different grain size distribution, as the small dust grains are entrained in the wind, and the presence of larger grains allows for more efficient dust cooling. And on the right, we have CO abundance, both gas and ice, plotted as a function of vertical scale heights. And we can see that over time, the snow line gradually moves inwards towards the midplane as dust grains grow and settle, locking in the CO ice and depleting the CO gas from the upper layers. Both models currently reach modest depletion factors of between 3 to 6, but we believe this is because it's still quite difficult to explain depletion factors of 100 on short timescales only with the physics. When we lower alpha to reflect weak turbulence, the differences become clearer. In the viscous case, diffusion slows down, and we achieve only about 50% of the CO depletion seen in the strong turbulence case after 1 million years. But in the strong wind case, the wind prevents the small grains from settling, which offsets the effect of slow diffusion. And this keeps CO depletion on million-year timescales. These results suggest that it's the diffusion timescale that sets the rate of depletion, and MHD winds provide an additional pathway for the removal of gas. We also explored how depletion changes with radial location in the disk. And we find that generally the outer disk regions show stronger depletion because of the lower temperatures. And this effect is especially pronounced in the viscous disks. But we would expect that that beyond 200 AU, depletion would be weaker and consistent with observations. In some of the wind-driven cases, we could see that the relative CO abundance increases after 3 million years, but this is because gas is being removed faster than CO. While our models currently reach maximum factors of between 3 to 10, if we were to include the radial drift in our models, this would remove the large dust grains and possibly increase the depletion levels that we reach. But because we would also be decreasing the dust abundance, the overall effect might not be huge. If we were to include the chemical processing of CO to less volatile molecules, this would definitely decrease the overall CO abundance and increase the depletion levels reached. So to conclude, we find that it's the diffusion timescale, hence the strength of turbulence, that controls the rate of depletion. And where there's evidence for weak turbulence and early onset of depletion, this suggests that the presence of MHD winds. And our future work will focus on implementing chemical processing into our models. So thank you for listening, and I welcome any questions.
Thank you. There.
Thank you for the nice talk. I was wondering, have you done these for any more massive stars or different luminosities? Like, how does that affect the timescale for things? Is it helpful? Is it not helpful?
I haven't looked at that yet, but that would be really interesting. Yeah.
Here, we have a question.
Hi, thanks for the talk. Just wondering what kind of chemical processing you're thinking of including and what might be the most significant?
For example, the hydrogenation, and we plan to include a full chemical network. So, yes, so all of the possible reactions. So grain surface chemistry and gas phase chemistry together. Yeah.
He has a quote for that.
Yes.
One more question there, Diego.
One thing that came out of James Webb's observation of disk is the possibility that the ices are not in pure form, but they are mixtures. So if you get CO and CO2 ices, you might have the depletion of CO that, however, survive until the inner region of the disk, at the CO2 is no line, so you might have the depletion without having to invoke different chemistry or more complex chemistry. It might be just that you get a mixture, so you're driven by the more refractory ice of the two.
Yes, that's a really interesting point. I think there is work currently being done to look at if you have mixtures of ices, how that would impact the snow lines, and how we can possibly include that in the models. But it would be really interesting to see what effect that would have on the results. Yeah. Thank you.
There is time for one more quick question. If not, then let's thank Susanne again.
Thank you.
Thank you. So the last speaker of this session is Hinur Han from Caltech.
Great. Well, hello everyone. So I have the honor of giving you the final talk of today, focusing on debris disks. So we've heard a lot about the planet formation context in the conference so far. Eventually the protoplanetary just disperses, and from it emerges a planetary system, which includes maybe planets and maybe also belts of planetesimals, and the latter of which is the sort of main component that we consider to be debris disks, which is also the focus of this talk. And so just I guess to show you a diagram of the solar system, this is the solar system debris disk main component, which is the Kuiper belt. There's also the asteroid belt shown in the diagram, but that's generally very difficult to resolve spatially. So I guess for the purpose of this talk, we'll consider debris disks to be the analogues of the Kuiper belt. There are different dust grain sizes in debris disks, which are all produced through collisions, that we think. And looking at different dust grain sizes reveals different physics. For example, the smaller grains could be affected by radiation pressure and therefore be blown out of the system. So that creates a disk halo shown on the diagram at the top. And grains that are slightly smaller than that are very significantly impacted by point Robertson drag, and that can create a sort of warm dust component interior to the main belt. So this talk focuses on the ALMA observations, which are sensitive to millimeter-sized dust, which we think is largely unaffected by these forces. So we think that these are a good reflection of essentially where the planetesimals are actually living, which themselves are not possible to detect. So here's a gallery of the ALMA imaging so far, I guess, before some of the high-resolution observations that I'll go into the details of later. And so a lot of these are not sort of super well resolved, but I guess there are still useful information that we can get from a lot of these disks. So for example, you can get the radius. Here on the left is showing the radius of this sample of disks as a function of the luminosity of the star. So if you take the view that the luminosity determines where the ice lines are, which they probably do, but if you consider these to be locations where you form dust traps and eventually planetesimals, then you should expect a correlation between the luminosity and the radius of debris disks, which we sort of, I guess, maybe see, but there's a very high scatter trend, so I guess there's something more complicated going on. And also, the dust mass is a very fundamental property of debris disks. Debris disks are sort of, I guess the evolution is dominated by collisions, and these collisions will eventually run down and deplete the disk. So you should expect the dust mass to go down as a function of age, which is also what we see from these observations, and also from unresolved, I guess, JCMT submillimeter observations. Which brings us to, I guess, the main focus of my talk, which is on some recent observations of debris disks at very high resolution as part of the ELMA survey to resolve exo-Kuiper belt substructures. I guess from the images earlier, we can see that sort of only so far you can tell from lower resolutions. So we're primarily interested in this program in the prevalence of substructures. So essentially things like gaps, for example, radial gaps in debris disks. This is about, I guess, 300 hours of ELMA time, which gives 18 new disk images. 6 of these in the gallery of 24 also satisfy the sample selection criteria, but have pretty good archival observations. So we'll just use that for the analysis. And yeah, so I guess I'll give a quick overview of some of the results and analysis that I've been doing, and also as part of the broader ARCS team. So I guess to start with, here's a gallery of all the deconvolved and deprojected radial profiles of all the disks that we've looked at so far. And I guess the sort of the biggest feature of the sample is that they have a very large diversity. This really messy diagram on the right is just sort of just for fun, but to show you, if you normalize the radius even by luminosity, then you still get this sort of huge range of different shapes and even extent of these belts. And on the left, so on the top, you can sort of see examples of disks that are sort of very clearly multi-ringed, and then there are other ones that are they have sort of a prominent single ring with a very large range of fractional widths, but they also, I guess, differ from a very, very simple ring in the sense that, especially some of the narrow ones, that you can quite obviously see that there's a halo, which we think is real, either on the outer edge or perhaps on the inner edge, and in some cases, perhaps even a sort of additional little ring with a gap separating it from the main belt. And I think I guess I skipped this slide earlier, which the point of this is to say that I guess now we finally have a sort of a decent-sized sample of debris disk observations, which are really faint and hard to observe. But we have these observations at comparable resolutions to, say, D-sharp of protoplanetary disks, and even earlier evolutionary stages that target class 0 or class 1 disks. And with that, we can kind of try and do some comparison of those structures. The plot on the left is showing you the distributional fractional width, so the number of AUs that define the width of an individual ring in the disk divided by the sort of central radius, so it's dimensionless. So this shows that quantity, the distribution of that for both debris disks and protoplanetary disks. And I guess the sort of what was relatively new to us is that a lot of the debris disk rings, when viewed at these high ELMA resolutions, are actually sort of just as narrow as protoplanetary disks, which is quite interesting. And also, there's a sort of pretty broad fractional width population of debris disks, which is here, which don't really have as clear of a sort of counterpart in the rings of protoplanetary disks, which I think is also quite interesting. If you sort of focus on those, I guess if you plot essentially fractional width in that sample as a function of age, then there's sort of this missing bottom right-hand corner here, which corresponds to, I guess, all disks that are quite narrow. I think that's quite interesting. There could be sort of observational biases for that, or there could be some, I guess, real radial evolution. For example, the disks could broaden over time, either by scattering amongst the planetesimal scattering amongst themselves, or maybe a planet came in analogous to what Neptune did to the Kuiper belt, and that could create a high eccentricity component to make the disk seem wider over time. And also, it's interesting to think about what this says about planets. So this plot here is a sort of very simplistic scenario, which is assuming that if you have a planet living in every gap that we see in the sample, and it hasn't migrated, and it has a circular orbit, then what kind of mass and radius that planet should have, and that gives you this population shown here, which they seem to be, I guess, reasonable planets, and I think almost all of these. Most of these, I think, from my understanding, consistent with non-detections so far in these systems, and yeah, but not too far off from the detection limit, I guess. And interestingly, on the right, that's sort of like some I guess earlier work based on protoplanetary disks from a more sort of hydrodynamical perspective to constrain planets from gaps based on the D-sharp sample, and you get a sort of, I guess, somewhat similar population, which I guess is just interesting to put side by side. I'll also say something about the vertical height, I guess. So this is work done by Brianna Zawaski, who is quite impressive that a lot of a big part of the sample was selected to be edge-on disk, so that you can actually get the scale height measurement if you have high enough resolution, which we do have for a lot of these disks. So some of those are marginally resolved. We could still say something about sort of the height. Yeah, so a lot of these heights come out to be, we're talking about the scale height aspect ratio here, so H/R. They come out to be quite small, so sort of 1% or even less, or maybe a couple of percent. And from that you can try and say something about the mass of debris disks, which, as you might expect, is quite difficult to measure because you can't actually see that the largest bodies would actually contain most of the mass. But if you assume the vertical height is a reflection of the inclination dispersion excited by sort of self-stirring, so the planetesimal stirring amongst themselves, then you can get some sort of estimate on what the sort of masses you would expect the disks to be. And they come out to be, I guess, it's quite a large range, a couple or a few tens of Earth masses here, up to about 100. And finally, just I guess quickly, this is work by Josh Lovell looking at the asymmetries in the sample. So debris disks generally look quite symmetric in the millimeter, unlike some of the images you may have seen of debris disks in scatter light. But we do see asymmetries here, especially in 121617. There's quite a clear crescent, and potentially in these other systems as well. And if you really sort of try and characterize the sort of cell location versus the disk center, you can identify some likely statistically significant offsets, which could be indicative of an eccentric disk, and also brightness asymmetries over here, which are quite subtle. So that does rely on very careful characterization of the noise in these observations. And also this one disk that is potentially warped. So I'll finish here and I'll leave the conclusions.
Thank you. That was pretty fast. Questions? Yeah.
Hi, thank you for the nice talk. I was wondering if we now think that we have these narrow debris disks, but we still have the broad ones, which are like kind of, we don't see in protoplanetary disks. Is there a way to like disentangle what's actually causing the broad ones, or do you think it's like the same effect or migration?
Yeah, I think that gets into the heart of like how like planetesimal belts form. I guess one view could be that if the rings in protoplanetary disks just like become belts of planetesimals, and if, as you can see in the histogram, they're quite narrow in the protoplanetary phase, then you form narrow debris disks. But these rings could migrate for various reasons, like if there's a planet like pushing it, or for example, for whatever reasons, I guess pebble drift could cause bumps that migrate. So if it migrates, then wherever it sweeps through, it could leave sort of planetesimals in its path, and that could create a broad debris disk. And then there's the subsequent evolution as well. So once the gas is gone, maybe continued evolution would also broaden the disk for whatever reason, either planets or amongst themselves.
All right, thank you.
Maybe. Do you have another question? No. Maybe a naive question. You showed the radial profile at the beginning. But doesn't the fact that you have these different inclinations affect that as well?
Yes. So
how do you account for that?
Yeah. So those are not just derived directly, sort of from the image, those are fitted,
Okay.
essentially. But they're fitted they don't look like they're fitted because they're fitted sort of non-parametrically without assuming a model. There are different tools to do it in either image space or visibility space.
Okay.
The profiles I showed use a method called Frank, which does deconvolution and deprojection in visibility space. So you can actually directly go from ELMA visibilities to a radial profile that is deconvolved and deprojected without you having to assume a model. The benefit of that is, you can sort of avoid the bias of assuming a wrong model. Yeah.
Okay, then let's thank Hino again and all speakers of this afternoon. Does someone need to say, well, I'll say, please vote for the poster. And I guess we see each other again at 7 there. Good. Thank you.